Good morning, everyone. Dear friends, we sincerely thank everyone for joining our second tutorial on large-scale holistic video understanding. I'm Vivek Sharma, welcoming you on behalf of our HVU Organization Committee. In this tutorial, we intend to put an effort in introducing holistic video understanding as a new challenge in the vision community. This tutorial focuses on learning a generic feature representation towards challenging holistic video analysis, recognizing scenes, objects, actions, attributes, and events in the real world and user-generated videos. In this tutorial, we also aim to cover important aspects of video recognition and understanding, such as future prediction in video, multiple object recognition in videos, object and activity detection in videos, weakly supervised learning from web videos, learning visual representation from videos, unsupervised and self-supervised learning with videos, 3D and 2D deep neural networks for action and activity recognition. Our HVU dataset is organized hierarchically in a semantic taxonomy that focuses on multi-label and multitask video understanding as a comprehensive problem that encompasses the recognition of multiple semantic tasks in the dynamic scene. Our dataset approximately has 572,000 videos in total with 9 million annotations for training, validation, and test set spanning over 3,142 labels. HVU encompasses semantic aspects defined on categories of scenes, objects, actions, events, attributes, and concepts, which naturally capture the real-world scenarios. In our today's event, we have 8 prolific speakers. We tried to make our event inclusive by bringing community from academics, corporate researchers, and entrepreneurs. All the talks from our event will be shared online and will be available to the general population in the next few days. Here's our today's schedule. Now I would like to pass it over to Shamil. Thanks.
Hi, everyone. I'm Shamil. I'm a PhD student with the Stanford Vision Lab, and I'll be moderating the morning session of this tutorial. We have an amazing lineup of speakers today. As an overview of our schedule, we'll have 2 sessions, one in the morning, one in the afternoon, with a 30-minute break in between. Each talk will be about 50 minutes long or so, with the remaining 10 minutes at the end for questions. And we'll be using the Zoom webinar interface to collect and moderate the questions. So please submit any questions that you have through there. This slide here is for our morning agenda, which will go from now until 1 p.m. Eastern time. And on the next slide, we have our afternoon agenda, which will resume after the break at 1:30 p.m. And you can also find this agenda on the tutorial website. Today's first speaker for the morning session is Hilde Kuehne, and she is an assistant professor at Goethe University Frankfurt and an affiliate professor at the MIT-IBM Watson Lab. And earlier this week was also the recipient of this year's TC PAMI Helmholtz Award at ICCV for foundational work on the HMDV dataset. We're very excited to have Hilde with us today, speaking on video understanding without labels. Hilde, the floor is yours.
Thanks so much, and thanks for the introduction, and thanks for having me. So as you already heard, my talk today will be about understanding videos with less labels, and mainly it will kind of like span 2 areas which are not so prominent but very interesting. First, unsupervised learning, and second, multimodal learning. And hopefully I can at the end of the talk even build a bit the bridge how they relate to each other and how they can help us to understand videos a bit better. I'm actually planned probably for 45 minutes roughly, so I hope we can have a bit more time at the end to discuss, because I think there are a lot of interesting things going on at the moment, especially with respect to video understanding, and it would be great to hear some kind of like opinions on how things can get going or where we want to go and how to unravel this whole field. Okay, then let's get going. First, let me actually see. This workshop is obviously about holistic video understanding, and thanks to Vivek and Musan and all the people who worked so hard on getting this holistic video understanding topic going. Just as kudos to have come up with the idea and to remember everyone what we are talking about. So today we want to mainly talk about models for comprehensive and video understanding tasks, so that we actually can kind of like move away from kind of like a solitary understanding of action classification means video understanding. And technically, I was thinking a bit about how to approach this whole thing of holistic video understanding. And I know the data set itself is more targeted towards different aspects like semantics, object detection, and so on. But they are also kind of like beyond just the let's say, plain tasks. There are different areas that actually come into mind when we think about video understanding. The most basic dirt digging part is probably that guy here who's doing the representation learning, who's kind of like training or kind of like burning a lot of carbon on a lot of GPUs to actually provide the community with better representations to work with. And technically, the guy that's most reliant on this representation learning guy is the one that sits here, actually wants to do the action classification, because there is no good action classification without good representations. And now the crowd gets actually a bit more interesting, because it's not only those two guys actually working in this field. We also have people who kind of like rely a bit on classification and then go one step further and do temporal action detection. Terms of not classifying clips, but actually finding action instances in long untrimmed videos. Then we have two more people standing around who are doing pose detection and video object tracking and video segmentation, which is also a very hot area at the moment. Then we have this guy sitting over there who does multi-object tracking, which is also interesting if you want to understand a video, but technically not so much incorporated at the moment. And then we have spatial temporal action detection. And finally, we have temporal action segmentation. And they all kind of like address the problem of how to understand videos, but from very different perspectives. And the first part of my talk today will actually, and technically to get there, so to understand videos, we have different tools. So the dirt that we are digging around is usually, or was till recently, mainly made up of fully supervised learning. But then we actually kind of like extended a bit to weakly supervised learning, unsupervised learning, which I will talk a bit about later. And currently where representation learning is mostly digging in is, I guess, self-supervised learning. And then obviously we also have multimodal learning. So we have a lot of different ways how we can actually shuffle our stuff. And today's talk, and that's actually what I wanted to tell before, is mainly going to be about that guy here, who's actually kind of like texting his boss all the things that representation learning and action classification is digging out, so that someone can actually do something with it. And the question is kind of like, with all the stuff that he's texting his boss, can temporal action segmentation actually do something for this holistic video understanding? And the idea why kind of like temporal action segmentation might be interesting for a holistic understanding of videos is kind of like baked in the task itself, because temporal action segmentation mainly means that you have an untrimmed video and that you actually want to put a label on each frame in your video. And technically, you can easily do that by kind of like just classifying each frame independent from the rest of the video. But practically, and this is now where usually the temporal segmentation people come in, frames have some relation. So usually when frames are temporarily close together, they probably represent the same action just because the way actions are structured. And then second, when you think about a video of having more action segments, sometimes they are also related. So for example, as you see here in the video, when you want to make a fried egg, usually you crack an egg and then you add the salt and then you mix it, you put it in the pan and so on. And temporal action segmentation is all about figuring out those small kind of connections as well as the big overall picture of your untrimmed video. And this is kind of like where we can say, okay, action classification is good. But when you think about temporal action segmentation, it's just the beginning of video understanding. Mainly because what action segmentation can do for you is putting labels on small segments, like for example, clips. And clip is actually an interesting unofficial undefined unit here of, let's say, roughly 30 to 150 frames. So it's mainly the input to your 3D neural network that you use to classify atomic actions. But it's not, and produces some nice results, but sometimes you want to have a bit more context. And the other way is those kind of like clip classification usually provides you with one label. And obviously at some point, you don't want to put too much load on this poor network if you can actually kind of like come up with more stuff from different workers. So when you think about how action classification relates to temporal action segmentation, it's kind of like a useful tool, but it's not the only tool that will give you a holistic understanding of your video. Question is, why is temporal action segmentation actually a topic at all? So why are we not done with just running clip classification and just collecting scores? And the answer is exactly what I told you, structure. The part that when you just consider a single video, obviously you lose all the structural information, and temporal segmentation is all about finding exactly this representation or this representation that captures the structure of your video and therefore of complex action sequences. So looking at old and new ways to get there, actually a lot of people have built very cool systems that actually think about, okay, how can we make sense of more temporal information in our video? We had some early work at CVPR 2017, which mainly was built on dynamic programming and single observation responses. Colin Lear had same year actually a very interesting paper which kind of like defined the second branch, which was based on temporal convolution. So where you say, okay, multiple frames actually make up one deconvolution, and then you can build encoder-decoder networks that actually do exactly the segmentation by taking more temporal context into consideration. And finally, network or an architecture that's still heavily used today is MSTCN, which is mainly kind of like using the idea of temporal convolution networks, but combining that kind of like with Google WaveNet style to have a multi-stage temporal convolutional architecture. So those are kind of like the ideas that are currently in the air and that are used by different also current works. And technically, they all try to get this temporal segmentation, but now you can ask, okay, we have those things and then we have temporal action detection. Aren't those two related? And the answer is a clear yes and no. And to kind of like make the difference a bit clear, this temporal action segmentation usually means that when you have an untrimmed video, you have more than one action class in this video. Then second, in your untrimmed video, you usually assume that you have a dense segmentation, which means each frame is labeled. But what's also important is it's not the majority background. It's really kind of like only a fraction of your overall video, more or less. And finally, what's assumed in temporal action segmentation is that all the actions that you have in your video, which we learned is more than one action class, actually have some temporal relation. Like the beginning video that you saw, cracking an egg, adding salt, mixing it, and so on, they follow a certain logic. And this is exactly the thing that we want to grasp with temporal action segmentation. On the opposite side, or on the other side, temporal action detection technically can do the same, but currently is a bit different in terms of that most kind of like baseline data sets or benchmark data sets don't have too many action classes in their untrimmed video. So when you think of tumors or ActivityNet, those would be the references. They usually have 1-2 action classes per video. Then the segmentation is actually very sparse, which means you have background, and then you have a short incident where the action that you want to detect actually happens, and the rest is again labeled as background. And this is probably the most interesting difference that's not so appearing, is that in action detection, you actually assume that all the actions you want to find are temporally independent. So you don't assume any relation between one action or the other. And when you think about it, actually makes a lot of sense, because temporal action detections mainly apply to things like, for example, sports coverage. And envision when you have a golf tournament and you want to detect all golf swing motions, then you have an edited video and they appear sometime within your news coverage, but you cannot actually tell, okay, they will definitely appear after something else. They will just be there at some point. And what's actually interesting is if you want to tell apart if a paper actually deals with temporal action segmentation or temporal action detection, you can actually easily look at the qualitative examples, because for temporal action segmentation, your qualitative examples will always look like, let's say, a colorful bar plot, where actually what you saw before, each frame is kind of like associated a certain action class. Whereas temporal action detection will also be a bar plot, but here it will usually be a unicolored bar plot. So it will only kind of like differentiate action versus background, but not have multiple colors in here. So technically, I guess we can easily train network to tell papers of those two classes apart. Beyond that, temporal action segmentation also has a number of data sets that we usually work with. The upper ones are actually the older ones that are not so commonly used at the moment. The core data sets, I guess, are 50 salads, breakfast, INRIA YouTube instructions, and GTEA for the representation of the egocentric community. And those are the data sets that we usually use to kind of like train our models on and evaluate and so on. Problem is, we need a lot of training data. And obviously, and this is where we come to the unsupervised learning part, at some point, if we want to train more fancy systems, it's completely unrealistic to label any of that by hand. And this is actually why the community moved a bit in terms of how we want to train our systems. In the beginning, obviously, we relied on supervised learning because, yeah, that's what's there. But let's say starting from 2015, 2016, more and more people actually said, okay, this with the fully supervised learning part is nice, but it's definitely not getting us where we actually want to be. And therefore, they thought about other ways to train without having to annotate each frame. And this is where weekly supervised learning came in. And technically, weekly is a bit kind of like ambiguous because everything can be weekly. In this case, it was actually a bit more specific in terms of that you were assumed to be given a sequence of input data, meaning the videos. And then you actually assumed that you were given transcripts. So the list of the order in which the actions occur in your video, but you don't know where they start and where they end. So your job was actually, or is actually, if you want to do that, to infer the actions that you get in your transcript, and then actually learn the boundaries during training, which is pretty cool and works kind of like pretty well. And then but technically the problem is you still need those transcripts. And obviously that's a limitation, because even annotating transcript data doesn't come for free. So it's nothing that you can scale up to, like, let's say, millions of videos. And therefore, more people actually started to look into unsupervised learning, where the idea is you're given a bunch of videos, period. And best case you can hope for is that you probably know an activity label for your video, or you don't. But no matter what, your job is to detect co-occurring actions in your video data without having any context or any information about what's on. And technically, the first work on that was by Fadime Senner in, I guess, 2018 at CVPR. Kind of like one of my students, Anna, picked up on that, and we actually had a look into this problem of how can we learn sequential actions in unsupervised way. And this comes with two interesting kind of like quirks, because first, as I already said in the beginning, there are some things that can help us. First, obviously, we have visual similarity. When something looks visually similar, we have a high chance that it belongs together. But beyond that, we also have, as we are looking into the temporal aspects of our actions, we also have the information that when frames are temporally close together, they probably have a higher chance of belonging to the same actions than when they are kind of like temporally further apart. So that's one interesting idea, how we can kind of like get a bit better than just kind of like clustering basic visual embeddings. And the second idea, and this is also related to the way videos are built, is that technically we can not only look at are frames temporally close together, so do they probably rather belong together than to another action, but also do frames happen in the beginning of a video, or do they happen at the end of a video? And to give you an idea why this is actually relevant, one of the action categories that we have in one of our data sets in INRIA instructions is actually instructional videos on how to change a tire of a car. And technically, changing a tire has an interesting visual structure, because first you have to unscrew all the bolts of the tire you want to take off. Then you have to take off your tire. Then you get a new one, you put on the new tire, and then you have to screw the bolts back in place. And you can imagine screwing off bolts versus screwing on bolts looks technically completely identical. There's no way you can tell from like a single 1 second frame if someone's screwing on or screwing off. Except when you're probably mechanic, then you get it from the way it's turned. But let's say it's very similar in a visual way. And the only thing that's actually different is one happens in the beginning of a video and one happens at the end of a video. So getting the timing right is actually an interesting problem in this whole context. And this is what this paper has mainly done. So the idea was very simple. We know we have some frames which have a visual appearance, and now we also want to learn, we want to kind of like tell them where they appear in the video. And therefore what we mainly did is we took input features and actually had kind of like a surrogate task where we mainly trained the network to predict the timestamp of each frame given a certain number of input features. And the cool thing that's actually happened when you're going to do this is you learn an embedding space. And I will talk a lot more about embedding spaces, but this is a very simple one, which is actually pretty cool because you have an embedding space which combines visual information and temporal information at once. And then when you cluster in this embedding space, first you kind of like already put frames together that are temporally close, but you also build clusters around frames that happen in the beginning versus frames that happen in the end. And you can use that and actually kind of like even put timestamps on each cluster when they appear, and then use those timestamps to, for example, segment videos. So in this case, we could show that we were actually better than state of the art, mainly because there was not much state of the art at this point. But technically, it worked kind of like okay-ish. One interesting thing that's kind of hidden in the comparison to state of the art here is actually the fact that, let's say we are very optimistic about our numbers. Because one problem that we have when we actually want to do unsupervised learning is at the end of our whole training procedure, we mainly end up with clusters. Let's say cluster 1 to 10. Problem is now, if we want to compare how those clusters match the ground truth, we don't have anyone telling us, okay, cluster 1 match is this one, and cluster B, cluster 2 is action B. So to evaluate what actually happens is, and this is not our thing that we use to optimize numbers, this is just how the benchmark works. You take all the clusters and you take your ground truth action segmentation, and then you actually do Hungarian matching to optimize the overlap between your clusters and your segmented actions. So technically the numbers that you see here, especially the 41%, is kind of the best upper bound that we would get if we would know all the ground truth data. So it's not directly comparable to numbers that you get from fully supervised or weakly supervised classification. But anyway, it kind of like worked pretty well. And then actually another student of mine had an idea how to extend that. So we had the same kind of like pipeline. We want to learn some joint visual temporal embedding. Then we want to do some clustering and decoding. And the interesting question is now, do we get this joint visual temporal embedding right the way we do it? And obviously the answer is maybe, because technically this temporal, the simple temporal embedding is destroying a lot of visual information. So therefore we thought, okay, let's see what we got when we actually combine this temporal loss and some visual loss that we actually train to predict frames rather than to just reconstruct them. So they should have a bit of notion of time, but not too much notion of time. And technically, we have those two ways to train embedding spaces, and they are both kind of like okay, but we thought, okay, let's make it even more interesting. And what we can actually do to make it more interesting is we can say, okay, when we are able to predict how frames or how embedding will look like in the future, let's say in the next frame, then we can actually also put the temporal loss on top. And by doing so, we actually can have both losses, a reconstruction loss and a temporal loss, to train our joint visual temporal embedding space. And when we look at numbers, it shows that this was actually a good idea, because when we look at results of stage 1, actually unit loss is still already performing pretty well, but actually using this embedding space, which is actually trained with both kind of like visual reconstruction and temporal reconstruction, finally gave us the best results for this task. And actually, I have one more on that. And this is another interesting kind of like way to think about it in many ways, but let's focus on the problem of unsupervised temporal segmentation here. The thing you saw in both previous architectures was we learned this embedding space, but we never actually include clustering in the training pipeline. So clustering is kind of like a post-processing task that happens after your job is mainly done, to be honest. Which is obviously not very nice. And obviously it would be much cooler if we could actually include the clustering in end-to-end way in this whole training pipeline. But making clustering differentiable is kind of like annoying. And we know we have Sinkhorn Knop for differentiable optimal transport. We can also try to include k-means. It all has some quirks and it's not so nice. And one of my students, Sevita, actually had an interesting idea of leveraging a concept which was actually first proposed, I guess, by the University of Amsterdam. So actually by the person who will be the next speaker, I guess. And here the idea is actually to use latent nodes to capture your embedding space. So you remember so far we mainly tried to learn an embedding space which somehow captures visual and temporal information at the same time. And now we actually introduce latent nodes, which you can just imagine as some random anchor points in your space to actually form something like anchors for your clusters. So technically, we just reformulate our whole system in terms of not only saying, okay, I want a good reconstruction of the temporal position and a good reconstruction of the visual input. You directly say, okay, I also want those to be kind of like centered around the nearest cluster points. And as you can update those cluster points, you kind of have a baked in k-means in your overall training pipeline. And the way you train it is very easy. You have technically the losses that we had before, reconstruction for time and reconstruction for visual feature. And then you also have a contrastive loss part, which actually kind of like pulls each feature representation to its closest anchor and pushes each anchor and pushes all other anchor points away. And by doing this, we actually get a very interesting space that can do pretty cool things because you have to imagine the output we got before when we were actually assigning frames to clusters was very noisy. So we actually always had to put the decoding on top of everything to make sure that we got segments right and so on. And it shows that with this kind of like latent-based learning, actually we are not able to outperform the numbers of this joint visual temporal pipeline. But what we actually get is we get very crisp initial segmentation just out of this clustering. So the later decoding actually still is necessary to push numbers, but technically we already have a very nicely sorted video as output of this overall procedure. And that's pretty cool. And with that, actually, I want to make a slight break and jump to multimodal learning. This is now completely unrelated to everything I have told you so far, but it's going to be pretty cool anyway. And this actually goes back to like work of 2018 to 2020, which resulted in a web video challenge at CVPR 2020 that, to be honest, nobody cared about. So technically we had 3 submissions on this task, and actually we had pretty good prize money, but whatever. And the idea of this Web Vision video challenge was we want to kind of understand what's going on in videos without any annotation. So technically, how can we learn videos without labels? We already have videos and we already have a lot of information, which is mainly the speech when people are kind of like talking about instructional videos. And the good thing is YouTube is pretty effective in providing videos with automatically generated captions. So technically we have a huge amount of video out there with text and audio, and we should be able to make something out of that. And this is kind of like how the idea started of mining action samples from subtitles, and how this mining YouTube dataset kind of arose. And the idea was pretty simple. The idea was, okay, we have action classes, and technically when we find them in the ASR, we can use those samples to kind of like train videos for this class. So technically what we did is we downloaded all the videos and all the subtitles and then used NLP tagging to find verb-object pairs. Then we did a lot of filtering, a lot of pruning, and out came some 800 action object pairs that were kind of like cooking related. And then we again pruned it to 513 action classes. Was it a good idea? Actually, the answer is no. Because when you do that, you get a lot of old and new problems. The old problems that you could probably expect from this exercise is that you have a highly imbalanced distribution. So we have a lot of video samples, for example, for crack egg or put it or like generic stuff. And then we have a very long tail for stuff where we have only few samples. Second problem, we have obviously also a lot of noise, but also inconsistent granularity in terms of like people are describing stuff at different levels. But and then finally we have a lot of like noise in terms of not all verbal comments refer to actions that are actually in the video. So imagine even when you kind of go through all the subtitles and you look for instances like roll it, you will have a lot of stuff where people are actually saying roll it or we roll it without showing the real action. And actually we even did some math. So we are talking about 50% wrongly labeled clips, if you want to see it like that. Actually, when we use edited subtitles, it's a bit better. Then we get like 60% good videos. But anyway, it's a lot of noise. But the interesting problem is actually not all the stuff that we actually know about. The interesting stuff is the problems that we run into that we didn't experience before. And this is actually the inconsistency of semantic language. Because when you look at the classes that you get out of such an exercise, you will have a lot of homonyms, which means that you have multiple expressions that have the same meaning. So technically, for example, we have 3 action classes. One is beat egg, one is mix egg, and the other is whisk egg. And obviously, they are all going to represent the same visual content. And then the other problem is we have polysemies, which means we have one expression which actually refers to different actions. Best example is something like add pepper. Add pepper can refer to like this brown powder stuff that's added, or it can actually refer to bell pepper and then it's usually some green, red, yellow cubes that are added to something. And overall, when you kind of like take all this together and you just try to train an action classifier, you end up with like 10% IOU alignment on temporal segmentation, which is really poor, literally. So, and actually, this was one of the reasons why this challenge, I guess, never took off, because the baseline was 10%, and I guess the best one got in with 13%. So it was actually kind of like a tricky problem. But the good thing is I have kind of like an idea for you how we can make this better. And the solution on how to make this better is actually kind of like what the second part of my talk will be all about. And this is how we can actually do multi-model learning, and best case, even multi-model zero-shot learning. So without ever having seen a class. And the idea that I'm going to present has again to do with embedding spaces. And in this case, we want an embedding space which has some interesting properties. We want an embedding space which actually combines visual information and, let's say, textual information, or could be audio or whatever second modality you want. And technically, you can imagine for each video that we get, we kind of like push it to some neural network and we get a feature representation. And obviously, also, you know that for text, you can do back of words embedding, or you can do some neural net embedding with BERT or whatever your favorite text encoder is. And for text, you can also get some features. In the beginning, those features are just kind of like vectors that don't have anything to do with each other. But technically, what would be pretty cool would be if we could actually learn an embedding space, which can take, for example, a text feature and place it somewhere, and then actually get a video feature and also place it somewhere in this embedding space, and actually do this in a way that we form semantic clusters across modalities. So that something that, for example, talks about putting marinade on chicken will end up in the same region as videos that actually show stuff that puts marinade on chicken, or that the text which says rinse and drain soaked whatever beans and add it to the food processor will add up pretty close to videos that actually show exactly that. So that would be pretty cool. And therefore, I'm mainly talking now about how to get there. So I guess most of you are familiar with basic contrastive learning, but just as a kind of like very quick recap, when you have contrastive learning, technically what you want to do is you want to predict distances between two instances instead of predicting class labels. So the idea is you extract some features or whatever, and technically you have a neural network that when the input comes from, for example, the same class, you want the features to be close together. And when the input comes from two different classes, you want the features to be further apart. You play this a lot today with self-supervised learning, where you, for example, have two instances of an image that you want to be same, and two other instances of two different images that you want to be further apart. Obviously, this also works when you talk about multimodal learning, because technically we can not only make the network learn distances between two images, but we can also make the network actually learn distances between text input and video input. And that's pretty much exactly what everybody does. So we extract features from, take your favorite backbone for video, take your favorite embedding model for text, and then actually train a network that makes sure that when your text and video are from the same source, the distance is close in the embedding space, and when text and video are not from the same instance, then push them as far apart as you can. And obviously, and there are many works in the field. So technically, I guess it kind of started a bit with Antoine's How to 100 Million paper, which also came out in 2019. So actually, it's a very new topic, but pretty cool. And then we already have a lot of follow-up works with MIL and Cees, which was proposed in end-to-end learning. We have multimodal versatile networks coming up last year. And we have cross-model audio video clustering, which is mainly XTC, sorry. From Facebook. We have the C'est la vie network. So we have a lot of different things. And our take on that is actually more related to combining audio-visual representations than to just focusing on vision and text matching. And this actually comes with some other interesting works that I will discuss a bit later. So the first paper that we had, and actually it got just recently published on Interspeech 2021 because it got rejected like multiple times. But anyway, it's a great paper, so check it out. And actually this paper, AVLNet, is kind of like one of our most robust baselines. And the idea here is to do exactly what I told you, to learn a shared multimodal embedding space directly from raw video inputs. And raw video in this case can be obviously the visual signal, it can be the audio, or it can be text. And then the idea of this paper actually is to use a combination of a max margin softmax loss and gating to actually take those three features and actually move them into a common shared embedding space. And the cool thing you can do now is you can actually train on one large scale data set, like how to 100 million, and then just test on whatever you want for downstream data. Places, audio captions, UCook, MSRVTT, crosstask, and so on. And technically it's up to you if you want to do fine tuning or not. And then when you're actually done with all that, you can play some pretty cool games. So first you can do retrieval across any modality you want. So you can start with audio and retrieve videos. You can actually, you also do audio image retrieval. You can do, and this is the most standard part, text video retrieval, and so on, so on, so on. So actually, once you get this embedding space, you actually got a lot of cool things that you can start working on, that you can start playing with. And technically, we found out that it makes a big difference if sound is there, or let's say if speech is there, or if sound is there. So this is one of the things that I will talk later a bit, that technically we have to have an eye on where the text comes from and how the sound is made up. Another paper that was actually, or that is actually presented right now at this year's ICCV, builds up on this idea and is called multimodal clustering networks. And here the idea is similar as with AVLNet, that we want to learn this common joint multimodal feature space. But now actually we do actually throw things together. And the two things that we want to throw together is clustering and contrastive learning. And the reason why this is important is because contrastive learning, as you kind of like saw and hopefully got an intuition, will always try to get pairs from the same source together, which means, let's say someone marinating a chicken, like the visual representation and the text will kind of like always be drawn near together. But what it does not care about is how those, for example, visual instances rely to each other. So as long as the marinating chicken vision representation is close to the marinating chicken text representation, everything's fine. But when you now think about something else, like for example, cutting chicken, or frying chicken and so on, those can be spread all across your space. And therefore, we thought it might be a good idea to not only do the contrastive part, but also include the clustering as a second loss in this whole thing, mainly to make sure that stuff that's kind of like, for example, visually similar, also gets mapped into one corner together with the textual representations, whereas sometimes we have stuff where the text is very similar, but the visual is very different, and where we want to get this clustered together. So we kind of like want, again, to start to organize our semantic space a bit more consistently. And this is the resulting network architecture we proposed. So you see it kind of like has this contrastive loss, and it has a clustering loss, and then some reconstruction, because this helps to stabilize training. And technically, that's pretty cool. But now to the things that you can actually do with it. And this is kind of like even cooler. First, you can obviously play all the retrieval games that you saw before. So you can take a text, map it to your common space, look for the nearest videos and just get them. And then you can solve retrieval. But what you can now also do, and this is kind of like where we get back to the temporal segmentation part, you can also do zero-shot action localization. And the way we do it here is because action localization, let's say temporal segmentation comes without any labels. That would be too hard. Action localization usually means that you want to do alignment, so that you are actually given the actions as they appear in the video, and you have to find the right boundaries. And technically with this task, what you can do is you can take all the labels that you have in a video, or for example, you can take all the captions that you have from a certain video, and then you can actually start to look for the textual representation. So you can take the textual representation, map it to your video, and then search for all the frames that are kind of like nearby and assign this label to it with a certain extent, and do this kind of like for all your stuff. And this is how you can even segment videos and localize actions. And in this case, you do it in an unsupervised way and without any labels. And technically, you can still map it to the labels without any Hungarian matching or anything, because you already know the semantic label to begin with. So that's kind of pretty cool. And because there will be definitely questions, okay, what about transformers? What about self-attention? We also played a bit around with how to include self-attention in this whole pipeline. And technically this paper is under review, so I'm not going to talk too much about it, but just to give you an idea how this works when you include self-attention into the pipeline. We ran one experiment where we had kind of like the vanilla version of the system going, and technically it gives decent numbers. And now when self-attention comes in, actually what's going to happen is numbers drop a bit on UCook2, and they will actually increase a bit on MSR-VTT. And I will tell you later why this happens, but for now you can assume that they both kind of like perform equally well. So it's not that self-attention is going to give you a boost of whatever 5–10% right out of the box in this whole game. And then we actually propose to use self-attention for routing, and this is kind of like getting a bit better overall. But anyway, that's upcoming work. So to kind of like move a bit closer to the end and to ask some questions, it's a nice way to actually understand videos by learning those embedding spaces. But technically it comes with some problem, because we know from image text matching that you can do the same job by just predicting distances with, for example, a fully connected layer. And one of the questions is obviously joint embedding space is good because it's efficient, but technically, is it also limiting? So can we do better when we ignore that, when we move away from the simple embedding and learn some higher level function about it? Another open question that we have is actually this retrieval that we at the moment use to evaluate our systems. Is this really a good metric? And obviously the answer is no, or perhaps a maybe, but whatever metric you see, please take it with a grain of salt, because what actually is going to happen when we measure retrieval is that we mine a lot of random clips that come with a certain text. And among those clips, there can be a lot of matching instances, and which one will be selected first is completely random. And therefore, retrieval at 1 is actually a very weird metric in this case. Retrieval at 5 or retrieval at 10 are probably the more stable metrics here. And if you actually want to learn more about that, there's a great paper from Dima Daman's group on semantic similarity in video retrieval at CVPR. Okay, some other open questions that we have to deal with at the moment is actually the data set domain gaps that are hidden and that also have some quirky side effects, because you remember how to 100 million actually comes from YouTube, is instructional, and technically it's natural language. So it's just the ASR that we have. It's noisy. People sometimes don't finish their sentences, and it's structured by time. So it starts at a random point in time and it ends at a random point in time. But technically the audio and text are highly related because the text is just transcribed audio speech. Now UCook2, which we use to test on, actually also has instructions from YouTube, which is good, mainly cooking. So the domain gap in terms of content is very small. But the problem is here, the text that we actually use to retrieve the videos is independent from the audio feed within the video. But the good thing is the text is kind of like describing what the people are doing. So it's semi-related to the spoken text in the video. And then finally, we have MSR-VTT, which is also video from YouTube, but not limited to the instructional domain. So the topic gap is larger. And here, again, the text is mainly based on captions. So it's a structured sentence and it has zero relation to the audio track at all. And this is exactly the reason why you will sometimes see papers where when numbers get high on UCOOC2, they will actually get lower on MSR VTT. Those are the ones that are trained longer on how to 100 million. And when numbers are higher on MSR VTT, it usually doesn't work so well on UCOOC2. So that's kind of like some of the weird effects that we have at the moment in our papers. Okay, question is it worth all this? And my opinion on that is, yes, it's definitely worth all the hazard to try to work more on this and to get rid of labels, because learning this label-free semantic space not only comes with significant reduction on labeling cost, but it also kind of like avoids a bit the labeling biases or assumptions that we have at the moment and that we artificially impose on our systems and which are not necessarily correlated to real life. And finally, when we can get rid of those labeling assumptions, perhaps we can even get a better action recognition. Okay. And technically, my hope is that when we kind of like follow that, holistic video understanding might at some point turn from that one to that one. And with that, I thank all my students who worked so hard on all those papers and who inspired so many great ideas on this topic. And I thank you for your attention, and I'm open for questions.
Wonderful. Thank you, Hilde. Again, for anyone who joined after we made the initial announcement, we're using the Zoom Q&A interface for questions. So please type any of your questions there. I guess in the meantime, while we wait for questions to come in through there, I'm wondering, Hilde, what is your opinion in terms of, you covered a big space of factors that all impact self-supervised learning with videos kind of at scale. What, in your opinion, are some of the key areas to watch for in terms of the data, the modeling, the objectives that we're looking at? What do you think will in the current set of work that's happening, what do you think will have in some sense the test of time impact for this space?
Well, that's actually a good question. And I have to say, I'm horrible in predicting trends and everything. If I would be good, I would probably have started with Transformers in 2018 or something. So perhaps what I think is, or what's interesting from my perspective, to probably just reframe the question a bit, I guess this multimodal learning, or getting at, let's say, this idea of getting rid of the concept of labels completely to start with is probably one of the most interesting ideas that I hope will have kind of like a trendy curve in this decade. Mainly because one thing that kind of like where action recognition or video understanding people are usually making their life very easy is we take those ideas of having classes from object recognition or image classification and just transfer it to our task. And the question is if this actually really makes sense, because for a mug or something or frog, you can say, okay, that's the frog. That's kind of like the physical boundaries of this object. For action, it's actually much more fluid. And having this concept of, let's say, strict action classes kind of hinders us to actually explore this kind of like more fluid field that we're actually dealing with. And therefore, I hope that probably this could be one of the more interesting aspects in the near future, at least.
Wonderful. I think one other aspect as a sort of student in the field of video understanding, one question I have, especially as it pertains to the general trends of scaling up the models and the data sets and so on, to really get some of the breakthroughs that we've seen, at least in the recent past. What do you think some of the barriers might be, or some of the key challenges that might need to be addressed in that sense, to ensure that both industry and academia can have impactful contributions in the emerging landscape?
Good question. So technically, the area which deals with kind of like temporal learning always has to is always kind of like swamped with data and always needs to process a lot of data. So what kind of like people resorted to get a grasp on everything is mainly to decouple it from the representation learning and not training backbones, but using backbones only as kind of like give us a feature, and then with this kind of like compressed representation, we are doing our thing. And technically, I think that's an interesting way that might also have a bit more long-term perspective than we thought, because most things can be shown with kind of like the small representation. So I actually try to avoid training backbones in general, because honestly, also in terms of carbon emission, I don't think it makes sense to retrain kind of like a deep ResNet just to get 1% more when I can show the same effect with like 1 or 2 layers of doing the right thing. And I hope that this kind of like mindset will probably be a bit more around in the field. So we can actually say, okay, there are people doing representation learning, let them work on their huge GPU clusters, but also give people a chance who are doing something else and who have some other ideas. And this is exactly, I guess, the gap that academia can fill actually very efficiently.
Wonderful. I have some follow-up things, but maybe we can take that discussion offline. We have a question in the chat. Do you represent a video from one modality as a single point in the shared latent space, or do you represent them at the level of clips? And if the latter, how do you temporally align them across modalities?
Actually, the answer is yes and yes. So a video is, let's say, or perhaps no and yes. So each video, each untrimmed video is actually broken down into small chunks. And this breakdown is actually defined by the ASR. So actually, when you kind of like follow YouTube automatically generated captions, you see that they usually have a time span of 5 to 10 seconds. And this is kind of like the initial segmentation that we take for each video. So what we get from ASR. And then each of those 10-second visual representations with like 300 frames are kind of like encoded into one feature representation. So usually we take ImageNet, ResNet for kind of like visual part, and then we have some 3D whatever ResNet, I guess at the moment ResNext, blah, that's trained on video, and then we just concatenate, and each feature then boils down to 4,000 something dimensional vector.
Wonderful. So I guess one other follow-up that I had was with respect to that, somewhat related to the embedding question. We often think of encoding videos into one summary encoding, but there's often a lot of dynamics and other things that we want to capture that maybe span multi-events and so on. Do you have any thoughts on potential modifications to how we think about representation in that context, especially as we increase the horizons and the scales that we want to achieve video understanding in?
Yes, so something that we started to work on, and that looking at also other papers might become a very interesting aspect of this whole representation space learning, is actually when we have a representation space and when we have, let's say, different anchor points in this representation space, can we, for example, model this temporal relation across anchor spaces by putting some kind of graph structure on top? Which is technically not so far away from the things we have done before. It just puts it on another level. And that might also be an interesting thing to think about in the near future, how we can combine those two aspects.
Definitely. Okay, cool. Thank you again, Hilde, for the wonderful talk. And now we'll have our next speaker joining us shortly. Is Efstratios here? I think maybe by a nickname. Let me see.
Hi there, can you hear me?
Yes, we can hear you.
Right.
Fantastic. Would you mind sharing your screen?
Sure. Give me a second.
Sure. And I guess as you're getting set up, I'll do the quick intro. So our next speaker, Efstratios Gavves, is an associate professor at the University of Amsterdam. And we're very excited to have him with us today, speaking on the nuances of learning about time and dynamics. So Efstratios, whenever you're ready, the floor is yours.
Sure, 1 second. I believe you should be able to see my screen now.
Yep, it looks good.
All right. Yes, thank you very much for the honor of inviting me to talk about holistic video understanding. So today I would like to discuss about some actually of the questions that you made, Hilde, about time and dynamics. In particular, interested about the machine learning of time and dynamics. And I would like to give a spin, maybe discuss this in the context of sciences. So as a very brief intro of who I am, for those of you who don't know me, I'm an associate professor at the University of Amsterdam, and I direct the Kuva lab with Qualcomm and the Popper lab with Electa, and we're hiring. So if you are interested, let me know. And I'm teaching deep learning at the master's level. I'm co-founder of Elogon AI, a company to personalize immunotherapy in oncology, and a scholar at the LS Network of Excellence in AI in Europe. My research interests lie within the triangle of temporal learning and dynamics, machine vision for science, and machine learning for oncology. And well, my background, I mean, I did computer vision almost entirely in my PhD, and I work a lot with video. The last, let's say, 5 years. So in the last couple of years, I've also been thinking what is next. And today, I would like to give to talk a bit about the role of time in machine learning and vision, at least as far as I've experienced it. Perhaps pose a central research question that I'm working on, and I believe is important for the next steps forward. What are the key challenges to answer this research question, and perhaps some ways forward, or at least some of my recent works to move further. So more specifically, I will discuss the first steps towards temporal learning and dynamics in tracking geometries, dynamical systems, and local invariants and equivariances, as well as causal structure discovery, which is not on video yet, but it's a very hard problem. And I think video is actually going to make things so much simpler. So I think it's worthwhile going through it quickly. And in the end, I would like to revisit perhaps the definition of what we consider as video as a community, and maybe even expand our reach. So, time, learning, and vision. You know, like you all know what was what happened like 10 years ago in 2012 specifically. It has been the golden age of learning algorithms. Maybe I cannot really see the crowd in front of me, so I cannot really judge the age. When I was doing my PhD, well, my PhD is basically finished by the time that AlexNet came up, in the surface. And back then, we had Pascal VOC, we had the deformable part models for localization, having around 32 mean average precision. Pascal VOC 2007 was the glass ceiling, and it was incredible. Like getting any improvement, any incremental improvement was like really, really hard. Now, during this golden age, we've got magnificent results. We can label every pixel according to the class. We can describe frames or like videos with text. We can process really complex biological data like AlphaFold. And we've got algorithms that can beat the world champion in Go, Lee Sedol, the 18 times world champion that is. Now, what is fascinating in this is that, sorry, what is fascinating in this is that all these algorithms, sorry, all these problems were solved basically by the same algorithm, of course, with small modifications given the problem, but basically deep learning, deep neural networks was the same algorithm that was deployed in all cases. So this makes it even more interesting and fascinating, our urgent paradox. So let's say I've got a video of an apple falling. In my work so far, what I've realized is that recognizing the apple falling, or anyways doing some more intelligent video processing, not without really specifically programming pixels and doing hacks, but using our regular models, it's very hard for the models to tell something about the temporal aspect of what's going on. In fact, in our experiments, whether videos were reversed, shuffled, or normal, there was no difference. The classification was the same. Like computer could predict that this isn't a falling apple. It wouldn't say that this doesn't make sense or anything. So the thing is that right now, at least according to my experience, the state of the art of spatial temporal models ignore time, at least to a large degree. And this doesn't mean that they are not accurate. They're perhaps really accurate, and has been tremendous successes over the years, especially lately. However, it is a question to me whether these algorithms can reason temporally. Temporal reasoning is urgent. It's urgent for forecasting, for instance, when we've got autonomous cars. It is urgent for future planning. So, for instance, when you're when you do medical, you want to give some medical advice, it's very important to understand, for instance, when a particular tumor is likely to be highlighted in a spatial temporal sequence of a CT scan. It is urgent for autonomous driving and anyways for the perception of the world around us. Right now, the most successful systems, also the ones deployed in practice, are usually static in the sense that they might be deployed with videos, but usually what happens is that you either process single frames and then you do some sort of very intelligent averaging, or you basically treat subsequences of videos as bigger images and then you process them and you do the same. But what is missing is more advanced temporal modeling. So the central question, I believe, is what is the role of time in visual recognition? And perhaps that's a very hard question, because arguably time is one of the most, the bigger mysteries also in other sciences like physics. And what I think is, well, not the answer per se, but where we should be moving towards is having models that learn temporality in entangled space-time sequences. So what does this mean? For instance, let's say I've got this video of the car moving. As it moves, let's say I've got a single feature describing what's going on. For instance, the angle of the viewpoint. And then as the car turns, this angle increases. Now, if I were to have the same sequence, but in reverse, like in the middle video, I would like to obtain exactly the same features or very similar features, but now moving towards the reverse direction. And if I were to have the same video sequence, but slower, at a slower pace, I would like again to get similar features, but slower. So I would like to have a model which basically can understand time in its computations. And what do I mean by entangled spatiotemporal data? I think that entangled spatiotemporal data is any data with spatial and temporal support. It can have thousands of dimensions and is confounded in different space and time scales. So for instance, when we're cooking, it's not just this couple of frames that are sufficient to recognize what's happening. No, we have to watch the entire sequence. And I believe, why even have an ending? Like maybe we need streaming videos, or we want just online data streams. So this is the most general case, which I think is what is the interesting way forward. And it can be videos in the wild, or scientific recordings, or long, like for instance, long and complex videos. Like we do have some example of data sets at the moment. Migration particles through time, and so on and so forth. But I will talk a bit about this later. So in an effort to understand why time is actually so hard to model, at least according to my experiences, perhaps we can very quickly revisit the current paradigm. So recognizing bicycles in videos, we've got a couple of frames which we annotate positively or negatively, whether they contain bicycles or not. And we can perhaps do an even better job by saying which pixels contain bicycles and which pixels do not contain bicycles. Then we pass these examples through a neural network that aggregates correlations locally. And afterward, with set operations that are basically orderless, like max or average pooling, we are aggregating information locally. And then we maximize separation. Now, in our case, we've got thousands of frames that are, even for moderate sequences, up to 10 or 30 seconds, they're really like exploding in their numerosity. It's not just single static images we're processing. Most methods rely on very strong supervision. So that's basically, I guess, 95 or 99% of the methods out there that they do that. Most methods are deterministic, and we've got a data model gap with more and more data. So at the moment, at least one secure way to have better numbers is to make sure you can consume more data. So these actually present some challenges, this status quo. So the fact that we've got thousands of frames, even for moderate sequences, means that we've got lots of correlations and lots of dynamics to account for. And we don't have good models in the first place, even for shorter sequences, let alone for so long sequences. So the first challenge is that state-of-the-art discards time by aggregating with set operations. By definition, maximum or averaging will throw away time. Second challenge is that it's hard to annotate manually, which makes supervised learning debatable and sort of forces us to have to work with shorter videos. And as the third challenge, I think we've got data that are really stochastic in their very nature. So whereas images are, you got the static image, nothing changes, like, you're not like going to, you can't really expect that the car, for instance, will change its appearance. However, in the sequence, you don't know whether the car is going to move to the left or to the right. There are a lot of possibilities. So I believe generative modeling is critical at some point. A fourth challenge is lack of standardization in a way. Data is so huge and algorithms so complex such that it's very hard to make apples to apples comparisons. It's just very, very practically very, very hard. And I believe the people working in this domain are, they found like very good, they have very good ideas, very intelligent solutions, so that we can even do some basic comparisons. However, making equal and fair comparisons is hard, which means that improving algorithms at the level not of a system but more fundamentally is by itself quite challenging. So ways forward, what I think is the way forward, and then later on I will move on to some works moving that way. I believe that we have to work with space-time geometry. So basically learning spatiotemporal geometric manifolds. For instance, like, you've got these geodesics on the sphere, which sort of represent the path. It's a latent space, and on it we have the frames, and the paths represent the trajectory of the video, so to speak. And if we could have that, then we could aggregate over geodesic time paths on that manifold, such that we obtain robust and repeatable representations of spatiotemporal sequences. I believe we should go away with manual annotations, which should replace it with space-time supervision using spatiotemporal properties. But for this, in my experience, again, we need to combine them with the right models. They have to be time sensitive. So if you have a model which relies on max pooling or average pooling, this model by definition cannot really understand time that well. So how can it be trained using time as a supervisor signal? So in a way, we have a chicken and egg problem here. Quite a few attempts have been made in this axis, and I believe it's a very exciting direction. It connects to self-supervised but learning. I believe that it has a unique flavor and distinction that we have not really explored that much, in the sense that self-supervised is very general, but space-time has properties that are very unique to the scenario. I believe we have to move to space-time stochastic models, so models that imagine all possible futures, and this includes spatiotemporal generative or Bayesian model, perhaps. And in the end, space-time evaluation. So we have to find a nicer way to standardize data and evaluate on temporal properties. So I'm not saying to stop working on the data we have. In fact, this is the way forward for really getting top accuracies. However, I think we also need some benchmarks to evaluate strictly on temporal properties and be able to compare algorithms equally. So in these directions, some first steps, perhaps some baby steps forward that I have been busy with the last couple of months. We can start with space-time tracking and geometries. As perhaps many of you have heard of geometric deep learning as being the new kid in block, a very impressive new literature. And Michael Bronstein is spearheading the effort. Equivariance, geometric group equivariance is huge. It's a huge chunk, and basically group equivariance wants to transfer properties like what convolution makes for translation to other types of symmetry. So for instance, if you have rotational symmetry or other types of groups like scales, then you could have much more sample efficient models by taking into account explicitly in the model these symmetries. So in this work, we're focusing on rotation equivariant equivariance, so rotational symmetries, and specifically we use it or we explore it in the context of tracking. So in tracking, like in 2015, me and I and colleagues, we proposed the CMS trackers. We had the first work to propose CMS trackers, and they were extremely robust. They work really well, especially for long-term tracking. But they are not perfect. Certainly, they cannot handle variations that normal convolutions or anyways operations that the normal neural networks would not be equipped to handle. In tracking specifically, quite often we have objects that constantly rotate, and they rotate without changing their identity or their semantics, right? Like when you have this motorbike doing all these flips, it's still a motorbike and we still want to be able to localize it. Or when the bunnies moving, or they're moving around, we have to still localize them. And it's hard for convolutions, especially when you don't have a system that has been trained to recognize explicitly this type of variations. What is equivariance shortly? So roughly, there is an extensive mathematical definition, but the basic intuition is quite simple. So roughly, change in the input should be proportionally transferred in the output of a function. So mathematically, if we have a group G, which contains all the possible instantiations of a symmetry, a function f, for a function f, we should have that when we apply this group on element x of f, it will be equivalent as if we were take to the group element and apply it on the function itself. Groups are mathematical objects that are far broader than rotations or translations. Rotation is a very popular one, especially in computer vision for obvious reasons. Yeah, they very much relate to the study of symmetries. So a simple example here, visual example, regular CNN on the left, and we see that once we start rotating the input image, the feature, I show a detail here in the, let me see if I can annotate here. We see that the feature changes, right? Like, of course, we see a contrast. This doesn't change, but the feature itself changes quite dramatically. And normally, what we expect from convolutional neural networks is to learn a lot of different filters that basically represent the same texture, the same appearances, only after rotation. So in a way, we're wasting convolutional operations to relearn similar things. Rotation equivariant neural networks take this rotational symmetry into account, and by redefining convolutions, they can yield feature maps that are much more robust to such rotational transformations. And to the right, we can see the difference between the two. So to the left, we've got the regular convolutions. To the right, we've got the rotation equivariant convolutions, which are much more stable. So one of the most, there are different ways you can implement rotation equivariance with neural networks. One of the most popular ones is recent work by Weiler and others with circular harmonics, basically saying that a convolution is the result of a magnitude. So basically, this is a scalar times circular harmonics. It's an exponential that is modulated by rotation. And by having many of those, you can sum them up and basically compute the features in under many possible rotations, and in the end obtain the final result. This brings the benefit that you don't need to optimize more filters to implicitly account for rotations. The rotations are already taken into account within the circular harmonics that are part of the convolution. And in our setup, we simply take this concept and introduce it to our CMS trackers. So starting from frame 0 and frame t, so basically that's how CMS trackers work. We first rotate the first frame under 8 possible rotations. So 8 rotations are typically good enough. Then we learn, we compute rotation equivariance convolutions, we obtain the respective feature maps, and we compare it then against our every new frame t. Then we summarize the results and do max pooling to discover what is the most likely next location for the target. As a result, we can improve by at least 10% or even more videos, tracking in videos where the object rotates, and we remain stable when it's not. Of course, we will not improve in cases where the target is not rotating, but it's great that we don't also lose performance. This means that we can be much more reliable in that sense. Right now, it works only for in-plane rotations, but we cannot do out-of-plane rotations. The reason is that mathematically, in-plane rotations are much easier to model using 2D data, like regular RGB images, whereas for out-of-plane, we would normally want 3D information. And considering rotational geometries in videos does make a difference for precision in inference. The second work towards a better understanding of time and dynamics is our recently accepted paper with Miltos Kofinas, Navin Shankar Nakaraja, and myself in Europe's 2021 on roto-translated local coordinate frames for interacting dynamical systems. So the idea here is that when you've got quite often we have dynamical systems, so basically spatial temporal sequences where objects interact with each other, like for instance a traffic scene with multiple bicycles, vehicles, and whatnot. But this can also be more generalized. For instance, the way that the like materials behave over time is also an interacting system, because the molecules interact, or anyways, the small particles interact with each other. So systems of interacting objects typically exhibit highly nonlinear and time-dependent behavior, and anyways, this is the setting we're focusing on. And complexity increases very quickly. So when you go from a system with one object only to two objects, you have to take into account the dynamics between these two objects. And if it's three objects, then this goes exponentially, because you have to take into account all possible interactions. So the idea here is, to give you perhaps a more straightforward example, maybe you have heard of the two-body and three-body problem. So two-body problems in physics is solved. Three-body problems is actually unsolvable, at least analytically, to give you perhaps a more intuitive understanding of the difficulty of the problem. So it's very hard to actually do this analytically. The question is, can we learn such dynamical systems from observations? So basically we have vehicle trajectories or particles colliding or material molecules in the way they're moving, or learning physics. Can we learn how they will interact over time or not? So in this work, we revisit the setting under the lens of Galilean invariance. So basically dynamics, this is very simple, well, simple by today's standards concept, meaning that the dynamics are the same no matter the reference frame, which then also means that the input representation should be invariant to rotation and translation arbitrariness of the reference frame. So for instance, if I'm looking at, if I'm a bicyclist and I'm trying to predict where everyone else is going to move, so that, for instance, to avoid them or to decide where to move next, my predictions of what everyone else will likely do should not depend on my location. It's the same, right? Like another bicycle next to me or across the street should try to or should be able to infer similar dynamics of the future. So this is basically or intuitively what Galilean invariance is, and this means that our interpretation should be invariant to rotation and translation arbitrariness, and out-interpretation should be equivariant. So if I change my viewpoint of the scene of the system, my predictions should change accordingly. I don't have to relearn them. For this, we propose the concept of local coordinate frames, which is extremely simple. So just change the input representation. If we have, if this is normally our system, and then we would normally have one coordinate here, and then one coordinate here for like per object, and then we would concatenate them and pass them to our whatever specialized neural network, like an LSTM or neural relational inference networks and whatever. Instead of doing that, we propose that we should have coordinate systems that are specific to any given object. And this means that we are doing a translation such that the object is in the 0.0 for every different object, like here or like there. And also we rotate the coordinates, the local coordinates of the system, such that the velocity, so the trajectory of my central object is always aligning with the x-axis. So basically, this is just changing the input representation, nothing else. And we can combine it with existing neural dynamic inference models, for instance, the one from KIPF or Grabber. Sorry, yes. And by doing so, we actually have magnificent, really good results. To the left, we see here particles colliding. So these are, for instance, I don't know, like in CERN, in the LHC, Large Hadron Collider experiment, and you want to predict where particles are going to move. And we see that, well, it's not really visible, but there is a light and darker color trajectory. The darker one is the prediction. The other one is the ground truth, and they're highly overlapping. In traffic scenes, so this is a more traditional computer vision task, again, our predictions align very well with ground truth trajectories. And to the right here, we see some curves showing quite a bit lower errors. So basically here as a takeaway, one must take into account the other person's perspective, point of view, to make good future prediction, or at least if you do so, then it's likely that you will improve significantly. It generalizes well to different dynamical systems, so be it traffic scenes, colliding particles, 3D motion captures. And I believe it's an exciting direction for research in machine perception learning. So generally the interaction or the interface between dynamical systems and videos and spatial temporal sequences, I think, is a really interesting really interesting direction that can offer lots of opportunities. Next, I would like to focus on the dynamics of learning. So this is not yet on videos, but I believe it shares lots of commonalities with videos, and I believe it is worth mentioning. So this is work that has been accepted in this year's ICCV, called Sparse Shot Learning with Exclusive Cross Entropy for Extremely Many Localizations. And here, so this work is in the context of computational pathology. So this is basically computer vision on really gigantic images of 100 by 100,000 pixels. And of course, with such images, it's extremely challenging how to annotate. So whereas for MNIST, you could just do it in a couple of seconds, or with MS COCO, maybe in a few minutes, you can annotate quite sufficiently the scene. Imagine if you have a gigantic image of 100, like basically it's one, like each image is 1 gigabyte image. Imagine having to annotate every small cell in it. That would be, yeah, that's impossible. That's really not possible. It's like taking a Google Maps picture and asking to annotate manually every house in it. So millions of objects to annotate, impossible to use ordinary machine learning models out of the box. And of course, there are smart, simpler solutions that you can do. And I believe that this works really well for images, so in settings with similarly huge image inputs like pathology, microscopy, and astronomy. But I believe video is also such a domain in the sense that you've got huge data for which label annotation is also extremely expensive. So what is the basic idea or the basic observation here? We realized that because annotations are extremely sparse, and we're not saying like, sparsity in the sense of like, I missed 1 out of 2 or 5, or 7 out of 10, but you actually have less than 10% of annotations, or even less, even more or less. Because of this sparsity, you've got extreme information loss. And this means that we cannot assume that background is all true negative, right? Normally you would say that, okay, everything is a negative. Whatever is not labeled as positive, it's a negative. And then you would train your classifier, and perhaps you can even do something smarter like weak pseudo annotations. However, just because of the extreme sparsity, weak pseudo annotations are extremely biased. They're going to mostly correspond to wrong annotations, like in the bottom right picture here, which means that if you use them as then pseudo positives, you would really have a model that doesn't work at all. At least we couldn't make it work. We couldn't have it working in our experiments at all. Generally, we observed that once you pass the threshold of 30%, so once you have more than 70% of annotations missing, your classifiers are extremely hard to be trained using the regular cross entropy and whatnot. So our key idea here is that, or our thought experiment, if you may, is that biased gradients push the model towards the suboptimal craters. So in the beginning of the training, especially in the early training, pseudo annotations are untrustworthy. So even if we had all annotations and we would start training the model, you wouldn't trust it in the early rounds, right? Like it's not good enough. Its confidence is unreliable. So why would you do weak annotations in an even harder setting where you have sparsity? So we think that basically the problem is that if you keep taking biased gradients, you end up in the wrong suboptimal crater. Instead, we would like to go as quickly as possible to unbiased craters. And this means that we have to downplay the relevance of biased gradients. And this can be also explained as slowing down the speed of learning from pseudo annotations. We don't want to discard them, because if we discard them, basically we discard the whole data set. Then we have very little data to train on. However, we want to make sure that the gradients obtained by unannotated areas do not contribute to too quick learning. So it's better to trust them a bit later. So by doing that, of course, there's all sorts of hacky ways you can do it. For instance, you can ignore annotations, or you can put a temporal like schedule. But in practice, none of these things work, because it's extremely hard to set correct hyperparameters that make sense for all your data and for all your annotations. Instead, what we proposed is the concept of exclusive cross entropy, which basically ignores the more reliable, the higher confidence predictions from annotated regions. And by doing so, we're able to obtain impressive performance, even with 90% of annotations missing. So if you will see here, we obtain very high results. And by almost 40%, we obtain nearly the same results as if we had the full annotations. and some qualitative results. Here with exclusive cross entropy. So we propose this new loss function, exclusive cross entropy. It worked very well with both YOLO and UNet, so for both detection and segmentation. Almost all boxes were detected with only 30% of annotations, and we could suppress false positives to a high degree. I'm not sure if I have the time for this, so we'll skip it and maybe go to the next subsection before the conclusion. So next, I would like to discuss about what is video, and perhaps whether we could rethink of what the definition of a video is. And yeah, inspiration for it comes from the sciences. So I believe that, or from where I'm standing, video is basically signals that have a spatial and a temporal component. So for instance, the majority of scientific recordings are videos, in my opinion, and we should treat them like that. Like in climate science, we got recordings of glaciers melting, or in biomedical domain, you've got basically, well, it's only about videos. It's like how these different cells interact and move. In physics, the same, or in ecology. In ecology, you got like migration patterns, and in astronomy, you want to discover exoplanets by taking measurements over time, or in particle physics, the same. My point is that video is not just recordings that we do with our phones. There is so much more spatiotemporal data with really endless and opportunities and exciting problems. There are really very interesting problems to work with, and I don't see any reason. I mean, I would love to hear counter opinions, but I cannot see any reason. Like, I cannot think of any reasons why our models, why our I3Ds and our trackers and our deep networks should not work with such spatiotemporal signals. If a deep neural network, which works very well, for instance, for understanding cooking pasta, should, in its basic form, work pretty well for similar spatiotemporal sequences. So I think that this also offers another interesting opportunity that relates to the evaluation I was talking before. So currently we evaluate models on larger and harder to process data sets, and this is very expensive for video and deceptive due to annotator bias. So how can we even generalize to more complex setups? So by expanding our definition of the video, perhaps we can use even scientific knowledge as our perfect ground truth, right? Like if my goal is, for instance, to predict future trajectories, then I know how the future trajectory of a particular particle will be, or a particular planet will be, and then this is actually a nice way to test the validity of my model. So there's more research from my team on the interface of machine learning and computer vision. So categorical normalized throws, Hermite variational autoencoders, implicit functions. So in graphics and machine learning, and in causality, as well as in the medical domain. So if you're interested in these concepts in machine learning and spatiotemporal learning, in system dynamics, machine vision for sciences, I would be happy if I receive, if I get contacted. I'm more than happy to synergize and collaborate. I have a postdoc vacancies on the fields above. So yeah, just drop me a line. So to conclude and be in time, I believe that we're at an exciting time. I believe that video is one of the most important and relevant for the future of computer vision directions. I think we've got very important fundamental and philosophical even problems and challenges ahead of us. I think interplay with geometry, dynamical systems is the way forward. I believe we have to shift our paradigm, because everybody's talking about static data, and most of the times I believe we have to move to temporal. So to a temporal perspective of our our data, right? Like things are temporal. They're not like, and they're non-stationary. They're dynamical. By making them static, it's only for convenience. It's not the reality, and it's an exciting time for computer vision, machine learning, and AI. Yeah, and with this, I would like to conclude. Thank you very much.
Wonderful, thank you. So a reminder again for the audience, if you have any questions, please feel free to write them in the Zoom Q&A, and we'll get to them accordingly. I had I guess a question for you with respect to the broader theme of learning invariances in videos. Your work covers such a big spectrum of domains and applications where the semantics of what we care about in terms of what we are, things that axes that we want to be sensitive to and axes that we want to be invariant to kind of change across these. Do you have any insights or intuition as to techniques that might be conditional on intent or more situational, but that can still be used to help learn sort of more broadly applicable models that can be applied to this range of fields?
So I'm not sure I understand completely. So you're asking if we can specialize the models or if we can generalize the models?
Yeah. Okay. Basically, we have a number of specializations for it,
Right.
but you can also imagine that even within specializations, you have different contexts. Like, for example, earlier in your talk, you had an example of you want rotational invariance for the semantics. The rotation doesn't change the semantics of the object that you're trying to recognize, but it does change the semantics of the action that is being performed by the motorcyclist.
Definitely.
So, you know, yeah, what are maybe some of your thoughts for? I think one of the big trends that is emerging in self-supervision is leveraging invariances in video
exactly
to help provide supervision. But in doing so, we often lose other information that we may also want, you know, ostensibly from video.
Right. So look, like I don't know, I did a few works in between 2015 and 17, 18. I was working a lot with video. I was trying to think, I don't know, like crazy ideas, see if they work. And we did some self-supervised back then. It was not really popular yet. What I realized and I found extremely thought-provoking was that, and not just from my work, but like reading, for instance, this is my papers on the time of arrow, is that you cannot have a model learn from temporal self-supervision, for instance, when the model itself is not temporally sensitive. So when we're trying to have like a standard convolutional neural network or a standard STM, I mean, these models get confused when you start playing with time. And once we had the better model to handle with the temporal changes, so with the times arrow, then it suddenly started working so much better. So more specifically to your question, indeed, per setting you might care for you know, different, like or your for per setting your focus is different. So you know, in tracking rotation is you should not care about it. Just make sure that you can you know, detect it. In action, it is core in the semantics. In either case, you want a model that is actually able to understand about these you know, basic transformations and these basic patterns, spatiotemporal patterns. Otherwise, you cannot account them for. Of course, you can also say that I try to be invariant to all these. So I don't really care to know about rotations and whatnot. But I believe that for the next generation of very precise predictions, we do need models that do not you know, just throw away all this information, but take into account and incorporate it. So incorporating inductive biases like that, I think, is really the next big thing. from machine learning, and I believe it will come to in computer vision as well. The problem with, well, not the problem, the specialty of computer vision is that the data is so much bigger and so much more complex. It's just so much harder to prove that, you know, you might have a really good method, but it's very hard to prove it's a good method. But I think, you know, like we can make small steps forward. Yeah, maybe with the evaluation that I propose is one such step.
Wonderful. I guess maybe a related question to that too is, there's such a broad space of application domains that you look at, all very impactful: physics, medicine, and so on. Maybe for our audience and for myself, to better appreciate sort of the diversity of the challenges that emerge in terms of data and you know, modeling and such. What are some observations that you've had as you've worked in all of these different spaces, and how might those relate back to computer vision?
I think that an interesting observation is that it's not like that different, because at the end of the day now we all use neural networks, and I mean my background, I also do basically computer vision most of the time, but I decided to spice it up a bit. It's not like that impossible, so it's really a matter of liking at the end of the day. Yeah, particles, I don't know, like they're just like you know, dots through time, x, y, z, comma, t. Yeah, if you go to social LSTMs for trajectory prediction in traffic scenes, that's basically the same type of data you have. If anything, it's much more regular because there are underlying laws of physics. Basically, there is no free will, whereas in computer vision, you have to also account for the free will of people, right? Like for behavioral factors. I think it's really exciting, and I mean, personally, I will push for it. I think what we really miss is systematic, like benchmarks for systematic evaluations, and maybe making it standardized, right? Like if you had a way to, you know, if you have an image net or a kinetics data set for some of these settings and data, it will be very easy for you to run your standard model and see how it works. I find this really exciting. And I believe that computer vision researchers are perhaps the right type of people to address all these challenges. What other observation? I think that yeah, so I will close that. I think it's much more common than one would expect. Let me leave this at that. Yeah.
Interesting. I don't think I would have expected it to be quite as common as
well, certainly we're not doing physics as in you know, the type of experiments that they do in CERN,
right.
But at the level of our abstraction, it's not too far.
Right. Interesting. So I guess maybe the specializations then come in your choice of inductive biases that you integrate into models, but the architectures and some of the general techniques kind of generalized to all the fields that you're looking at.
At least so far. Yes.
I think it'll be interesting to see how that continues to evolve. We have a question from the audience. What if spatiotemporal monitoring cannot handle one or more frames? How does it affect time-sensitive models? I'm not quite sure I'm interpreting the question correctly. So if the person who asked the question can give a follow-up also, or Efstratios, if you have an interpretation.
I'm not sure what it means by monitoring, maybe modeling.
Yeah, I'm guessing monitoring was modeling. And but in that case, I'm not quite sure also what right. Maybe the general context is.
So I will interpret it freely, as we do also with reviews that we
right
when we don't do something. Actually, that's one of the biggest problems. Like, and to me, it's also a big question whether transformers will survive at the end of the day, because, you know, can they handle more frames? What's the limit? LSTMs are known to be very similar to chaotic systems, basically, because when you change a bit the initialization, their predictions can vary really tremendously. And this was only with very simple language data. When you've got space and time, and then you've got features, you don't really have one-hot encodings anymore, but you've got learned features, and then through time, over thousands of, or even hundreds, or even dozens of frames, I believe this is extremely complex. I think that's the next, yeah, it's, yeah, what if? There is no real answer at the moment. I think what's happening is that we still perform, we optimize data sets, we don't optimize models quite often. So we discover solutions that work pretty well for short clips or for specific types of actions, for instance. Yeah, if it generalizes to longer sequences, like I think the long actions and long videos is the next big thing, or at least one of the next big questions. I don't think there is an answer yet, at least to my. I believe that, again, geometry, and this is what I'm encouraging my students to work on. I believe geometry, again, is going to be quite crucial here, in the sense mostly of graphs. So I believe graph neural networks, where different nodes are, for instance, different concepts, and then edges are connecting concepts over time, I think, and then maybe actions are basically random walks on these graphs. I think that's actually a very interesting direction, because this offers sublinear complexity. Your graph remains the same no matter how long your video is. You just need to, walk on it. But yeah, I don't have a. We had a paper with Nuruddin Hossein, which showed promising results, but I haven't explored this direction further.
I think that was a wonderful interpretation, and especially relevant as we've seen the introduction of larger scale transformer models in both 2D settings, but also now increasingly in video settings as well. One other follow up to earlier in your talk, you spoke about interest in causality, in modeling more causal relationships.
Yes.
And there's, in some sense, there's different time resolutions for causality. We can think of causality in terms of the local physics, like one ball hitting another, or counterfactuals of this ball colliding with another ball and removing that ball from the path of another ball. And so,
yes.
That order. But that's at sort of one time scale, one sense of locality. There's also a broader notion of causality between events and social situations and motivations of people. I think Hilde actually had some points on this as well. So I guess, what are your thoughts in terms of the methods that you've been looking at? What are some maybe the assumptions that would maybe need to be re-examined in the context of some of these other timescales?
Right. So I think that's a fascinating, a very good question and fascinating direction. I'm working with Philip Lippe and Taco Kuehne on causality, and we're in fact working on exactly this problem. Well, it's for object-centric representations. Where you want your features to be specialized to particular, to specific objects in the scene, in the context, without, of course, having explicit supervision for that. So I don't want to know it's a bicycle or it's a car. I just want to learn that it's an object based on causal interactions that take place in the scene. One of the biggest problems is, at least so far, has been credit assignment. So basically, how do you make sure that through time your credit does not over dilute with respect to the crucial interventions that took place in your causal setting? There are some interesting works in that direction. I was pointed out recently to the hindsight credit assignment. from the reinforcement learning to literature. Again, it's a big problem. It's a big and open problem. That's why I'm saying, like, this area, if you like, for whoever decides to go this direction, I think it offers like ample opportunities for innovation, and it's definitely not easy, but yeah, it's there. It's waiting for us to address it, to go about it.
Wonderful. I think it's a very hopeful, optimistic note to kind of end things on.
The problem with well, it depends on, there are various ways you can interpret causality, and I dare say there is no one correct way, right? Like at the end of the day, it's in the eye of the beholder. Now, under the guise of, you know, causality being a system where you can intervene, and then basically you're doing experiments, trial and error. What is really hard is, of course, that you know, what kind of data will you have? If you have, again, sort of static data, you stored your data in your hard disk, and then you learn from them. There is no notion of intervention, right? Like otherwise there are exponential amounts of futures. Then you have to go to simulators, but then simulators are not realistic enough. So you've got a lot of practical problems. But it's interesting because while you've got these practical problems, you also have theoretical problems. So like these theoretical problems are solved. So perhaps it makes sense to, you know, put the practical problems aside. You know, you can have practical solutions for them and then focus on the theoretical part. And for instance, try to go about your your very question. You know, how do you address the multiple time scales? I think that's actually one of the biggest problems in all spatial temporal learning. And it's also a very deep question. Like basically scales is one of the most important notions in, you know, in physics, for instance, or in mathematics and dynamical systems, how things interact in different scales. In our field, usually we treat it more practically, like, okay, I'm going to put more convolutional sizes and that's it, and then I'm just going to do an averaging. But this goes only so far. If you really want to do the extra mile, you really have to understand what scale is. And I'm not saying that I understand or I have a solution. I'm just saying what I've learned so far.
Yeah, I think that's a really excellent point, especially in the context of when you're moving to like larger scale events. You know, time gets very relative.
Exactly.
Then, and so some of our standard techniques for window, you know, processing of multi-scale things don't quite generalize to that setting, at least not
exactly
intuitively. Wonderful.
I completely agree. Yes.
Wonderful. So I think we actually do have a little bit more time for the next talk before we can start the next talk. So if there's any final questions from the audience, they can feel free to ask. Also, Hilde, I don't know if you're still here, but would love to hear your thoughts on some of these questions as well, if you wanted to jump in. In the meantime, I will, a brief aside, one of the other questions that we got was a bit more of a practical question, which was how do I process feature length videos using an I3D model if you have limited compute resources constraints? Generally, the technique is you stream the video in a sense where you're only processing a few frames at a time and you're extracting your features, and you leave the feature, you save the features and go from there.
So that's interesting, right? You have to cut them and you have to process them, and of course it makes a lot of sense, but you know, it wouldn't be nice to actually not have to do that.
Yes, and I should also add, this is still in that paradigm that Hilde was mentioning in her last talk, which is where oftentimes in academia we operate as downstream consumers of representations that have been kind of determined and trained a priori. But if we are trying to do some of the things which you're showing in your work here, where the representations themselves need to get need to have certain invariances and so on, be robust in certain systematic directions, then it can prove a bit more challenging then your model scale becomes a lot more relevant.
Yes, exactly.
That setting. Wonderful. Okay, so I think we're going to go ahead with the next talk now. If anyone has any further questions for Stratis, feel free to, I guess, drop a note. And but otherwise, thank you so much for the wonderful talk.
Yeah, I'll stick around, and thank you very much again for the opportunity. And if anyone is interested in a postdoc vacancy, drop me a line. Thank you very much.
Thank you. Okay, and so our next speaker is was actually unable to make it in person. It's Kees Snoek from the University of Amsterdam. Kees is a professor at the university. He pre-recorded his main talk and will be playing that today during the main part of the session. And then for any questions that are directed at him specifically, you can reach out to him directly. Stratis and Hilde, if you're available to stick around at the end, would be interested to hear some of your thoughts and discussion, maybe as in sort of in lieu of Kees being here live, we can have some discussions.
Sure, we'll do
in that way.
No problem.
Hello, my name is Kees Snoek. I'm from the University of Amsterdam, and I'm happy to fill another slot in this second tutorial on large-scale holistic video understanding. And as my title today, I have chosen Return of the Tubelets. And that will become clear in a bit. So the overarching question I would like to put on the table for this tutorial is that, is video more than the sum of its individual images? And I would like to start with this video by famous Russian and Soviet filmmaker Lev Kuleshov, who is well known for the Kuleshov effect. And let me demonstrate this by showing the video. So by showing the same face of the same actor after a different initial shot, Kuleshov showed that he could arouse feelings of hunger, grief, or desire, depending on how the shots were edited. So by doing so, he demonstrated the power of montage as well as how meaning derived from video is more than just the sum of its parts. And I think this is an inspiring example why video is a different medium than just a static image. So taking a jump and showing another video, typical of work done in our community. So this is eventually what one wants to recognize in video material. So what are the activities going on? Who are the people? What are they doing? Where are they going? And why are they doing the things they want to do? So much of the work done in the vision community and also this week at ICCV will focus on techniques and algorithms to infer meaning from video. So one such approach is tubelets. And let me start with giving an overview of tubelets. So I think one of the first or early works presenting tubelets was from CFPR 2014 with Mihir Jain. And basically tubelets are unsupervised activity proposals. So on the left, you see ground truth video, trimmed video, where we are looking for a soccer activity. And what Mihir showed is that when you perform a supervoxel segmentation of such a video and then start to group these supervoxels based on criteria like color, texture, shape, and motion, one could come up with all kinds of proposals that are resulting from merging several supervoxels that are guaranteed to capture the activity of interest. So one has essentially then reduced a video of supervoxels to a video of activity proposals. Now, what was the beauty of this tublet algorithm? These activity proposals are obtained in an unsupervised fashion, and they analyze space and time jointly to obtain these so-called activity proposals. They are agnostic for the action class, and they can cover variable aspect ratios and temporal length. So depending on what is depicted in the content, these tubelets will adapt to the content. They rely on supervoxels, then popular in 2014. I don't think anybody uses them till today, but they were fit for the purpose at the time. And they showed that we could get a high recall with only a few proposals. There are also alternatives. This is work by Jan van Gemert, and he showed that you could do the same thing, but then with dense trajectories. So rather than relying on supervoxels, he relied on dense trajectories, performed some clustering on the dense trajectories, and then grouped these clusters in a hierarchical fashion. And the big advantage of these dense trajectories over the supervoxels is that then often the same representation was used for creating the proposals and also for the downstream task. It was typically action detection at the time. Now, what can you do with these proposals? So let's say you have a supervised action classifier. You let it classify all the proposals that you infer from a test video, and then you can predict the most likely activity for this tublet, and you automatically get his spatiotemporal extent with it as well. There is still a downside that at training time you need to provide class information as well as bounding box information for every frame that comes in your training data. So while tubelets are nice at inference time, at training time you still depend on a lot of annotations. But also here tubelets proved effective. So this is an idea by Pascal Mettes, where he said, well, you know, we don't need to train on these bounding boxes as specified at training time per se. We might as well train on activity proposals, as long as we are able to find a good fitted activity proposal at training time. So what he showed was, well, he took an off-the-shelf tublet generation method. So you have a bunch of those activity proposals at training time. And rather than labeling boxes, he suggested to rely on point annotation. So a human assessor labeled a single point at the center of an activity to label the activity of interest. And then he showed that with a simple algorithm based on multiple instance learning, he could mine the best proposal given the provided point annotations. And this reduced annotation time compared to box annotation considerably, especially as there's no need to label every individual frame. You could easily skip multiple frames and still get a reliable proposal out of it. In follow-up work, he even showed that you don't need a human labeler to provide these points. You can also rely on so-called pseudo points. And pseudo points can be obtained from automated detectors. For example, a person detector, motion analysis, or object proposals, and even the activity proposals themselves would be valuable cues to determine points automatically. We also considered zero-shot localization based on tubelets. So here the procedure is as follows. You generate several action tube proposals per video. Each of those tubes is then encoded with 15,000 object classes as predicted by a standard deep net. At the time, this was still an AlexNet. You perform a zero-shot prediction for all the tubes in the video, and one simply selects the best one as the most fitted one. And how does this work? Because every tube is encoded by means of 15,000 semantic object labels, one can find object and action affinities using a word-to-vec representation. And then based on an action query, you can find the most likely objects that co-occur with this activity in text corpora, and then simply look for the tube in the video that maximizes this affinity also in the visual representation. And that's how you could perform zero-shot recognition on video using tubelets. Here you see some results from this approach. So in green, the predicted results by our zero-shot approach, and in yellow, the ground truth. So for this diving video, it works quite well. And also for this skateboarding activity, the zero-shot prediction fits the ground truth box quite good. Here's a failure case for a person playing golf. So here the zero-shot predicted tublet focuses on the golf tie rather than also including the person performing the activity. So that was initial success of tubelets, mostly based on old school representations. So much of it relied on super voxels, dense trajectories, and not really integrated with the power of deep learning that came around at the same time. So it was not surprising that there was a strike back by the spatial detector. And one excellent example of such a work is the finding action tubes that appeared at CFPR 2015 by Georgia and Jitendra. And what they showed is that when you perform detection per video frame, for example, using an actor detector, you can get very reliable boxes, and you can do so based on both the RGB and the optical flow representation. And then to get a decision at video level, one simply links the individual detections by dynamic programming approach based on the Viterbi algorithm. And this proved very effective. And here is another example, essentially same approach, but with a lot more muscle. So this is the result of the slow-fast network on the AVA collection. And essentially what they did was, the slow-fast is originally designed for action classification, so a very strong representation for video recognition. And they demonstrated localization by applying the same approach on an actor detector, so a person detector, based on faster RCNN, and then running the same representation and action classification on the box information. So this worked really well. An alternative approach was based on recurrent networks, for example, the video LSTM. So in this work, we show that one can enable action localization from solving an action classification task only. So here the idea was to exploit the attention map that is generated by an attention LSTM, and to use this attention map for action localization. So there were a few more items of interest here. We used optical flow to generate the attention map, the idea being that what moves in the video is probably what needs to be localized. And also we made the attention LSTM suitable for convolutional feature maps. And then what this algorithm did, per frame, it generated an attention map. And we performed some simple temporal smoothing by linear regression to get a tube out of this at the video level. So it would be optimized for an action class, an action activity like a long jump, and it would automatically find the best fitted tube given the produced attention maps during the optimization. And we could rely on temporal smoothing by linear regression here because we assumed there would be only one proposal per video. We never extended this to multiple activities happening simultaneously. Another approach is work by Victor Escorcia and colleagues, and what they showed is that they also used an actor detector, so a 2D detector to find an actor, and to be able to deal with the random deformations that may appear in a video. They did not rely on only the detector, but also combined it with the Siamese instant search algorithm that could simply track the patches belonging to the actor throughout the video, even when there were severe deformations happening. Based on 2D spatial detectors, one can perform zero-shot activity recognition too. So this is again work from Pascal Mettes from Amsterdam, where he showed that based on detected actors, cocoa objects, and spatial relationships between actors and objects as they appear in large-scale image collections, he could infer localized actions based on these image detector results only. And by using a box representation based on object semantics, akin to the objects to action work presented earlier, he could also do the zero-shot action detection. So given an action like horse riding as input, he could infer the correct box localized in the video, and by simply relying on linking using dynamic programming, as presented before, he could create a tube as well. And with this approach, what is interesting, it could also enable spatio-temporal video search. So let's say you're looking for somebody who wears a backpack. Then with this algorithm, you could not only find the actor of interest, but also the actor when he or she is wearing a backpack. Because the location of the object was there, we could also infer size specifiers. So you can find a sports ball of relative size that appears left of an actor. So new form of activity search without the need for any video examples. Okay, so this showed that thanks to the benefits of and progress of deep learning, the tubelets were essentially overpowered by spatial-based methods. But there is recently there has been a revival, and that's why I would like to discuss the return of the tubelets. So many people kept on working on tubelets. Here is some sample from the literature. So we have work on tube convolutional neural networks that uses 3D convnets together to in the context of tubelets. Also from the same conference, Vicky Kalogaiton, as part of her PhD, proposed action tublet detector to really take temporal extent into account in addition to just 2D representations. Gurpreet Singh and co-authors show that you can also predict action tubes also if you have not seen the entire video. So based on a short sample of video, he could predict the remainder of the tublet. And in CFPR 2019, we show together with Yao Zhao how you can also leverage both optical flow and RGB easily in a tublet-based representation. But here I would like to discuss some more recent work. And the first is a tublet transformer. And this is joint work with folks at Amazon, where JJ did her internship last summer. This paper appears on Archive. And this is called Tuber. So Tuber is a tube transformer for action detection. And it builds on I3D backbone, comes with its transformer, and then predicts the boxes belonging to several actor instances. And what is special here, it allows each 2D plus T position to attend to all other 2D plus T positions in a video clip, which is essential for modeling action relationships. So it is aware of not only its own tube, but also other tubes active in the video. So the motivation here is that the self-attention mechanism of transformers facilitates the exchange of boxes between frames, which helps us to form more reliable action tuplets. So what is the main contribution of this work? So this shows the big picture, and essentially the work makes 3 contributions. It is based on a transformer like Detter, but we make it specific for video. And the 3 technical contributions are the tuplet query, the tuplet attention layer, and also the short band multi-head attention layer, that are all optimized for transformers in video. So I will go over those one by one briefly. So the first is the tuplet query. So each tuplet query consists of T box queries, and these box queries share the identity feature C'S for the visual similarity and have independent features C'T to capture changes over time. And this, especially this identity feature, is of importance because without it, a tuplet is not automatically formed. And this identity feature, for example, helps to capture the appearance of an actor as he or she moves throughout the video. Then the next one is our tuplet attention layer. And what is special about this layer is that it performs attention first within a tuplet and then between a tuplet. So here we are really reasoning inside a video on the tuplet level. And what is also nice here is that traditional self-attention has a quadratic time complexity depending on the input size. And by using this tuplet attention, we can reduce the computations while maintaining recognition accuracy. So it is not only makes more sense, but also results in less computing. And then as a third contribution for Tuber, it uses a short band multi-head attention. And this is advantageous compared to more traditional long band attention, because a long band decodes box queries inside a tuplet from all video features, while the short band allows us to decode box queries that are only from relevant frame features. So when you have a scene cut, for example, common in AVA, the short band can still effectively recognize the tuplet because it can learn to ignore the information in the frame from the different shot. And in the paper, we show that Tuber works for both AVA and UCF. So AVA is optimized for frame-based recognition. So you could argue AVA is especially very good for traditional 2D spatial-based methods, while UCF is more suited for spatio-temporal. And Tuber is agnostic to the underlying dataset and performs well for both. Then the next work I would like to highlight is about tuplet similarity in a few shot setting. And this is work performed by Pengwang Yang and Pascal Mettes and was published in CVPR last summer. And here we got inspired by traditional few shot classification, where one learns from a few examples, labeled examples, how to recognize an unseen class. And this was extended by Tao Hu to also take few shot detection into account. So here, the goal is to identify the object in an unseen query image, but we do provide a bunch of support images where we provide the label and the box annotation. So the goal would then here be to recognize that the dog over here, which is also labeled in the box support image over here, is automatically found at query time. And then Tao Hu introduced a new paradigm, which he referred to as few-shot common object localization, where the goal is to localize the common object in the query image without any label and box annotation in the support images. So we have the same support images as before, but now we don't have their label, and we also don't have any box annotation, and we are still able to localize the object of interest in the query image. And how does that work technically? Well, he proposed to use modules related to spatial similarity to find what is similar among all these images, and also to learn to reweight different features from different images, as some support images might be more indicative than others. Now, we thought this was an interesting idea, and we extended this to few-shot common action detection in time and space. And the idea here is that given a few trimmed support videos without knowing their label, all we know is that they depict the same activity. Our goal is to identify in an untrimmed, so untrimmed query video, identify not only the start and the end of the action of interest, but also its spatial extent, or in other words, to find its tublet. So it does not need any action class labels or any temporal and or spatial annotations at training time. And we do so again with a few shot with the transformer. So let's have a look on what that looks like. So here we have a set of 5 support videos and 1 query video. And I will show some results based on 1-shot prediction and 5-shot prediction. So without having any knowledge of what the activity is here, all we know is that they share a commonality. The algorithm is able to predict with varying accuracy the spatio-temporal extent of the activity of interest. So how do we go about in getting there? So we are again inspired by transformers from object detection. So this is the well-known Detter architecture. And the benefit of transformers is that it avoids any needle in the haystack problems that come from proposals. And it provides also powerful relational modeling capability. So our method is also based on an encoder-decoder transformer. And let me highlight you what is different. So to accurately localize the tuplets in the query video, long-term spatio-temporal information needs to be modeled. And what is special about our tactic is this common attention block that is in the legend over here, and that comes back at several places in our architecture. So we just process all the support and query videos with an i3D backbone, extract features, and send the untrimmed query clip into our common attention block. Then in the encoder size, we need to supplement the encoding with fixed spatio-temporal positional encodings, because the encoder is permutation invariant. And we add those positional encodings to both the support video and the query clip features. And for the support branch, we let the support videos go through the encoder one by one, and we simply concatenate the output at the end. In the standard decoder, there are 2 inputs, but in our few-shot transformer decoder, there are 3 inputs. So we have the input from the support branch over here, as well as the query branch over here. In addition, we also have the input embeddings, which are the learned positional encodings. Then at prediction time, we send the output from the decoder through a feed-forward network, and which is a simple 3-layer perceptron that is performed to the output embedding of the few-shot transformer, together with the ReLU activation and linear set-based projection layer. Given the clip level common localization results, we again link them over time to attain the final action tubes for the whole untrimmed query video. And that is how we get a tubelet out of these, a similarity tubelet out of these support and query video. Now, this is a new task, so we needed a new evaluation setup, and we repurposed the AVA and UCF datasets for this purpose, as they provide bounding box annotations, and they have slightly different characteristics. So AVA has or at least the partition that we use has a smaller number of instances, shorter length, but much more training videos, and also much more classes. Now, we performed several ablations on this common AVA dataset to show the benefits of our transformer architecture, the influence of using an encoder for both the support, the query, as well as decoder. And what this shows is that the few-shot transformer performs best when the encoder processes both the support and the query videos. And of course, also the decoder is beneficial. So if we include all the encoders and decoders, we get best results. We also ablated the benefit of the positional encoding, and including it in both support and query leads again to the best results in our setting. So the positional encoding is important. We also ablated the effect of having different type of support videos. So considering both the length as well as the number of videos there. And we also considered what is the influence of noise. So let's say you have 5 support videos and 4 all have the common activity class of a long jump, but the 5th one is another activity. How does that influence results? So first we looked in this plot, what is the influence of the length of the support videos in number of frames versus the number of videos that are available in the support set. And what this shows is not so surprising is that we obtain a more precise common localization with more and longer support videos. But also, even if the support videos are relatively short, with only like 15 frames, and if we have 3 of them, for example, over here, we already can get quite good common localization accuracy. Then this table shows the effect of having noise in your support examples. So when we have no noise, sort of like the baseline, we get a frame level MAP of 28.1. And if we replace one of the 5 support videos with one noisy support video of another class, results drop, but not so much. And it doesn't matter much whether the noisy video has an alternative activity or no activity, the results are about the same. And even when we increase the number of noisy videos further, results drop only slowly. We also considered the effect of frame level noise, where we injected noisy frame in each support video. And also here, we are quite tolerant to noise. Results drop only gradually. So here is again some result clip. So all the videos in the support clips, in the trim support clips show person riding, and also in the test time in the query video we can find indeed this person riding, to indicate that the approach works. More experiments are in the provided paper, including comparison with alternative tactics. Then the last topic I would like to address in this tutorial on tubelets is about tubelet relations. And this is a work together with Shou Chen, Jinglin Shi, and again Pascal Mettes that appeared at ICCV this week. And it's entitled Social Fabric, Tubelet Compositions for Video Relation Detection. And here we consider the problem of video relation detection. And here is a typical video that is considered in this task, where the goal is to, given an input video, the goal is to output relation triplets. So to not only find activities, but also essentially find subjects, objects, and their predicate class. So the challenge is here not only spatio-temporal localization, but also the modeling of the interactions that are going on inside the videos. And as you can tell from this example video, this is quite challenging indeed. The problem is relatively new. It was posed by Zhang et al. In work in ACM Multimedia at 2017, and they also introduced the first data set to make research on this problem feasible. There was quite a lot of follow-up work, and the leading approaches have a few commonalities. They typically contain 3 steps, and the first step tends to be to generate object and subject proposals on short video snippets, then to encode these individual proposals and predict their relationship, again on the level of a snippet, and then to associate the relationships over the entire video to get a sort of video relation prediction in the end. Then there was work from Liu et al. That appeared at CVPR last year, and they, for the first time, can do video relation detection without the need for snippets. So they propose to localize individual object and subject tubelets throughout the entire video. What they then do in the second step is to filter out unlikely pairs of tubelets. And finally, they predict predicates for the remaining ones. And the approach is slightly more involved, but this is sort of like in general terms what the approach does. Now, the key idea that we have is that all these existing works on video relation prediction treat object proposals or tubelets as single entities, and then model their relationships a posteriori, like in the end. And so rather than modeling these relationships afterwards, we propose to classify and detect predicates for pairs of object tubelets from the start. So that is a different take on this problem. And as a consequence, we only need 2 stages where all the other approaches need 3. So we generate first what we call interaction proposals from tublet pairs, and then we predict the appropriate predicate that belongs to the pair of tubelets. And we call our tublet representation social fabric. So this is schematic overview of the approach. In stage 1, we form the interaction proposals. We do so by running object detection and linking them with a tracker. And then we consider all possible tublet combinations that appear in a video by classifying their interactiveness score per frame. Then we perform a watershed algorithm over all time steps of the pair. And those are sort of like the set of interactivity proposals that we consider. Then we encode all these interactivity proposals with a set of video language features as are common in the video relation prediction literature. So we use spatial location features that originate from a paper by Su et al. From ACM Multimedia 2020. For the visual features, we just use a faster RCNN backbone followed by ROE pooling. The language features are off-the-shelf 600-dimensional Word2Vec features pre-trained on Google News. I3D is just a standard one. And we also rely on masks that are generated based on bounding boxes of subject and object in tublet pairs following Xi et al. Then we have an encoding layer that normalizes features and tries to find what we call interaction primitives. And what this layer does, it learns a set of K interaction primitives so that we can represent each tuplet pair as a combination of such primitives. And to make this more clear, here's an example that tries to explain what is going on here. So we encode compositions of interaction primitives over tuplet pairs. And in the top video, you see a person sword fighting with another person. And the idea here is that this activity, this video relationship, is composed of interaction primitives, like there is a approach activity, there is a clash primitive, and there is eventually a fall primitive. Now, in the bottom, you see another video relationship, an adult chasing a child. And this one shares some of the primitives with the previous example, but not all of them, right? It will have the approach and fall primitive, but it also has a different one, which is in this case a run primitive. So akin to code words as used in a well-known bag of words like approach for images, this sort of like to find activity primitives on which to build an encoding for video relationship prediction. Now, based on these primitives, we encode each interactivity proposal, and then together we learn a fully connected layer classification head, which can be used to determine whether this tuplet pair makes for a good proposal. And we can also use it later to predict its predicate using the shallow network head. And this is used to just a binary cross entropy loss. So nothing special here. So in stage 2, after we have encoded each proposal, we feed the representation into a final linear layer to obtain predicate scores. And this predicate prediction is optimized with the softmax cross entropy. And this tells us not only what is the spatio-temporal extent of the video relation, but also what is the subject, what is the object, and what is the corresponding predicates. Now, there are also alternative ways of doing things. So we listed a few alternative representations. So one could rely on average pooling, which is a special case when considering only a single primitive. Transformers, of course. The advantage that we offer is that our approach provides a fixed size representation, and this is important because tuplet pairs are of varying length. Then we are inspired by NetFLAT and ActionFLAT, but they operate on whole images and videos, and our encoding operates on pairs of spatiotemporal tuplets. And to the best of our knowledge, we are also the first compositional encoding for video relation detection. Now, we evaluated our approach on the datasets by Zhang et al., who originally proposed the ImageNet VID VRD dataset, which contains about 1,000 videos and 35 subject-object categories for a total of 132 predicates. In follow-up work, they also introduced the VIDOR dataset. This one is far more challenging with far more videos. More object and subject categories, but less predicate categories. And taken together, these are the two benchmarks that matter in video relation detection, and everybody reports on both of those sets. So we first ablated the influence of the number of features. So what this shows is that our tuplet representation and using the primitive encoding effectively captures multimodal features. So essentially, the more features we add, the better the results become. So it's an effective way to exploit multimodality of video and to include that into tuplets. And here are a few additional ablations on parameters of the approach. So we looked into the number of clusters K to use for the primitives, and we find that actually it doesn't matter too much, but with 64 primitives, we got the best trade-off. We also compared the social fabric encoding with alternative encodings like average pooling, the transformers, and the net VLAD, etc. And on all accounts, our proposal is slightly better. And last but not least, we also considered the effect of having the two stages. So do we really need to have the interaction proposal encoding and the predicate prediction encoding? And indeed, it contributes to both stages. Then we also compared with all other approaches in the literature, or several other approaches in the literature. And I've highlighted an important comparison because Liu et al. Is the other approach that relies on tuplets, but where they combine the tuplets afterwards, we combine them from the start. And that has a good advantage on accuracy. So here's the comparison when we use the same set of features as they use in their paper. And if we expand the set of features, using also inspiration from other papers from the literature, we can further increase video relation results. So I think the takeaway here is that using these social fabric encoding, we outperform all snippet-based methods, as well as the only other tuplet-based approach by Liu et al. And this is another comparison where we especially look into the duration of the video relationship, because many approaches are based on snippets, so they have an advantage when emphasizing short video relationships. We were interested, does our approach show value, especially for videos where there are long video relationships? And indeed, as can be seen from this approach, where we compare again against Liu et al. From CVPR, as well as Xi et al. From ACM Multimedia, and we see that while we are better for any duration, especially for the longer duration, the difference between alternative approaches is more prominent. So the longer the video relation, the more benefit you will get from our approach. Then some success and failure cases. So here we have a success case, an adult next to another adult. And here we only show the predictions with very high scores. So the subject is the red box and the object is the blue box. Here's another example, an adult cleaning a horse. And although there is some occlusion going on, both tuplets are detected well together with the correct predicate. And this is also an example of a relatively long range relationship. This is a mistake, a failure case. So here the predicate is chicken in front of a child, and well, obviously we are looking at another chicken. So the object is misrecognized and that we cannot recover from that mistake. And here's another failure case, and this is due to inaccurate and redundant object bounding boxes. So method does not know how to cope with this particular case. All right, that brings me to the end of this part, and I would like to conclude with the following statements. Video understanding is treated by many as a glorified image recognition problem. I think that is not the best approach to consider video. So we presented holistic video perspective based on spatio-temporal tuplets, and showed some advantages for traditional and also more modern video recognition problems, especially the ones on few-shot learning and video relationship detection. So I hope this inspires you to also consider alternative approaches to video understanding, and I wish you an entertaining remainder of this tutorial. Should you have any questions and would like to reach out, please do so by contacting me via the usual means. And with that, I would like to thank you for your attention, and till we meet again. Bye-bye.
Okay, and that was Professor Kees Snoek from the University of Amsterdam in his talk. We have a few more minutes remaining before we begin our next talk. I guess Stratis and Hilde, do you have any thoughts on some of the broader, maybe even common shared themes brought up in Kees's work that's somewhat related to potentially your own?
I am with my kid next to me, so we might hear various sounds at the same time. But I think Kees addresses with his work many of the problems that are definitely open at the moment. For instance, localization or zero shot. Yeah, I think it represents an interesting line of work, a very interesting line of work in that sense. What is especially like something that I'm not working with, and I see Kees and I mean I see the community generally going forward, is the use of language and video, so multimodality. And yeah, so I'm not an expert in that. I'll be interested to hear what are your thoughts on, you know, like do you think we should go into using language more, less? Is it like a nuisance, or is it like a replacement for supervision?
Well, I certainly have my thoughts. Hilde, by chance, do you have some potential thoughts on this front?
Yeah, can you actually repeat the question?
Oh, sure. Stratis, you can correct me if I'm misrepresenting the question, but broadly speaking, I think Stratis was bringing up the point of how well, one is, should we incorporate language as a form of supervision in the problems that we care about in video, and two, how best should we do it? And I know that was explicitly a big theme of your talk, so I'd love to hear your thoughts.
No, that's correct. That's correct.
Yeah, so maybe I'm a bit biased because kind of like that's my thing. I'm not sure if, I mean, I guess language, it sounds great. Honestly, I'm not sure how far we can get there, because technically we just scratched the surface. So I guess I would be careful in making any fixed predictions about that. I would say it looks interesting and it has some features that classical supervision cannot kind of like provide, but we haven't even scratched it, so it's hard to actually say, okay, those will be the drawbacks and this will be the cases where we need fully supervised versus language. So perhaps I'm on it, but I would be careful in terms of framing, okay, it will be this way or that way at the moment.
Yeah, I think I share a lot of those similar biases, in that I think that you get a lot of more flexibility in our representation space, you know, relative to maybe our classical classification spaces that we've considered in the past. But there's still probably the space of language that we've been working with in the context of videos may not necessarily be the space of all the concepts that we want to really think about with videos. And then separately, there's broader themes and issues of systematicity and things that we still have yet to properly address, like in terms of thinking of how best we incorporate these multiple modalities. Okay, so I think that concludes our third speaker's slot. Again, if you have anyone in the audience, if you have further questions for Kees specifically, please feel free to send him a message. His information was on the last slide there, but it's also available on his website. On the theme of multimodality and self-supervision kind of at scale is our next speaker. Our next speaker is Yale Song. He's a senior researcher in the computer vision group at Microsoft Research. We're very excited to have him with us today, speaking on improving self-supervision and the representations we learn from videos. Yale, the floor is yours.
All right. Thanks for inviting me. Let me first make sure that you can see all the shared screens. Just give me 1 second. I might have to rejoin at a max security setting. So let's see you in a few seconds.
Sure.
Okay. I'm assuming you can see my screen.
Yep, your screen looks good.
Great. Yeah. So thanks for inviting me for this talk. I really like the direction of this workshop. I personally echo the goals and motivations behind this large-scale holistic video understanding. And I think there's just a lot of interesting work to be done in this area. What I thought I would do today is to provide my perspective on learning representations that'll be useful for holistic video understanding. And I will be specifically focusing on self-supervised method that learn from multimodal signals of video data. And also talk a little bit about how we can scale this up to learn from hundreds of millions of noisy online videos. Before we begin, let me spend a few minutes to talk about where we are today as I see it in video understanding community. I think the community has made a coordinated effort to build essentially an assembly line for video understanding. We have multiple different components, each tackling specific tasks and problems needed for the whole system to work. And we have models that do great on action recognition, video retrieval, highlight detection, all the way to the tracking and video synthesis, deepfake, and VQA. And the list goes just on and on. But can we really say that the current models are understanding the content of videos? This is a loaded question, but what are we building? What I think we are building is an army of highly specialized agents, each optimized to be good at just one thing. And essentially, we are building models to view the world through a straw. We are training models to solve the given task by looking at just enough information to solve the task. And consequently, I think these models will learn video representations that capture only a limited amount of information, which might be just a fraction of what's really needed for holistic video understanding. And one of the biggest issues that I see is doing well on one task can be misleading. A model can achieve state-of-the-art result on action recognition data set, but at the same time might fail miserably on other video tasks, such as captioning and question answering. And part of the issue that I see here is neural nets just love to cheat. It's been reported so many times that neural nets can do well on a task just by exploiting low-level statistics without really obtaining general understanding of the task itself. To give you a concrete example, sort of this one dirty little secret within the action recognition community is that there exists this strong scene bias in popular action recognition benchmarks. So a model can do extremely well on action recognition by simply relying on scene information and completely discarding motion information. This is quite evident from these examples from Choi et al. Even without seeing the actual human action, we can reasonably guess what action category each image might belong to. And so is true for neural nets. And there is this very interesting paper under submission at iClear for next year. And just to be clear, this is not my paper, but I found this to be very interesting. So what they do here is they convert a video into an image format by simply putting one frame, one after the other in this tile format. Then they feed that to an image classifier and train it with a standard cross-entropy loss. So essentially, this forces the network to ignore any temporal information and solve the action recognition task simply by using scene information. And the results are quite surprising. They achieve state-of-the-art on Kinetics 400, outperforming more sophisticated architectures like 3D CNNs and transformers. So are we doomed, or are we missing something fundamental in action recognition? Well, is temporal information necessary at all? Sevilla Lara et al. In their WACB 2021 paper, they show that temporal information is still essential for certain actions, but might be redundant for others. So they show this example where the frames are shuffled in order. Can you guess what the person is doing just by looking at these images? I'll give you a couple of seconds just to think through. The answer is yawning for both cases. And I don't know about you, but to me, I thought the person on top is sneezing and the bottom is crying. So they did an interesting set of experiments based on this observation. They tried to categorize kinetics and something videos into static and temporal categories. And to come up with these categories, they asked the humans to predict labels of videos where the frame orders are shuffled like this. If they can correctly predict the label, even when the frames are shuffled, then they categorize them as static, and otherwise they are considered temporal. Then they compare two neural nets trained on videos only from the static classes and another neural net trained only on the temporal categories. And what this graph shows is essentially that neural nets trained on temporal categories generalize much better than the one trained on static categories. To show this, they first get the baseline results, which is what we see here, by testing these models in the in-distribution setting. Then they freeze the weights and transfer that to a out-of-distribution setting. So they train a linear classifier on top, freezing all the learned weights, and in the out-of-distribution setting. And what they found is that when tested on temporal categories, the static pre-trained model performs significantly worse than the temporal model. But on the static test set, which is on the right, the temporal model performs almost as good as the static model. And this suggests that when you learn temporal information, those models actually generalize better to the out-of-distribution setting. And I think this is just a very promising result that shows, yes, there is still hope. Learning temporal information is still important. But as long as the current data sets have this kind of strong scene bias issue, it is really difficult to track the progress in a reliable manner. There has been some attempts to fix this kind of scene bias issue in video benchmarks. And one example is the mimetics data set. Here they take 50 classes from kinetics and collect videos that explicitly do not have a scene bias. For example, they collect videos of a person surfing in an indoor setting, miming violin action without the actual instrument, and playing bowling in a soccer field. And in a similar vein, me and my colleagues have proposed TGIF QA dataset for video question answering. So typical video VQA datasets contain questions that can be easily answered from frame level information, such as what is the color of the bulldog here? And we refer to these as a frame QA. And to make the task truly video-centric, we defined 3 QA types: repetition count, repeating action, and state transition. And we show that conventional methods do not really perform well on these challenging tasks compared to the frame QA tasks. So these attempts are great. They help establish benchmarks that are relatively less biased than the others. And then from time to time, there comes these really ambitious efforts to build what I call the big picture data sets. These are large scale, multitask, multi-label data sets that come with an extensive set of labels from just a wide range of tasks. And what I think is great about these data sets is it is significantly more difficult for neural nets to cheat in order to do well on this suite of tasks. So I think these are just great efforts that could really help the community to evaluate different approaches on a common ground. While these are great efforts, we have to consider this question of quality versus quantity. Well, this question may not be so much of an issue for model evaluation scenario. I think we can just probably optimize for quality as long as the quantity isn't unreasonably low and the samples are representative enough. But for model training, for neural net training, we all know that large-scale data sets are essential to achieve competitive performance. And as the model size gets bigger and bigger, we will just need more training examples. So what is really ideal will be, at least for the training regime, if we have a data curation process that is easily scalable to hundreds of millions of hours and to the video. So how can we achieve this? As long as we are focusing on the supervised learning, our hands are tied to this supervisor. But once we start having our models roll up their sleeves and learn by themselves without a supervisor, we can really start leveraging large amounts of unlabeled data for building foundational models, which can be used to solve many downstream scenarios. And I think we are all familiar with self-supervised learning these days. The basic concept here is that you design a pretext task that doesn't require manually annotated labels and train a neural net from unlabeled data from scratch. And once you finish this pre-training step, the learned representation and model can be transferred to different downstream tasks by attaching this new prediction heads specific to different tasks and training the network on a target scenario. So if you squint your eyes, what we are essentially doing is developing foundational models. To make an analogy, we are essentially developing this solid foundation that is essential to support buildings of various shapes and sizes and functionalities. During self-supervised learning, we prepare the model to become sort of familiar with the data distribution and learn how to represent each data point. And these representations then become the foundation for solving downstream tasks. So how do we currently evaluate these video self-supervised methods? Perhaps the most common protocol is to evaluate it on action recognition and video retrieval tasks. So these tasks, I think, focus on evaluating the quality of global video level representations. And there are also tasks that evaluate the quality of local representations, such as sounding source localization, temporal action segmentation, and various tracking tasks. So given that the goal of self-supervised learning is to learn representations that are generalizable to a wide variety of tasks, ideally, we would want to see methods working well on both kinds of the tasks. But the reality is we don't talk with each other. This is just rarely done in the literature. We often see papers evaluating their method on tasks that require global representation, but not necessarily the ones that require local information, and vice versa. And there could be many reasons for this, but one thing that's clear here is that this global versus local evaluation practice is suboptimal. It could produce misleading conclusions about the model's generalization ability. And more seriously, I think, it could potentially encourage us to design self-supervised methods that are just overfitting to a particular downstream scenario. And this is just the opposite of what self-supervised learning was originally set out to do, and could be harmful to the community as a whole. So with this background, I'd like to pose a research question. How can we build self-supervised holistic video representations? Specifically, first, what do we mean by holistic video representations, and how do we learn them? How can we evaluate them in an objective manner? And how can we best leverage noisy online videos as the source of training data? So in the remainder of this talk, I'd like to introduce two of our recent works that try to answer some of these questions. First, I will present our work that proposes a contrastive approach to learn global and local video representations from audiovisual self-supervision. And perhaps this part of the talk is directly related to the theme of this workshop, which is to build models that can do well across many different tasks. In this work, we show that we can pre-train our model only once and transfer it to solve different tasks like action recognition, event localization, to the lip reading and deepfake detection. Now, the self-supervised learning benefits from larger scale data. So in the second part of the talk, I will introduce Archive 100 million. It's the largest video data set with high audio-visual correspondence that could be useful for self-supervised learning. So let's get to the first part. This is a joint work with my colleagues at MSR and Zhao Yang from SYSU. So the central idea behind this work is learning global and local video representations. So what do we mean by that? When we consider a video sequence as space-time cubes, we could consider a few subspaces that each encode different aspects of video data. There could be this spatially local, temporally local representation, which captures dense information at every space-time cube locations. Then you can temporally pull it and obtain spatially local, temporally global representation. And this will give you, for each spatial location, a summary view across time. You can also spatially pull it and obtain spatially global and temporally local representation. And this might capture time-sensitive information. And finally, we can pull it in both space and time and obtain spatially and temporally global representation. And this will give you a high-level summary of the whole video sequence and often being used in sequence-level classification tasks. And for audio, there will be, since there is no notion of space, you can have local temporal representation and global temporal representation. Now, it'll be an interesting thought experiment to think about which of these representations is important for different kinds of video tasks that we know of. And perhaps more importantly, how can we learn these representations without using any labels? So in this work, we consider massive amounts of online videos as our training data. And in particular, we aim to learn from the natural audio-visual correspondence as the primary learning signal. And I think there are so many ways to leverage audio-visual correspondence, depending on the granularity of the information that we match against. Perhaps the most common idea is to learn video representations by capitalizing on global audio-visual correspondence. These approaches typically obtain global representation of audio-visual signals, and they design loss functions that match their representations to tell if they come from the same video or different. And as a result, this evaluation tends to focus on tasks that require global representation, like the action recognition and sound classification. And there are many works that follow this specific scheme, and most of these existing approaches differ by like how they obtain the representations, what is their network architectures, how they construct positive and negative pairs to contrast against, and how they define the self-supervised loss function. Now, when we consider learning from this dense audio-visual correspondence at the local region and time level, things get a little bit complicated. This is because we don't know which specific region and time in a video is related to the corresponding audio track. It might come from this tiny local region, such as your lip or your talking head, or it could come from, much larger region or multiple separated regions at once. And when we try to construct a contrastive learning objective, for example, this leads to a challenge of essentially modeling many-to-many relationship. There are some approaches that learn from this spatially localized audio-visual correspondence. So these approaches typically take spatially local but temporally global representation of the video and try to learn region-wise correspondence between audio and visual signals. And evaluation tend to focus on a different scenario that requires this type of local representation, such as sounding source separation, localization, audio spatialization, which is also called upmixing, and audio-visual object detection and tracking. So in this work, we want to learn a holistic video representation that captures both global and local information. What do we mean by that? We learn both spatially local and temporally global representations, and spatially global and temporally local representation in a joint manner. So this is our way of learning this dense, spatially and globally local representation, but in a factorized manner. And unlike most existing approaches, we evaluate our method on both the tasks that require global information, such as action recognition, and also the ones that require local information, such as event localization, lip reading, and deepfake detection. Here's a high-level overview of our approach. Given video and audio signals, we first obtain their temporally global representations, and while preserving the spatial dimensions in the visual channel. Now, we perform contrastive learning between the audio and visual features at every patch location. And here we use samples from different videos as the negatives. Now, since we don't have the region level ground truth correspondence between audio and visual signals, we formulate this as a multiple instance learning problem and apply the well-known MIL and CE objective. For temporally local representations, we first compute these dense embeddings and use the spatially local representation that we learned from the top part to compute this audio-visual attention map and use it to pull the attention pooling. So intuitively, this attention map gives us sort of the sounding regions in the video. And these are, in general, helpful to learn audio-visual correspondence. And for audio, we do the similar process and preserve the time information and get the temporally local information. And finally, we perform contrastive learning between audio and visual features at every time locations. Here, to encourage the network to learn local temporal information, we use features from different time steps of the same video as the negatives. And one important detail I want to mention is that audio signals typically have a higher sampling rate than visual signals, which means there might be multiple instances that match with a single visual frame. To deal with this, we simply consider all the audio features that fall under the time span of one video frame as positives. And if you squint, this is quite similar to what we have on top. For a single instance, we have multiple possible positives. So again, this leads to MIL and CE objective. How do we evaluate this? As I sort of emphasized before, I think establishing a good evaluation protocol is very important. The conventional protocol here is to take a pre-training data set that is roughly in a similar distribution as the downstream task data sets. For example, we often pre-train a model on kinetics and transfer that to action recognition. Or take maybe a speech-centric data set and transfer that to speech-related tasks. Oftentimes, you take one way or the other and demonstrate method on either of these settings. But in this work, we evaluate our model on a unified framework where we pre-train our model just once based on a combination of different data sets and transfer that to widely different downstream scenarios. And to my knowledge, this is rarely done in the literature. And I hope the community will move towards this direction, which is sort of this holistic way of evaluating self-supervised video methods. So to start off, here are some results on the standard action recognition and sound classification, which we refer to as the global tasks. So we can see here that our model achieves competitive performance on UCF, HNDB, and ESC data sets. If you see on the bottom, the two row, we are reporting two sets of results. One is pre-trained on a combination of kinetics and AV speech with 240K clips. And we also tried our model on the conventional protocol where you pre-train a model on kinetics 400 data set. And this second model, because the kinetics is action-centric data set, this leads to slight performance boost on UCF and HNDB. But the environmental sound classification data set, ESC, we see the opposite pattern. But I think overall, these differences are not too significant. Next, we evaluate our method on deepfake detection. This is a task where identifying fine-grained audiovisual inconsistencies in a video is crucial. I think the model needs to identify this misalignment between lip motions in a visual feature space and the speech in the audio feature space. There could be unnatural appearance of the face at lip regions given the audio, and sometimes even this asymmetry between different visual parts like local face regions, left and right part, or maybe the movement of the face might be inconsistent with the rest of your body. So the current state-of-the-art approaches achieve this video-wise area under curve score of 91.5. And we haven't seen much reported results on self-supervised methods. So we just ran these sets of baselines by ourselves, which is shown in the second group of results. Note that all these methods are optimized to learn temporally global representations. DPC, dense predictive coding, and VDIM, video deep informax, learns the spatially local representations, but others learn just spatially and globally, spatially and temporally local, global representation. Compared to these methods, we achieve much better performance when pre-trained on the same data set, KAV15K, which is shown in blue. And when we take our previous model, which was pre-trained on KAV240K data set, we achieved the state-of-the-art results on this task. We also evaluate this on lip reading using RLS2 and RLW data sets. It is the task of visually recognizing a speaker's utterance, this is quite challenging because lip movements for different sounding letters can be visually similar to each other. For example, ba and pa and da and ta. If you just look at my lip region, they are visually identical. Again, here we compare with existing supervised method and report our own results for self-supervised baselines. And overall, we see similar pattern as before as deepfake results. And this is perhaps because the lip reading solving that also requires both spatially local and temporally local representations, which the current self-supervised method do not do very well. One interesting experiment that we did in this work is this question of, do we really need off-the-shelf face and mouth region detectors? The state-of-the-art method require these off-the-shelf detectors to achieve good performance. Like in the deepfake, they first crop the face region, and for lip reading, they crop the surrounding region of your lip. And in our work, we compute, if you remember a few slides back, we compute this audio-visual attention map as part of the inference process. And intuitively, the attention is capturing regions with high audio-visual correspondence. And in the scenarios of deepfake and lip reading, human face and mouth regions are most highly correlated with audio. So one way to evaluate the effectiveness of the attention that we compute is to compare that to an off-the-shelf specialized detector. Here we compare with the state-of-the-art method, which require these mouth and face detectors, and compare that to 3 of our evaluation settings. The first is we don't use the attention map, we just do global average pooling. Second, we do our proposed attention pooling. And third, we follow the previous work, use these off-the-shelf detectors to do the pooling. And we can see here that global average pooled representations perform very poorly. The attention-based pooling works quite well competitively as the detector-based method. And we believe this is a promising result that suggests maybe we may even not need these off-the-shelf complicated detectors to solve these tasks. If you learn the representation right, then the representation itself will already give you this sort of region detectors necessary for tackling your task. And here we visualize the audio-visual attention maps, and we can see they work reasonably well in most of the cases. Not always. If you see these bottom 3 cases, these are scenarios where there is no apparent audio-visual correspondence. Okay, so that's the first part of this talk, and let's move to the second part. In this work, we propose an automatic dataset curation process and release the resulting video dataset called Archive 100 million for audio-visual video representation learning. Why do we work on this? What's the motivation behind this? Well, learning from this seemingly infinite amounts of unlabeled videos is a very attractive idea. Like you have this couch potato continuing to watch online videos and learn useful concepts of the world. But it also poses significant challenges on how to deal with noisy real-world videos. I would like to ask, can we really learn from any videos? My guess is probably not. I would say many online videos do not provide necessary audio-visual correspondence, such as the ones shown here. This is primarily because audio overdubbing, which essentially wipes out the natural sound coming from the visual scene. And ultimately, this breaks this audio-visual correspondence assumption, which is, the sounding source should be visible in the visual scene for most of times. And breaking this assumption can be harmful for self-supervised methods that rely on this assumption. And I think because of this noise, audio-visual data sets are usually difficult to scale up. To find videos that meet this assumption, you either collect domain-specific data sets, such as AV speech that contains videos of speaking persons, or greatest hits where you record yourself hitting everything that you see on your surroundings. If you want domain agnostic data, you typically turn to data sets that are manually annotated or verified by humans. This is to ensure that this audio-visual correspondence is reasonably guaranteed in most of the videos. However, we see, compared to this recent video text data set, How to 100 Million, these are just miles smaller than this large-scale vision and language data set. So in this work, we released the largest audio-visual video data set called Archive 100 Million. It stands for Automatically Curated Audio-Visual Video Data Set. This is 2 orders of magnitude larger than audio set, and it is twice the size of How to 100 Million, which is currently the largest available data set. Our data set curation process is fully automatic. It doesn't require any manual annotation or human verification. And because our method doesn't require a predefined taxonomy of concepts, keywords, and categories, there is a very large variety of concepts appearing in our videos. And as I will show in a sec, the representation trained with our data set shows great performance in several downstream tasks. So how do we do this? We formulate a constraint optimization problem where the goal is to find a subset from the large population that maximizes the total mutual information between audio and visual channels of the videos. Intuitively, this mutual information tells us how much the knowledge of one variable reduces the uncertainty about the other. So a subset with the maximum mutual information is just likely to have a high portion of videos with audio-visual correspondence, which is precisely what we want in audio-visual self-supervised method. The challenge here is, of course, how do we estimate mutual information? So the MI estimation method can be largely divided into this instance level and set level method, depending on the granularity of the alignment that you're looking for. The instance level method estimates the mutual information on a per video basis by aligning channels of a data point, such as audio and visual information, without considering the whole population. And this can be done using the contrastive learning approach that is quite popular nowadays, by using this co-occurring audio and visual signals as positive pairs. But there is this chicken and egg problem, if you think about it. Contrastive learning requires a data set where we can reliably construct positive pairs. But this is exactly what we set out to find in the first place. So in this work, we use the set level method, which takes the whole population of the subset into the account. So among the set level method, we use specifically the classical clustering-based algorithm to measure the mutual information. So in a high level, here's how it works. Given a candidate subset during your optimization process, we cluster all the videos in that subset with respect to audio and then the visual signals, respectively. Then you will have this contingency table of clustering assignments with respect to the audio signal and then the visual signal. We measure the mutual information in a discrete space from this contingency table, which essentially encodes the overlap between audio concepts and visual concepts. With this definition of set-based mutual information estimator, we now turn to solving the constraint optimization problem. And this can be considered as an approximate submodular optimization. So in general, finding a global solution requires a combinatorial search, which is NP-hard. So we implement a greedy solution, which is widely used in the submodular optimization community. And specifically, we use the batch greedy version proposed by Chen and Krause. This method randomly samples a batch from the remaining pool of candidates and searches for the next element, single element, to be added to the solution only within that batch. So this eliminates this relatively huge search space of the candidate set. You only need to look for samples in a batch. And this batch trick reduces the complexity from, well, exponential to quadratic. And then this batch trick then allows you to get this linear complexity in terms of the candidate set size N and the mini batch size B. So we use this framework to curate a large scale data set. So for this, we begin with a large collection of videos, which consist of 140 full-length videos collected from YouTube. And this spans more than 1,000 years in total duration and requires 2 petabytes of storage. From this, we extracted up to 3 10-second long clips from each video. And here, instead of just randomly extracting these clips, we performed some basic shot segmentation and diversity sampling so that we just don't get redundant clips. And if you're interested in nitty-gritty details, here's a very simple way to achieve this. And I've worked on shot segmentation and highlight detection for a while, and I was quite surprised these 2 lines of FFmpeg comment can give you quite competitive results. So the result here is 300 million clips, each 10 seconds long. This is in total 95 years in total. And this set becomes our population. And our goal then is, among this population, we want to find a subset with high audiovisual correspondence. And in the experiments that I'll show, we generate data sets with this population at different scales. And this is easily done. You just have to solve this optimization problem. So we evaluate our method in the self-supervised learning scenario. And I know there's a lot going on in this figure, so let me hash it out. So each bar represents top 1 and top 5 accuracy in the downstream data set, in this case, UCF 101. The pink bar is when you take randomly initialized weights, freeze them, and just train the linear classifier on top. The pink is the performance of a model pre-trained on one of the baseline data sets. So at the 20K scale, it is kinetic sounds. So yellow is the performance of a model pre-trained on a random subset from our 300 million population. And the blue is our method, but with the instance-based MI estimation baseline, we used the SimClear objective. And green is ours with the proposed set-based MI estimation method. And all these graphs at 20K show that downstream performance of an identical architecture trained on different data sets with the same training protocol, and all the data sets under 20K, they are of roughly in the same scale. And we repeat this experiment for 200K and 2 million scales, using VGG sound and audio set as our baseline data sets. And as you can see, our data set leads to competitive performance on UCF 101 here. And it's worth pointing out that these baseline data sets, kinetic sounds, VGG sound, audio set, they all require manual annotation and or human verification. And on top of this, the biggest benefit of our approach is the scalability. We repeat this experiment up to 100 million and improve and achieve the improved performance. The point that I'm trying to make here is not that we achieve the state-of-the-art results, but that we have a data set curation method that can easily scale up. And it's well known that self-supervised methods perform well when it's pre-trained on larger data sets. And our method precisely enables you to do that. Now, we repeat this experiment for sound classification and audio-visual video classification and observe similar patterns of the results. Now, one important result that I specifically want to point out is that this yellow bar, the randomly sampled videos from the same population, it doesn't actually give you competitive performance compared to our method, but also compared to the baseline. And this makes sense because if you just randomly take videos off the internet, there's a high chance that you will encounter these noisy videos. So you solve it either by manual processes or using our automatic process. And because our data set curation process doesn't require a predefined taxonomy of concepts, keywords, and label categories, the videos in our data set show an incredible level of diversity in both the audio and visual concepts. I don't think I've seen a data set that has a number of videos that shows how to unbox shoes, for example. So our project webpage is up and live. There we provide the data set, code to generate the data set, and various other results like the basic statistics, concept distribution, and we also have the video browser just for you to go and check what kinds of concepts that they appear. So you can visit the link below and check them out. So that's all I have today. I hope that I provided you why self-supervised learning is promising direction for holistic video understanding. I think it provides you this foundational representation that can lead you to successful applications in many different scenarios. And what needs to, and I also was trying to say, what needs to be done to learn holistic video representations in terms of algorithms and evaluation protocol and the data sets. And with that, I'm ready to take your questions. Thanks.
Wonderful. Thank you, Yale. Wonderful talk. And the new data set seems like a very, very cool resource. I guess we'll start with one of the questions in the chat. So the question is posed as follows. Rather than looking at reasoning-based tasks such as recognition, etc., for learning generalizable representations, as is common practice, could it be useful to look at generative tasks towards this end as well? And I guess we can interpret reasoning-based tasks as more broadly like discriminative versus generative in the context of self-supervision for video.
I think it's a very good question. A famous quote here is, "What I cannot create, I don't understand," by Richard Feynman. I think the community has looked at that motivation maybe in mid-2010 with this task of video prediction. And we are still moving forward with it. I think there is this really cool paper that I cleared this year. What is it called? MokoGen HD. It's by Sergey Tolyakov from Snap Research. And they really, master this high resolution video synthesis results. But that said, I think there's some, many difficulties that we really need to solve to make the evaluation protocol complete. I think measuring the quality of the perceptual quality of the generated videos is just difficult. Ultimately, you need to ask humans with, subjective opinions. And there is an evaluation issue which leads to design of the loss. I think many years of blurry results concluded that maybe pixel level loss functions aren't what we are looking for. Maybe we want to look at, predicting the generating instances at the embedding space. And I think that's part of the motivation behind the InfoNCE paper from Aaron van den Oord. So to answer that question, I think the motivation still holds. I think the synthesis task, synthesis or generation task as the objective for learning as well as evaluation. I think this is a very promising direction, but we have this challenge of designing good loss functions and designing good evaluation protocol. I think though, there are already some successful application scenarios with video synthesis.
Yeah, I think the dichotomy of generation versus discriminative tasks for self-supervision is very intriguing. I think maybe also touching on the theme of multimodality. It's so in natural language processing, generative models have been very successful, and we've had a few of those in some sense at like a video token level in the video space. But I guess, do you have any thoughts potentially on how generative models for video might sort of go beyond the limitations of the high dimensionality that comes with trying to understand all the pixels across a huge number of frames, to maybe get some of the higher level downstream tasks that maybe beyond just action recognition, but into a little bit more of a like inter-event understanding, like causality and things like that?
So I think this is a loaded question. Let me hash it out. So first, I think the language is just a different kind of a beast compared to visual and audio signal. Not only the language is sparse and discrete, and audio and visual, they are high dimensional and continuous space. The language is by definition symbolic representation, and visual and audio signal, they are low level signal. And the prediction generation task, synthesis task as the form of supervision in the language space, I think it's incredible because incredible in the sense that it's incredible it works so well. And it's incredible in the sense of it's a great form of supervision. I think in the symbolic space, doing the future prediction or fill in the blank type of generation task, it makes sense intuitively. When we think about future, when we think about hypothetical scenarios, I don't think we think about them in a pixel level accuracy. We just think about them in a conceptual level. And that's precisely what, not precisely, but more similar in the language space than video and audio space. I think in the video literature, people have looked at trying to predict future in more abstract, feature embedding space, or try to predict the action of the future, like early action recognition. So I think these are very promising direction and maybe a form of self-supervision. The other part of your question was multimodal. If I understood your question correctly, and correct me if I'm wrong, you're asking if we can design a evaluation scheme that really looks at the multimodal signal. Is that right?
Yeah, I think that's close.
Yeah. So I think eventually we want to get there. When I see video, I look at the scene, but I also hear. And I think that's what video understanding means. I listen to the sound, and if there's utterances, I process those speech in, at a semantic level. And I think eventually we want to get there. And with this army of specialized agents, I think we are getting to the right direction. But obviously, we need a lot of more work to be done.
Yeah, I agree. And I should add, I didn't mean to quite load the question as much. The context for the question stems from models like VideoBERT and others from recent years that have tried to tokenize the video space, and also I guess the emergence of video transformers that tokenize by discretizing the images into patches, and have had some measure of success in that capacity. But overall, I think there is a theme of careful consideration of how to treat the raw signals that we are given, since we do operate with a much lower level, higher dimensional input space in that regard, in order to best achieve what we want ultimately in terms of downstream tasks. And I think that's an ongoing and active area of research, and very exciting.
Yeah.
Very cool. I guess, how much time do we have left? Oh, I'm not sure we have enough time for that question. Well,
Let's try.
Okay. Well, I have maybe another question, which is, are there tasks which are not listed here, for example, that you would like the video field, like in terms of your ideal sense of representations that video models can get in a self-supervised way? What might some of those tasks look like if they're not already expressed in this flowchart here? And I guess as one point of inspiration that's also present in this diagram, robotics is increasingly looking at videos and video understanding to help guide the development of like algorithms for those settings. So yeah, are there thoughts that thoughts of tasks that you would like to see now for video-based representations?
Yeah, absolutely. And I think part of these is already being done. Vivek, are you trying to say something?
Yeah, so I was trying to add up his question by saying, so what's next also I would add.
Yeah, that's a great question. Interaction. Like, agents interacting with the environment, actively looking for things to look at next, trying to decide what to do, try to be successful in a given task, even if mundane. I think there's large literature that tells human visual cognition, if you don't have the agency, the notion of agency, if your hands are tied, your legs are tied, you're just sitting and you're presented with visual signals that you didn't intend to get, then that significantly harms the cognitive ability. A lot of these experiments are done on, like guinea pigs, mouse, and animals. But I think the point is clear. Just intuitively, if we don't have intention and interaction with the world when obtaining these visual representations, I think there's something significantly that we are missing. And same as go for the evaluation scheme. If none of these tasks really measure the interaction part. Now, I know there are already significant effort in like visual navigation, etc., that leads to that direction. And I should have included those as well. So I think that's like the next important step that the video community should also focus on.
Excellent. As I said, I think that the answers to that question can itself lead a much longer discussion. But yeah, so thank you again for the amazing talk. And I'd like to give a big thank you to all the speakers from our morning session, Hilde, Efstratios, Cees, and Yale. This concludes the first half of our tutorial session. I'm really looking forward also to the lineup of speakers that we have in the afternoon. So looking forward to seeing everyone after the half-hour break. Thank you again.
All right, thanks.
Hi, my name is Raquel Urtasun, and I am the founder and CEO of Wabi. Today, I'm going to be talking about an AI-first approach to self-driving. I think it's worth to start by saying that self-driving is really one of the most exciting and important technologies of our generation. And if you think about it, right, one solve at the scale is really going to change the world as we know it and make it a much better place. So I hope that everybody here is as excited as me as what's going to happen when this technology is ready. So before I go into the main topic of today, we are going to start by reviewing how typically a self-driving car actually makes decisions. So if you look at most of the software stacks out there, they work in the following way. First, the vehicle senses the environment. This is typically done with cameras, LiDAR, radar, etc. I'm illustrating this here with a LiDAR point cloud, which is basically view from the top. And typically, the first thing that a vehicle does is that it localizes with precision of a few centimeters. And the reason to do this is that typically vehicles have high definition maps that have a lot of prior knowledge about what to expect to see in the environment, where are the lanes, where are the intersections, pedestrian crossings, what are the rules in those intersections, etc. Okay, so knowing this information a priori makes the task of driving much simpler, and that's why localization is typically key. Now, the next step is that the vehicle perceives all the objects around it, and not only needs to kind of understand the present as well as the past, but also needs to understand how these different actors are going to be moving in the next few seconds. This is typically called prediction in self-driving. It's called motion forecasting, typically in academia. And then now that we have understood, the past, the present, and the future, the next thing that we need to do is basically decide what is the maneuver for the self-driving car to execute. And that's the task of motion planning. This is a process that we repeat every fraction of a second, typically synchronized with the LiDAR, so like 100 milliseconds. And basically the last bit is actually control, where, if you think of, what the decision of the self-driving car is and what the vehicle actually executes, there is typically a slight difference. And basically the control system, moves or basically changes slightly the plans such that what we intended to execute is actually what we execute. Okay, and this is due to friction, not having exact vehicle dynamics, etc. These discrepancies. Cool. So in a nutshell, this is how self-driving works. Now, if we look a little bit at the industry, there's been a lot of promises, right? It's like self-driving cars are here, almost here, for now many years, right? So there's been meaningful progress since the DARPA challenge, which was now 17 years ago. But when you look at commercial deployment of this technology, it really is only in very simple and limited operation domains. And I guess probably you're thinking, why is this the case? Why is this promise of self-driving, something that is still a promise, and these vehicles are not here? Well, there is really like two reasons for this. Well, first, the problem is really hard. If you look at the task of driving, it's actually pretty nuisance, because small changes on the environment might actually make you take very different decisions as you drive around. Now, if you also think about the number of possibilities of how the scene can be presented to you in front, right? There is exponentially many. Whether it's the weather conditions, the road conditions, the traffic, the appearance of the actors, the background, etc. Right? There's many possibilities, and a self-driving vehicle needs to handle all the possibilities that might arise on the operation domain where it's actually driving. And what makes this even harder is the fact that, well, not only there is many things, But most of these things, we actually rarely or never see them in a lifetime of a vehicle, right? So many things appear very, very rarely. This, there is very, very long tails of this distribution. And, in order to really observe it in the real world, you need a gigantic fleet and then driving, trillions of miles, right? And that makes, extremely hard this task. But it's not just about the problem being difficult. There is also potentially a problem with the current technology, right? There has been very little evolution since the DARPA challenge. Still, software stacks in industry, they look very reminiscent to, what, teams sort of had in DARPA challenge. And it's not surprising because most of the, current industry is actually led by people that led DARPA challenge. And, one of the main issues with current technology is the fact that they really rely on manual tuning. It's very hand engineered. It looks a lot like an expert system. And it's very, very capital intensive. You need this massive, fleet driving miles, in the real world, in order to really get a sense of how your system is doing. And, people brag about the millions of miles that have driven, but it's not necessarily, in my opinion, something to brag about. I think this is, you should drive much less and then you should progress more. Now, if we go one level deeper in terms of, what are the sort of the problems with the current approaches of driving. So next, I'm gonna give you a little bit of a flavor of, how development in industry works and sort of where the issues come. So let's start by saying that, if, one of the main problems right now is that current software stacks are very, very complex. And they have, a couple of thousands of engineers typically working on just the autonomy software stack, right? And if you think of a developer is tasked with a very, very small part in this very complex system. For example, you are within the perception team and you actually work on, say, pedestrian tracking, right? So your view of the entire system is extremely myopic. So it's going to be very, very hard to build, very good global solutions by looking just at the individual pieces that somehow need to fit. And then typically what is designed is just interfaces, right? But that's not how you make compatibility really for, solving such a complex task as self-driving. Okay, so there's the problem of, this being, this technology being developed in silos. And the analogy I always make with this is the fact that imagine you want to build a puzzle. Okay, so what is the best way to build a puzzle? Where you take something that is already completed and then you cut pieces, right? It's a holistic top-down approach. Now, the equivalent of what sort of the industry way of working is more of, I'm going to develop, in silos or in isolation these pieces, and then I hope that they fit together. And then I'm going to do small modifications to try to align them. And this is how I get the complex system. So as you can imagine, it's very, very hard to come up with the optimal puzzle, the shape of the pieces, by actually just shaping them, bottoms up, right? So this is, sort of analogy of what I was talking about. The other thing that is also problematic is that because these interfaces between these models are designed by humans, they are designed by humans for humans, meaning that, they are very, very narrow, meaning there is very little information passed. Maybe it's the vehicle state or the state of other vehicles on the road or other actors on the road, as well as maybe some trajectories and some, let's say, some measure of confidence, right? So by that point, you have lost so much information that you had, when you started with the raw sensor data, right? So the problem or the consequence of this is that you're going to have cascading of mistakes. So as you go down the stack, right, you have less and less information, you go more and more blind, and you have to make more and more complex decisions, right? So this is kind of the opposite of what you would like. So you end up with these cascading mistakes and not being able to recover from them. On top of this, typically the way that these teams work is that you have them, driving around the world, with a fleet of vehicles, right? And every time there is an intervention or a problem, you basically kind of look later on at that data, and then you categorize mistakes. And then for every type of mistake, there's two things you can do. You can try to build a holistic solution or change your existing solution in a meaningful way or a major way, or you can build some modules that actually address that specific problem you've seen. And unfortunately, what we see in this industry is the second approach, which is that imagine, your system is having issues with leaf on the ground, like things that are, objects, and it's gonna, slam on the brakes, things like this. So what do? They basically build a leaf classifier, and then somehow put it in this decision-making process of the vehicle. Let's say that you have problems with a bike rack. They build a bike rack classifier or detector. And then through your decision process, again, you have one more of these things. And then somehow you need to build this, kind of expert system at the end. Right, so this is now, you cannot just build a model for every single thing that might happen on the road. Right, this is just so complicated, and somehow combine this by hand. Right, so that's not scalable. And then you need bigger and bigger groups, and that's the reason why you get this, massive amount of engineers working in the industry. And on top of this, there is, very little to no automation. Right, every time that you make a change, say you're making a change in your perception system, then you need to retune everything else. And then you need to go one step at a time, retuning this, right? So this is something that is very costly, and it doesn't work well, right? And you typically what happens is that it takes 1 or 2 quarters to land a very small change. So this is what slows down progress extremely significant, and there is a lot of developer productivity is actually pretty low. All right, so we need something else. So people have looked at AI as sort of the holy grail of, can we just use AI and it's going to solve all our problems, right? So the idea is that you have maps, you have sensors, and then you have this magic thing, black box in the middle, with the hope that it's going to give you the right output, which is things like steering command, acceleration. Now this approach also doesn't work, right? And first of all, it's very difficult to make progress where the only thing that you have is a black box. Maybe you can try different architectures, maybe you can try to add more data, but this is not how you're going to solve this complex problem. And furthermore, it's actually pretty difficult to verify the system, right? Or to get any interpretability of what the system is thinking. And if you think about also the fact that you need to be able to react or accordingly or do the right thing, in safety critical cases, right? So you need examples of all these things. And then the question is, how do you collect these examples? Well, you cannot just go on the road and explicitly get to near accidents, right? That's not something that is ethical or, that, from a safety perspective, we will be, sort of comfortable with, right? So that's also problematic, right? That the systems do not, have compound errors, do not generalize well when something is about to happen. So we need something else. So over the past couple of years, I've been advocating for a different type of approach that kind of takes the advantages of these two things without inherently their disadvantages. And what this approach is AI first, meaning that we're going to have something that is end-to-end trainable, but it's going to be modular. It's going to be interpretable. So it has also some of the great characteristics of the advantages of the traditional stack. Okay, but also inherently the advantages of having a single system. All right, so in more details, what does that mean? Well, with this AI first approach, so we're going to be able to train the entire system at once. So this is great because you can actually use more complex functions. You can, instead of having these very simple interfaces, along the stack, even for motion planning or control, you can access raw sensor data. So there is no more cascading of mistakes. All the models are trained for the end task, meaning that every time that you improve perception, you improve it for the task of driving, not just for perception metrics, which is a problem in the industry. And you get interpretability, and you can kind of verify, and it's better for safety. The type of algorithms that we've been developing, which are these deep structure models, are also scalable. They can perform very complex reasoning, can generalize well across different geographies, different countries, different sensor configurations, etc. This is very important because self-driving vehicles are important when they get here to scale, not when they can do a very tiny operation domain. And finally, it's very affordable because you can develop all this without building hundreds of models. You don't need thousands of engineers. You can actually do this with a much less need for a large engineering team. On top of this, the other thing that is important, and I will touch a little bit today on this, is the fact that there has been misunderstood really the importance of simulation in self-driving. So yes, it's typically used, but only has a secondary role. Instead, simulation is as important, in my opinion, as autonomy. And in particular, the simulator that actually is, the self-driving industry is a simulator that works in closed loop, meaning that it's reactive. It's like a video game without necessarily being a video game, right? But you can test, how the vehicle can react to the environment reacts to the vehicle, etc. So you have to unroll, right, your plans in order to understand this compound of errors, etc. You can test safety critical cases at the scale, and in particular, we are creating a super high fidelity simulator that we can simulate the raw sensor data, meaning that we can test the entire software stack in near real time. And this is a game changer compared to what you see out there. And the reason why is because now you can actually test the entire software stack. And in our case, because we have an AI first approach, you can even train the entire software stack, right? So this is really self-driving 2.0, next generation of self-driving, where instead of having a robotics mindset, you start with an AI mindset into developing holistically this technology. Cool. So very quickly, agenda of today, I'm gonna talk a lot about autonomy, which I thought that for this crowd will be of interest, and I'm gonna give you a glimpse about the simulator as well. Okay, because as I said, these two pieces are super important and they come together hand in hand. If you only have one, you're not gonna solve the problem. You need both, and you need next generation for both. All right, so let's start with autonomy then. Cool. So we are gonna basically go through. We're gonna start with a model that is very simple, and we're gonna add more and more levels of complexity. And at the end, we're gonna take, and handle the entire software stack with a single model. Okay. And I thought that doing this, step by step, will actually, sort of give you a lot of insights into what goes into how to model this, and what are the the different things that you need to take into account when you go into building such a complex decision-making process as a self-driving vehicle. All right, so the first thing that we're gonna do is we are gonna start with a single AI system that is able to do perception and motion forecasting, okay? And in particular, if my computer wants to work, great. I'm going to start with sort of the first of its kind. So many years ago now, I guess, or 3.5 years ago, we showcased this paper called Fast and Furious, which was the first time or the first approach that was really unifying this. And the idea was actually pretty simple, but very, very powerful, which is that, you can have your LiDAR, in this case, your input sensor data, LiDAR sweeps. You're going to pass it through a neural net, your favorite convolutional network, to get some feature representation. These are special features, right? Inverse view. And then we're going to basically have a branch that detects the actors of interest. Sorry about that. And a second branch that is going to basically regress the trajectories of these actors into the future. Okay. So very simple multitask representation for doing the entire perception as well as motion forecasting. So this huge piece of the stack reduced to a single network. Okay, so this was actually a very simple idea, very controversial at the time in the self-driving industry, but actually it worked remarkably well. And in particular, what I'm showing you here is results at the time where you see the quality of the detection as well as the prediction. In this case, is shown with these dotted dots. Okay, this is the prediction into the future of what we believe the actors are going to be doing. Using a single dot, it means that we predict that this actor is static. Okay, and you see the level of complexity of how many actors and things are happening in the real world, right? So self-driving is pretty tough. All right, so this, you can do this inference, in around 20 to 30 milliseconds, and this thing was able to really blow away approaches that have first perception and then more traditional motion forecasting. Okay, so very, very simple but very powerful idea. All right, so the next thing that we're gonna do is that here I was showing you LiDAR as input, which is For most self-driving vehicles, the sort of the sensory data of interest, or that is, or the primary sensory modality. But obviously, we can use multiple sensor modalities. Okay, and I'm going to show you one example. We've done more in the past, but particularly, right, we can very easily use cameras as well. And something that works actually remarkably well is to somehow get feature representations of the images, and then basically fuse this information not just as early fusion or as late fusion, but actually fuse along the way, and let the network learn how to fuse this information. Okay, so this is just a single network with two paths. And the other thing that is interesting here is that these operations here of fusing information are actually geometry aware, and they are based on extensions of continuous convolution. So there is some nice kind of math in terms of how you can do this. All right, so this is, we have done similar things with the radar as well. You will see in a bit how to use maps as well, but you can basically fuse all your sensors and learn how to fuse. Okay, very, very important. Learn how to fuse works much, much better than early fusion or late fusion, which were the very traditional approaches that typically the industry has taken and is still taking for many autonomy stacks. All right, so just showing you how this looks like. So in this case, you see bird's eye view here, you see projected into the camera space as well, right? And then you see this is multi-class, right? And one thing to note here is that, well, the sensors are not going to be perfect. There is, in this case, heavy rain, so there is all sort of, artifacts, right? Like fog, etc. in the sensor. And, you have to handle all these things. And then you have to have a single method that actually works across all these weather conditions. You can't just be switching networks or things like that. Okay, so in this case, I'm showing you, different cities across North America, as well as different kind of weather conditions, etc. Okay, and this also works at night. It's not just during the day. Cool. So very easily you can fuse this information in a way that makes sense. And again, the power of learning is something that for many years was misunderstood in this industry. Cool. So now we're going to go one step forward, and right, we have detections, right? We have regressions into the future, trajectories for motion forecasting. And on top of this, now we're going to reason about intentions, which is actually important for motion planning. It's like, what is the intention into the future of all these different actors? Okay, are they going to change lanes? Are they going to cut in front of me? Are they going to take, a right at the next intersection? So that's what we're going to do. And the other change that we're going to do is we're also going to incorporate maps in our network. Okay, and in particular, you can choose your favorite architecture. Something that works well is to process a little bit the maps, which are actually, you can use rasterizations, or you can use graph-based representations, which we also have done some work on this that actually works pretty well, and it's more efficient. But anyways, for simplicity, you can use raster map. And then you can fuse the information and basically treat this as a multitask problem where you detect, you regress, and then you get the intentions. All right, so how does this work? So I want you to focus on the bottom part of the video where different colors represent different intentions. The more yellow it is, the more the probability of continuous straight, the more red, the higher the probability of stopping, and the more purple, the higher the probability of being parked. Note that the stopping and park look very similar. However, as a self-driving vehicle, we will actually do different things depending on which one of the two we see in front of us. Right. The other thing is that the arrows in this video represent our probability of turning, as well as our probability of changing lanes, okay, or continuous straight. So you see here, this is the sort of a representation. Is you get multimodality for free if you do this, right? Because you have intentions. For every intention, you can predict a trajectory or a set of trajectories, or a probability distribution of the trajectories. Cool. All right. So now the other thing to take into account is that when you think about the intentions, actually humans oftentimes want to tell us their intention, right? And the way that we do this is with turn signals. So in this case, you can use a network or a part of the network here, right? You can build it on your architecture where it's going to take spatiotemporal volume around every one of the detected objects. and it's going to estimate which of the turn signal is on, which is the arrows that you see down here. Okay, in this case, the right turn signal is on, and therefore we expect, for example, with high probability a right turn, right? And here the supervision that is given to the network in order to learn this is just a few examples of which turn signal is on. We don't tell the network what a turn signal is and what it is in the vehicle, okay? But it's learning, as you see here, it's putting attention towards the things where potentially turn signals could be, and it learns this in a weakly supervised fashion. Okay. And again, very interpretable what the network is doing. All right, cool. So now we're gonna go and turn our attention to try to get this system right to be much more sophisticated in terms of the motion forecasting. And in particular, let's talk for a second about what are the difficulties of motion forecasting in dynamic or highly dynamic environments. Well, first, one of the problems or difficulties is the fact that you don't really know, for many of the actors, where they are intending to go, for example. Right? For example, you see this actor that is arriving towards an intersection, maybe it doesn't have the turn signal on, and then it could continue straight, or it could take a right. Right? And oftentimes, humans don't have their turn signal on even when they turn. Right? So this is the reason why we need to model multimodal distributions, right? Because if you only model one mode and it's the wrong mode, you might end up in a collision, and that's very, very dangerous. The other thing to take into account is like, the different drivers, right, or actors, they are not just acting in isolation, right? There is a lot of interactions between the different actors or agents in the scene, right? For example, if you have a situation where this vehicle is intended to go there, this other vehicle is intended to go here, depending, for example, of whether this guy is going fast or not, then this person is gonna wait to do the turn or not, right? So there is these complex interactions. And on top of this, in order to deal with safety critical situations, you need to do this complex inference super, super fast, right? At a fraction of a second. So you can't have, super sophisticated process for inference that take hours to give you a sample, right? You need to do something that is real time, right? So this is why this task is actually extremely complex. So in terms of what, we've seen a lot of approaches in the past couple of years really is looking at, can we model the marginal distribution of the trajectory of every one of these actors? And there is like different representations that have been used, whether it's with mixtures of Gaussians, like multipath is an example, whether it is with things like occupancy grids, which is something that we actually like quite a bit, particularly for pedestrians, which are non-parametric representations. We can also have non-parametric in terms of trajectories. So for every actor, you have a set of trajectories, and then you score those trajectories, gives you a nice probability distribution. Or you can use things like autoregressive models, right? That you can sample from them and then get many possible futures. Now but the problem with these marginal distributions is the following: is that if you just use marginal distributions, right, you're not really going to understand that there is, within the cross product of all the things that might happen, some of them are feasible, some of them are not, right? So if, let's say that I sample from the marginal of this vehicle and I get like two behaviors, I get two samples. I sample from this other vehicle, I get two other behaviors. Right, and now the self-driving vehicle needs to make a decision based on these samples, but it doesn't really understand how this, are these things happening? Do I have like 4 possibilities here, or how many possibilities do I have? Right? Are they all, equally probable, etc. So, but if you think about, what happens here, right, is that there is really like 2 futures that are more likely than others. For example, if these 2 vehicles are slowing down for us, then my action should be to continue driving. If one of these vehicles is going to actually enter the intersection, I probably want to slow down, right? And so these are only a subset of the things happen, and within these possibilities, and my actions as a self-driving vehicle are conditioned on those possibilities. All right, so next we're gonna look at how we can have a model that is not gonna produce marginal distributions. Instead, it's gonna produce samples of the joint distribution of the entire scene. One sample is the entire scene trajectories into the future, okay? Instead of one sample being for one vehicle a trajectory, as we had before with the marginals. All right, so how can we do this? So the idea is that, again, we have our input representation, voxel, rasters, images, whatever you want, right? We are gonna create this intermediate representation, and now we're gonna have a bit more sophisticated detector. It's gonna be two-stage, where basically we're gonna detect, and basically we're gonna have rotated array pooling to get a representation for every one of the actors, okay, that we detect. Another question is, given this representation for every actor, how can we model the probability distribution, the joint probability of the entire scene? So we're gonna do this, before I go into how we're gonna do this, and remember that we have this real-time inference constraint, and by real-time I mean only a few milliseconds. Okay, so we're gonna do this through a conditional model, conditional latent variable model, which is kind of implicit, okay? Where you can think of this as a conditional VAE on steroids, okay? Where we are gonna encode what's happening in the scene through a graph neural network, which is very amenable to the fact that we have a variable number of actors, right? So through message passing, we're gonna aggregate this information to create our latent distribution, right? And then we are gonna sample from this distribution. And then basically we also have a decoder, which is another graph neural network that's gonna provide us with the trajectory samples. Okay, so let's be more explicit about the sampling process. So we have, as I say, extracted the information for every actor. Then we are gonna encode this information. We're gonna sample from the conditional distribution, condition on the input, right? The data, the map, as well as the later data, right? And then basically every sample, we use the GNN to decode it, and we get one sample, the trajectory, we get trajectories for every single actor in the scene with one sample, okay? So that's the difference with respect to the marginal distributions that we were talking about before. We can sample it over and over, and then we have, different representations of different distributions. All right, so the other thing that is interesting here, so you can, what I'm doing here is I'm moving basically the latent space, in the latent space, and I'm decoding. And in this case, I have two samples, and then basically I'm interpolating in between. And then what you're seeing is that as we move, right, the entire scene moves accordingly and in ways that actually make sense from a traffic perspective. Okay, so it's really capturing this nice joint distribution. And the good thing about this model is that you can train it end to end, and you will train it, with reconstruction laws as well as KL laws, as you will do any conditional VAE, right? And on top of this, we have some loss function as well for object detection. Because remember, this is joint perception and prediction. This is actually a pretty complex kind of neural net. Okay, cool. So how does this work? Actually, it works remarkably well. And here I'm just showing, multiple samples from the model, different colors are different trajectories into the future, and then here are the detection results as well. Okay, so you see that it can handle, very complex kind of scenes. It nicely, understands the map. Is multimodal without you requiring to tell how many modes you have, etc. Cool. So now we have a really complex way to actually model how the world, potentially can evolve in the next few seconds. Now, if you look at, everything that I've said so far, one of the things that you will notice is that, our results are going to be as good as the sensor data that we have as input. Right, and let's look a little bit at typical scenes. So here is this driving vehicle. This is LiDAR view from the top, again bird's eye view. Then we notice that if vehicles are nearby, typically you have a lot of information, so you can detect them well. Typically, you will predict well their behavior. Things are far away. well, there's very little evidence, whether it's in letter or images, so it's going to be pretty tough. But there is more than this, right? There is the fact that there is all these occlusions. And something might be like super close by to you, but however, you might not actually see, right, because of the occlusion. And this is pretty dangerous, right? Because hidden, behind this vehicle might have been a child that is actually gonna maybe run in front of us. And we need to react immediately to this for safety, right? So this makes, the task of self-driving extremely, extremely hard. And the concept of reaction time, extremely, extremely important. Now, if you think of the future, right, where fleets of vehicles are gonna be out there, these self-driving vehicles, one of the things that comes to mind is that, well, if these vehicles are able to communicate what they see, you should be able to see much more, because now you have much more eyes into this scene, right? And as self-driving vehicles get to scale, these vehicles will be everywhere, right? So if you use vehicle-to-vehicle communication, you should be able to actually see much better along basically almost everywhere, if not everywhere, right? So let's build into how we can build a vehicle-to-vehicle communication system. So in this case, we're going to use our simulator to generate data for V2V, okay, because large fleets of vehicles are not yet there. Here is in the 3D scene, in color are different self-driving vehicles, and you can see in non-color the other vehicles that are in the scene that are driven by humans, right? We have a hybrid world, and this is the sensor data that we generate for the different vehicles, okay, that represent where they are in the scene. So we can, have this data in order to kind of learn to do vehicle-to-vehicle communication. Now, if you want to do vehicle-to-vehicle communication, the question is, which information should you transmit? And there is two things that you need to take into account, is that you want to transmit little information so that you don't have a lot of bandwidth requirements, and you don't overwhelm the receiving agent that's going to receive a lot of messages from different vehicles. But at the same time, you want to convey all the information such that every vehicle can actually have much more robust and safe solutions, right? And so it's going to be a trade-off there, and let's look at what possibilities do we have. On one side, you might think that, well, if in order to not lose information, I might just transmit the raw sensor data, right? So this is good in terms of, okay, I preserve all my information, so that's great. But imagine if it was already difficult to do inference in real time when you have your own sensor data. Imagine if now you multiply that by n vehicles that are sending you information. So that's going to be super hard or impossible to do in real time. And furthermore, you need a huge communication bandwidth to do this. So that's not a great solution. An alternative solution is to say, well, let's get every vehicle to do perception and prediction, and then we can communicate the outputs. So this is very compact, very cheap. The problem is that by this point, we have lost almost all information, right? We have these super condensed representations. So we have limited expressiveness, we don't have context. So this is not great either. The alternative is what we propose, which is, why don't we learn in intermediate representations that we're gonna send to the medium so that other vehicles can actually access, in a way that these intermediate representations are highly compressible. So we only need a few bits, but we send all the information necessary. Okay, this is a very powerful thought. And the interesting thing here is that you can think of your fleet as a distributed computing system, where everybody is computing or doing computation with respect to their own sensor data, transmitting bits of information, very small, and then basically fusing that information with respect to every vehicle. Okay, so let's look at this with an illustration. Okay, so we have the sensor data for all the vehicles. This is our own car. Okay, these are other self-driving vehicles in the scene. Each vehicle is going to compute these intermediate representations. Then it's going to send, it's going to compress those intermediate representations and send them right to the air. And then we're going to be able to listen and basically get access to the information of the vehicles that are nearby us. This is not a centralized system, it's a decentralized system. Okay, so only we will hear about things that are nearby. We can then listen get the information, decompress, and in particular, we use a special, especially aware GNN, to basically merge all this information through message passing with our internal representations in order to basically finally predict our perception and prediction. Okay. This is again very powerful. There is very little, an epsilon of more computation that you need, but suddenly you are much more robust. And let me show you how much more robust you are. All right, cool. So what you see here is, as a function of the percentage of vehicles in the scene, you know, how good the perception system is, and in this case is error for the prediction system. Okay, so you see that it grows almost linearly with the number of vehicles, which is fantastic, right? And you see that there is huge improvements in terms of AP, right? If you work on detection, you know that every AP percent is like such a, you know, you need to suffer so much to increase that, right? And you go over many, many months to increase 1%, right? So in this case, just by the fact that you have multiple vehicles in the scene, and without changing anything on your perception and prediction system, apart from the aggregation of the messages, you end up with much better results. All right, so we saw a lot of, you know, we started with joint perception and prediction. We went into different levels of complexity of the actual system, right, by adding more and more sort of reasoning to it. And what we're going to do now is we are going to go all the way end-to-end to motion planning. Okay, today I'm not going to talk about how to incorporate controls. This is something that is easy to do, you can do as well. But I will talk all the way to just motion planning. All right, so how can we do this? I'm going to show two simple versions of this. There is a lot of different neural motion planners that we have done. And there is one particular workshop, the MKL workshop here, MTL, sorry, workshop here at ICCV, where I'm giving, you know, an in-depth description of this, you know, all this neural motion planner work. But yes, in a nutshell, the first version of this that we built was actually pretty easy. Was rooted again on the concept of multitask learning, where given the input data and the raster map, we're going to compute the intermediate representations, and as multitask, we're going to do detection, regression, as well as we are going to compute a non-parametric cost volume in order to do motion planning. Okay, and the way that we use this non-parametric cost volume for planning is the following: is that we're going to sample trajectories. Our trajectory sample only samples physically realizable trajectories. So you have those constraints inherently in the sampler. You can build, you know, a couple of thousand, 10,000 of these samples. And then basically what you do is that in order to evaluate every sample, cost it, you basically index in this cost volume to see what the cost is. Okay, so this cost volume is spatial and temporal. Spatial in terms of, you know, the area around the SDV, and temporal in terms of the planning horizon. Okay, so every layer here is basically t plus 1, t plus 2, t plus 3, etc. All right, so we can basically sample, for every sample, we can index in the cost volume, right? We can add the trajectory values that we get, and then that's the cost of that particular sample, okay, of that particular trajectory. And then we pick the one with the minimum cost. All right, so this is something that, you know, very simple, and actually works very well in practice. And the good thing about this is that you can do end-to-end learning of the entire software stack here, right? You can do it through utilizing max margin for the planner, right? Because we cannot supervise directly the cost volume because we don't know what the answer is. And then we have detection and prediction loss. And basically we just back propagate through the entire thing. Okay, so let's look at how well this works. So what you're seeing here is basically, so the maps, the LiDAR sweeps, our detection results, our motion forecasting results, and in color you see basically, so I'm going to project the three-dimensional cost volume into 2D, and different colors means different points in time in the future. Okay, and I'm only showing the trajectories here that, sorry, the parts of the cost volume that have low cost, okay, where it gives you an impression of the car, what the vehicle is basically thinking. So it can handle, you know, directly multimodal distributions, as you can see. It understands the concept of slowing down, changing lanes to avoid the collision. doing notches or super notches, like in this case, right? So it learns all these complex things from, yes, a few examples. Now, a little bit more about maybe sort of the systems that we built so far, right? And you think of the industry as a whole, the way they typically have or reason about perception is with detection-based methods. And there is something underlyingly problematic about detection-based perception. Okay, let me explain the concept. So imagine we have a self-driving vehicle and we have two actors in the scene. So if things go well, right, we're going to detect the actors, and then we're going to plan a trajectory that takes them into account, and it's a safe trajectory, right? So that's good. Now with detection, what happens is that we only pass to the next stage things that are above a threshold. So there is this cutting, underlying threshold, that if you are below the threshold, then that information will never make it to the next, to the motion forecasting system. Right. So what happens is that, there is chances that maybe this vehicle in front of us is below the threshold. Maybe it's the reflectivity of the paint, maybe it's a weird shape, whatever the reason. Right. So then what happens is that we're going to plan a trajectory that actually is unsafe, right? Because we are going to act as if this thing was not here. And we might, end up in a collision. So this is very dangerous. So we need something else. So what we're going to do next is, instead of doing detection followed by motion forecasting, we're actually going to look at different representations that do not do object detection. Instead, they directly work on this concept of semantic occupancies in the current time step, as well as the planning horizon. Okay, so the next time steps into the future. And they're going to be semantic in the sense that we're going to represent things like type of whether it's a vehicle or not, whether it is, we have a different layer for whether it is bicycle, pedestrian, and you can go with all levels of granularity, whether it's incoming traffic, whether it's dangerous driving, whether it's occluded, etc., etc., etc. Okay, and the way that we actually estimate these occupancies, remember, we have the lidar strips of the past as well as the present. We have the raster map, and we're going to predict the occupancy on the next few seconds so that we can do motion planning. Right? So the way that we do this is with a recurrent net. And in particular, basically, we are going to use our previous estimates to get the estimate for the next time step, etc. And the reason we do this is to try to get consistency across time in these occupancies. All right, now once we have the occupancy, we need to create a motion planner that is able to work with this type of representation. So we're going to use, again, a sample-based motion planner. But in this case, the difference is going to be that, in the first neural motion planner I showed, it was non-parametric, it was a neural net. It didn't have any prior knowledge really encoded into the discussed volume. And instead, they had to learn everything from data. Now, because of safety, we're going to use a combination of learned codes as well as codes that are more handcrafted or where the prior knowledge is injected. Okay. But the planner is very similar in the sense that it's going to be a sample-based planner. So we're going to sample a set of trajectories. In this case, the sampler is going to be more sophisticated. We're going to understand the notion of behavior. So for every type of behavior, we have a whole bunch of samples. And then we're going to cost those samples. In this case, it's a combination of costs that handle things or that model things like we should avoid occupied regions. We should drive comfortably towards our goal. We should follow the route. We should drive in the center of the lane, etc. And again, we cost all the trajectories. Again, the order is 10,000, and then you select the one with the minimum cost. And again, you can train the entire thing end to end, right? Despite the fact that we have, these intermediate representations and these very sophisticated networks. Basically, in this case, we use cost entropy for the semantic occupancy, where the ground truth occupancy comes from the exact same ground truth as we were utilizing for detection-based methods. And we use max margin again for the planner. Okay, and then again, you train end-to-end the entire system. So this actually works really well. It has much less collisions than you will see out there. It imitates very well humans. Is also more comfortable, has less jerk, and it's as good as any other approach in terms of progress. Let me show you some results. So in this case, I'm going to show you in open loop the forecast. So we have the previous frames and the current frame as input, and then we're going to forecast this into the future. And then you're going to see here with different colors, like the different semantics. Okay, so let's go into it. You see that it's multimodal, right? For this vehicle, it could have take a right or continue straight. And these bounding boxes here are just for you to see the ground truth. Okay. But in here is open loop. We are forecasting the next few seconds with the current observations without seeing the future. It actually works very well, and it actually captures very, very fine-grained details. Like, for example, predicts very nicely where these pedestrians are going to be going the next few seconds, and also captures interactions really nicely. For example, it captures that this guy here is going to slow down so that pedestrians can actually cross. All right, but open loop is actually not sufficient in order to really test software stack. We need to go to reactive mode to really execute the plans that our vehicle is planning, to really understand compound of errors and things like this. So we're gonna now utilize our cutting edge simulator in order to test the motion planner in a reactive way. Okay, and the actors are gonna be reactive as well. And basically, we're gonna use our sensor simulation as input. So this is when you start seeing like huge differences with respect to all other approaches, where basically we get much safer plans that are much smoother, and we make more progress. Okay, some of these metrics were more flat in the open loop because it's not really showing issues. Huge differences when you go to closed loop. All right, and very, very quickly, I'm gonna talk maybe 5 minutes about the simulator. Okay, how that is enable us this test, but also, as I mentioned, training. And in order to think about simulation, right, I think it's worth to spend 1 minute to think about, okay, how is simulation used in the industry? There is 2 types of simulation used. There is this thing called log replay, where you just replay the sensor data that you capture. That's not simulation, okay? That's just, just utilizing data that you have captured in the future. When you really go to simulation, where you're actually modifying the world, you look at the simulators in the industry, they actually start with trajectories and bounding boxes, and they typically only test the motion planner. They are not able to test the entire stack. And this is very problematic in 2 ways. First, you're only trying to validate one piece. And second, you're not really validating it because you don't have the noise characteristics and mistakes of the perception and prediction system. So even that thing that you're trying to validate, you can't really do justice into what potential issues are. Now, if you wanna, really be able to test the entire system, what do you need to do? Well, you need to be able to create virtual worlds with appearance, right? You need to be able to create the scenarios at the scale of normal things and safety critical. And then you need to be able to simulate in real time or near real time how the sensors will have observed that scene, such that in reactive mode, you can test your entire stack. There is nothing like this in the industry. And this is what I'm gonna show you now is, a version of our simulator. Now we have, I guess, 2.0 that one day soon I will show you as well. But I'm gonna show you, I guess, the public version that we have shown before of a simulator that actually can really do all these things at once. All right, so in order to do this, we need to capture the assets, right, the world. We need to be able to simulate behaviors and then do sensor sim. Okay, so let's go quickly into how to do this. So in terms of the industry, if we look at current approaches, the way that they build these virtual worlds is going to be typically using artists and using very simple automation through procedural modeling by just copy pasting sort of or modifying some parameters of these artist generated assets. So this doesn't have the diversity of the real world. It's not realistic. Our approach is very different in nature. The idea is that by driving around, you see the world. So if you can reconstruct the world very reliably as we can, then basically you can resimulate things in this world, right? So we can capture the static part of the environment. We can capture the all the dynamics, dynamic actors, like all the vehicles, in a way that we can resimulate them, as well as every single pedestrian you observe. And we can, capture the pedestrians in a way that we can resimulate them to create or do any sort of poses, arbitrary poses, as you are seeing here. Okay, all automatically at the scale. So this is a game changer, right? Artist stuff that doesn't scale, not realistic. Yes, capture the world and then compose it to create new worlds. Then we have like very realistic multi-agent simulators. In the industry, what you will see is very rule-based, very simplistic simulation. Doesn't look like humans, doesn't generalize to the long tail. Instead, what I'm showing you here is one of our multi-agent AI approaches to do this, where we simulate the entire scene at once. Okay. So I'm showing you here, yes, the diversity of types of simulations that we can do. We can generate, billions, trillions of these simulations. Right? It's actually pretty fast to sample from this model. And you see that the behaviors are actually very realistic. You don't see vehicles shooting off the road. And as we go now, I'm going to show you some of the maneuvers that are a bit more rare. You see that it's going to do it in a very naturalistic way, like nudges here, right? U-turns and this kind of thing, it's hard to do with all the long tails. You can't really do it by just scripting, as you will see in the industry. Lane changes, and then you're going to see an unprotected left. All right, so very naturalistic. It's waiting for the other vehicle to pass without us needing to actually script this behavior, right? Just by unrolling the model, you can actually get this for all vehicles. Cool. And the last bit is that then we can actually generate the sensor data, how the sensors will have observed the scene. On the left-hand side, you see our LiDAR simulation for, on the left-hand side, you see the real LiDAR. On the right-hand side, you see our LiDAR simulation for the same scene that we have reconstructed. And then you can see that it looks very similar, but what's more important is that there is really no domain gap. The perception system in green, the output is actually, the same in the real world as in simulation, meaning that, for the autonomy system, right, it behaves in the same way. And this is an absolute game changer for self-driving, because now you can really test in simulation. You don't need to test, by driving dummy miles on the road over and over and over. So you can create, safety critical cases, for example, here. And then in this case, I'm showing how, what the simulation is in terms of the LiDAR. This is the input to the entire software stack. And here we see that we are able to react accordingly and slow down. Okay, so in this case, it's passing the test of somebody that is coming out of occlusion in front of us. All right, and then we can do this at the scale in different geographies with different actors and different behaviors, etc., etc., etc. So this scales so much better. And last bit I want to show is that this is not just about one type of sensor; it's about many sensors, right? So what I'm showing you here is what we call actor injection, which is these are real logs where for every video it's going to be repeated twice. And there is a few of the vehicles that are actually fake, meaning that they weren't there in the first place, and then we are injecting them. And then your task is to try to guess which ones are fake. In many cases, it's actually pretty difficult to say. For example, in this scene, it turns out that this vehicle in front of us and this vehicle on the side are actually fake. So this is in 3D. This understands it has shadows, right? It has like really nice behavioral sort of like how these actors behave, etc. And things that we can do is that we can also generate multiple cameras in the same scene in a way that is consistent, and it's consistent with the LiDAR simulator. Okay, so you can really test the entire stack. All right, and this simulator is really super key to develop self-driving. And in particular, it enabled us to not need to, drive all these millions, billions, whatever of miles in the real world. Instead, we can do this in the simulator, which is much safer, and you can really control what the vehicle observes, such that it can really learn much more efficiently. All right, so just to conclude, right, the promise of self-driving is really the promise of a better world. There is so much benefits of this technology, from saving lives to, create greener spaces for our cities, to really, solve some of the supply chain issues that we see right now with the shortage of drivers, for example, for long-haul trucks. And if you are excited about really changing the world, come join us, visit our jobs webpage, where we have plenty of openings, and we look forward to be creating this amazing technology with you. This is all for me today. Thank you.
So our next speaker is Ehsan Adeli. Ehsan is an assistant professor at Stanford University and scientist at Stanford AI Lab and Standard Vision and Learning. The title of his talk is Forecasting Human Dynamics in the Multiple Levels of Abstraction. The floor is yours, Ehsan. Please feel free to share your screen and go ahead.
Thank you. You should be able to see my screen, right?
Perfect.
I optimized for video. If by any chance the quality is not good, please let me know, because when you optimize for video, sometimes it drops the resolution. So yes, I'm very happy to be here today. I'm going to talk with you about some of our recent works around the topic of anticipating the future, forecasting dynamics, human dynamics in different levels of abstraction. Autonomous agents perceive the world around them and take actions. Reasoning over visual data is a desirable capability for them that enables them to forecast the next events or actions in the video. Observing the past, it's very important and crucial for them to anticipate what's going to happen in the future for safe and smooth navigation. Anticipating the future is a simple yet useful piece of information that helps the agents decide what action to take before it is late. One way to anticipate the future is to directly predict the pixel values of future frames. However, this is costly and often inefficient, we all know. This type of visual forecasting defines the lowest level of abstraction in this abstraction hierarchy that we are creating. One of the interesting aspects to learn about is forecasting the future semantics and dynamics between different entities in the scene. This can be achieved if we predict the scene semantic segmentation by observing the past video, defining a second level of abstraction. Although forecasting the scene dynamics and semantics can provide the agents with detailed configuration of the scene formation in the future, in some cases to make decisions, precise trajectory or body part movements are of greater importance. Therefore, prediction of individual trajectories and detailed movements of the body, often referred to as the body pose, are of interest. Detailed trajectory and pose characterize a higher level of abstraction than the previous two in the hierarchical structure that we created. A higher level of abstraction would be predicting the future actions. For example, in this case, intention of the pedestrian, if they want to cross the street or not. This inference can be performed for all of the pedestrians in the scene. And therefore, actions or intentions designate the highest level in our abstraction hierarchy. So we have done a lot of investigation in each of these four levels. We've published papers in each of those. As I mentioned earlier, in a couple of papers, we propose forecasting visual content in the pixel level, but I'm going to skip this one here since it may be of not of a great interest these days, and publications are rather old. One of our recent works was investigating the problem of semantic segmentation, segmenting the future, forecasting the semantic segments. So by
yes, sorry to interrupt. So your screen, it's very blurred, and
yeah,
the text is hardly readable.
Let me then
notify.
Yes, yeah, sometimes when I do share the screen with video optimization, this happens. So let me share. Better?
Yeah, it's great. Perfect.
Yes. Okay. Yes. Yeah, I just removed the video optimization. So by observing only the past RGB frames, we want to output the future scene semantics, semantic segmentation in the future. We implemented this idea by using a student network with three main components: past encoder, 3D convolutional forecasting module, and future decoder. We used supervised forecasting loss to train the, the model. However, our model's capabilities were augmented by what's happening? Yes, by a teacher network. Sorry, the animations are very slow on the computer now. So our model's capabilities are were augmented by a teacher network, which used the distillation loss. This teacher network had access to the future frames. We compared our results with several baseline methods, such as zero motion, optical flow, a two-stage method that first predicted future RGB frame, then segmented it, and the Carnival STM previously published baseline. Our model outperformed all of the models using mean intersection over union evaluation metric on the cityscapes dataset for short-term, mid-term, and long-term predictions. So some qualitative results. In this sequence, the rider and the bike are moving to the right, and there is one car behind them moving to the left. Our model is able to correctly predict their future positions and generates better boundaries, as can be seen here. One interesting observation here is that because this was a 2D model, 2D segmentation model, in the past, the car and the bike, they had separate, they were in separate locations. And now that they're cross-passing from the camera's viewpoint, since our model didn't have the information, the depth information, it was confused which one is in front of the other one. But the good thing is that it was able to predict the motion properly. So in this next sequence, the ego car is moving forward. Our model is able to predict the relative motion and future positions of the parked cars and generate better boundaries here. In this next sequence, which was for long-term forecasting, some of the pedestrians are moving left and the others are moving rightward. Our model correctly identified and predicted the moving direction of each individual pedestrian, as you can see again in this result. So next for trajectory and pose forecasting, we've completed several works published recently. Let me start with the topic of trajectory forecasting. Given a past trajectory, the goal is to predict the future trajectory and movements of the individual, the person, the pedestrian in this case. In recent works, in a recent work, we proposed trajectory prediction method conditioned on the person's goal. Prior work tackling this task use an autoregressive ordering on the future time points. In other words, the joint distribution over the future steps is modeled by first predicting the first future point given the past, then predicting the next point given the past and the predicted first future point, and so on until the end point of the trajectory. But we know that pedestrians are not passive, but goal-oriented agents. They have a goal in mind and a particular direction that they are following. They will be following, which will show their will. Hence, we proposed a model to consider this human prior while past planning. This also motivated our title of the paper. It's not the journey, but the destination. Specifically, we proposed modeling the joint distribution by first modeling the endpoint distribution of each person independently, sampling from this distribution separately for each pedestrian yields endpoints for all pedestrians in the scene. And finally, we predict all their future trajectories jointly by conditioning both on the past and the sampled endpoints. Our method provides rich multimodal prediction that also respects social constraints. We proposed a method called Predicted Endpoint Condition Network, or a PECNet. During training, the past trajectory information is encoded using a past encoder. The ground truth trajectory endpoints are also encoded with an encoder, an endpoint encoder. And the outputs of these two are concatenated with each other to be used in the subsequent conditional VAE. The concatenated embeddings are then mapped into parameters for the latent space. A latent space representation is then sampled from the parameterized distribution and decoded into potential guesses for the future endpoint. With these predicted endpoints, then they are re-encoded, forming the predicted destination or endpoint encoding. Concatenated with the obtained past trajectory embeddings, they are used as inputs to our novel social pooling module. The proposed attention-based pooling operation with a pre-computed social mask and learnable neighborhood weights effectively merges the context across social neighbors. Finally, these embeddings are then jointly decoded with the future prediction module to predict multimodal future trajectories compliant with both the observed past trajectory and social norms. During inference, however, since we do have access to future, do not have access to future endpoint paths denoted by the dashed line during the training, what we do is we specifically use the trained latent space here. In the first step, only the past trajectory information is encoded, which forms the conditional information for decoding the sampled latent code in the CVAE. This procedure produces multimodal guesses for future endpoints, which then proceeds through the network identically as in the training phase. The lower part is completely identical to the training phase. We measure the performance using widely used metrics in the literature. Average displacement error, or ADE, is defined as the average L2 error between predicted points and the ground truth future points for a given past trajectory. Similarly, final displacement error, or FDE, is defined as the L2 error in the last predicted point or the end point with respect to the ground truth. With these metrics, we benchmark PECNet's performance on the well-studied Stanford drone dataset, given a sequence of 8 frames or 3.2 seconds long. We aim to predict the pedestrian's position for the future 4.8 seconds or the next 12 frames. We compare against several competitive baselines such as Social GAN and SOFI. We also compared against the previous state of the art established by conditional flow VAE. Further, we also compared against some concurrent works published in the same conference, P2, TIRL, and SIMARC. These two methods, which were co-published with our paper in ICCV 2020. Our reported results are using 20 samples per trajectory, as is widely used in the prior work as well. Under standardized evaluation protocol, PECnet achieves an ADE error of, as you can see, 9.96 and FDE of 1588, which improves upon the previous state of the art by a significant margin. We also compared PECnet's performance on the widely used ETH-UCY benchmark. We follow the Live1 scene out evaluation protocol on this benchmark, training on the rest of the 4 scenes and testing on the 5th. We compare against several published well-performing baselines, such as Social GAN, SOFI, and CGNS. Again, we find that PECnet improves upon the state-of-the-art performance by a very large margin. Here we see some qualitative results demonstrating PECnet's rich multimodal predictions. White denotes the past input trajectory, blue represents the ground truth future, and red, the red dots are PECnet's predictions. We also visualize PECnet's behavior in case of common pedestrian social interaction modes, such as merging and cutting through. We show that the best single predicted trajectory in the middle, as well as the multimodal prediction for each pedestrian in the last column. So, however, to predict the future movements, human movements, with more details, to extend these works, we need to do detailed human pose forecasting, predicting the future skeleton and pose movements. Traditionally, this problem of pose forecasting is defined by discarding the global motion and predicting only local joint movements. As you can see here, this is how it was defined in the past. Specifically, given the past pose sequence as the input, you would like to forecast the future pose sequence. This task can be used in several applications such as robotics, healthcare, autonomous driving vehicles, and so on. In an early work, what we did was inspired by hierarchical structures and multi-scale nature of human motion. We presented a model called triangular prism RNN, or TPRNN, hierarchical multi-scale RNN. The first level of the RNN with the green color in the diagram, as you can see, takes the velocity sequences as the input. As you see, it's just the residuals, the velocity of the joint values. As the input, the second level of the RNN has two channels with the orange color. Each channel connects to either the even or odd steps, as you can see here, of the first level. Finally, we use the most recent hidden state and two-layer neural network, as shown in the red color here, to forecast the future velocities, future movements. So the model sort of creates a triangular prism, and that's why we called it this way. As we go up in the hierarchy, more parallel RNN sequences are incorporated, could be incorporated. Parallel multi-phase LSTMs in the same level share the same weights used for some sort of data augmentation as well. So these are the characteristics of this model. As you can see, the hierarchical, multi-scale, somehow multi-phase data augmentation, and we are working in the velocity space. Experiments on human 3.6 data set revealed each of these four components characterize a good have good contribution to lowering the mean angular error of the pose prediction. So the metric that we use was MAE. The lower is better. Compared to the previous work, this residual Martinez 2017, as you can see in this model, in this figure, our model outperforms by a significant margin. Besides, we can also see that the performance gains between our model and the previous work become more significant in the longer term evaluations, as you can see here. Here we show some qualitative results in synchronized animation. The ground truth and the input poses are in purple, as you can see here. And our models predicted future poses are all in red. We can see that our results have a very smooth transition from the past to predicted future, and our results are very close to the ground truths as outlined here. Although this previous work that I presented, this early work that we've done, resulted in good performance, it needed a fully supervised setting for training and possibly not enough generalizable to challenging cases. Therefore, we redesigned the method based on imitation learning algorithms to train the post-prediction model. In this work, we call it an agent, post-prediction agent under reinforcement learning formulation instead of simple supervised learning. The goal here is to model, to learn, and generate the expert demonstration given the input state, which is the past sequence of poses as seen here. In RL and imitation learning terminology, it means that we generate an action that imitates the expert's behavior. This is done by using a policy generator to make sure these actions are in line with an expert behavior. We use a critic network similar to discriminator used in GANs to generate a reward if action is in line with the expert behavior. This is done by policy gradient. We used behavioral cloning to initialize the policy generator network, and then we use Yale or generative adversarial imitation learning to train the whole system. This model, like the previous work, we tested it on the human 3.6 data set with 3D human poses performing different types of actions. As can be seen in this table, our imitation learning model outperforms all other supervised methods, including our previous work, TP, RNN. On average, for all different action categories on this data set, our method predicted most accurate fine pose movements in both short-term and long-term predictions. So I talked about two works so far. As I said earlier, previous works of post forecasting often ignore the global motion, and this was the case for the first two works that I presented. They remove the global motion from the joint coordinates and define the problem to only predict the joint coordinates in the local space. In a set of follow-up works, what we did was predicting the coordinates in the global space, which means it can infer both local and global motion components simultaneously. Defining this new task, which we initially called it pedestrian locomotion forecasting. Locomotion being defined as overall motion of the body in space and time, a work published in VACRI 2020. So what we did here was, starting with raw data, we first built a post-completion framework that gets the incomplete poses out of any off-the-shelf model. We used OpenPose here to get the incomplete poses. Then our pose, this was the pose estimation model. Then we developed a post-completion model to denoise and complete the incomplete poses that were output of the off-the-shelf model. Then the movements were disentangled to global and local components, which were forecasted into the future, the core to our algorithm was here a prediction module that operates both in local and global subproblems. And then these information and predictions were merged to create this merged forecasted locomotion. As I said, the core to this method was this forecasting module, which was simply defined by using an encoder of the past, encoding of the past, then forecasting in the latent space, and then decoding the future image, both in global and local components separately. How we implemented this was based on, as I briefly mentioned earlier, sequence encoder and sequence decoders, and then this quasi-RNN forecasting module that we implemented for forecasting in the latent space. We use this for doing the predictions in the global, just the predictions of the trajectory, and also local movements of the body joints as shown here. The evaluation was again based on an error metric. This time we used key point displacement error, and the reason we use this one instead of angles is now the evaluation is in pixel space, so we used a metric, an error metric in the pixel space. The results showed that our model performs best compared to other naive baselines like constant velocity and learning-based baselines using more basic implementations. So although in this work we predicted the poses in the global coordinates, there were several caveats to this work. So one of them was that this work somehow ignored context. These previous works ignored context. For example, just to give you an understanding of why it is important, given the current sequence of poses, as you can see here, without context, the system may think that the person is walking and therefore predict the future like this. While in a system that observes the context, as shown here, it is possible to infer that the person is actually punching, is going to punch a piece of information that can help better predict person's future pose. In addition, the prior work often ignored social forces and interactions among humans in the scene. Before this work, it's better to clarify that most of the social methods were only used for single point trajectory forecasting and not very much in post forecasting space. Specifically in the post forecasting, it's important. For example, with this example, if we consider the social forces, the thing is that with the knowledge of the second person and their movements, it becomes more apparent that this person is actually most probably going to be defending instead of punching. Therefore, we can predict and create a better prediction of the future movements and pose. So therefore, we took these challenges and defined new methods. We published a work in IRIS 2020 and examined methods that use context and social cues. And for that, I'm going to start with this one. Our model, the IRIS 2020 model had 4 main modules of encoder: social pooling, spatial temporal context encoding and decoder. The encoder module used the GRU sequence-to-sequence scheme to encode the historical sequence of poses for each individual in the scene. Social pooling module was a simple social pooling shared socially aware feature network by pooling features across embeddings. And we had a spatial temporal context encoding module that used an I3D model to extract spatial temporal features from the videos, which were then passed through a multi-layer perceptron neural network to create the shared context features. And finally, for each person present in the scene, a feature vector was built by putting together the feature specific to that person. The social features and the context features, all of them were concatenated. The decoder module then received the concatenated person-specific embedding, shared social and context features to predict the future poses of each single individual. The network was trained with a loss function that we defined this way that calculated prediction error in the global space. We evaluated the method on 2 data sets. First, we reported results on the post-track data set, which is a challenging multi-person data set. In this data set, complex activities happen in each video. The data set is annotated with 2D poses of each person in the image coordinates. Additionally, the second data set in this work, the NTU RGBD data set, we used videos that had 2 persons in the scene performing 11 different actions. The data set included 3D annotations of the body pose and all in a 3D word coordinate. For evaluations, we used the mean square error metric, which calculated the difference between the predicted and the ground truth coordinates in the global space. We sum these error calculations over all persons in the scene. So we compared our method with several baselines and prior state-of-the-art methods. Since prior work separated the local and global trajectory predictions, our baseline consisted of 2 components. The first component was defined by local forecasting methods, and the second one by global or trajectory prediction methods. The first set of methods included simple baselines that do not involve learning, such as zero or constant motion, which have shown very competitive results compared to even learning-based methods. Then we show some models that only do learning in the local space. And finally, all of the methods that are doing joint learning, our model and its ablated components, ablated versions. So as can be seen, our results are best compared to the other methods. Let's look at some qualitative results. As you can see, our results that does joint, our method that does joint learning performs much better than doing local pose and global trajectory predictions separately and then merged. Both of these are competitive state-of-the-art models for themselves at the time of the publication. So a second example also shows similar type of results in terms of performance. We see a similar misprediction trend with the predictions of baseline, the baseline method, as you can see here, while our joint learning method produces results similar to the ground truth. Continuing this direction in a follow-up work, we moved one step further by modeling different human-human interactions, human object interactions at different levels over time. Using graph attentional networks between human and humans and human and objects. Not only this, we also propose to continue modeling the interactions in the future, something mainly ignored by the prior work. Lastly, due to partial or full occlusion, or even individuals exiting the scene, the body joints may be invisible in some frames, which can deteriorate training process. So we propose a training scheme and evaluation metric aware of invisible joints. So for that, we developed a model, specifically the pose location vectors are put together, encoded by graphs and attention calculated over them. Then they are fed into a recurrent network encoding the movements over time. We then form attention graph between the humans. In parallel, an object branch extracts features for the objects present in the scene, and this enables us to model human to object interactions with another attention graph, as can be seen here. This process yields feature vectors for all individuals, encoding their social interactions and interactions with objects as well. We concatenate these with object features and use them to decode future movements. And yes, the future, the movements in the future, we consider interactions between humans and humans as an important factor for forecasting as well. So this work, we actually defined, out of this work, we defined a benchmark with two metrics, the visibility ignored metric, VIM, which was the simple error metric used in previous works too, and another metric, visibility aware metric, which was actually inspired by a set distance. It penalizes false predicted invisible joints. This was also run on 2 data sets, but this time we used the more challenging 3D PW data set with 3D poses and 3D world coordinates of daily life activities, and 2 persons in the scene in almost all cases. We also included post-track, multiple persons. It involves complex activities and 2D poses, as I discussed earlier too. As can be seen in this slide, the results of tripod, our method, are significantly lower in terms of error compared to all of the previous works, including our own previous paper, the IRIS paper I just talked about. This is also a similar type of results on the post-track data set, obtaining the best results compared to all of the methods. You see the significant differences. Some qualitative results out of this work, as you can see, for example, this example, the interaction between the human and object defines the future movements, and it is best captured by our method, while other methods, even they are using context and social features, since they don't have interaction with objects, the results are not the best, as you can see here. Similarly, when there is invisible joints, the other methods often create random outputs, adding to the complications in training, while our method is able to ignore those parts, those joints that are not visible. Some qualitative results, very much similar to the previous work. Again, as you can see, this is our own previous work, not including the interactions in the attention graphs. And this is the other work that does the disjoint training. And as you can see, again, our results are better than the others, not completely same as the ground truths, but capture movements in a better way. Similar type of results for the cases that we have here. We are showing, sorry, here, same type of comparison with the previous method without considering the interactions and the disjoint learning framework. So with this new type of analysis, we actually defined a benchmark, the social motion forecasting benchmark, which this is the address, home of the Stanford .edu. You can submit. We also organized the workshop, which finished just in the morning today. You can still submit your results if you're interested. You can go online and train your models and submit results and see the live leaderboard. With that, I would like to go to the last part of this work, which is basically this intent and action prediction part work. So first, in this work, which we built a spatiotemporal reasoning pipeline for intent prediction. First, a scene parsing component using instance segmentation of scene elements was used to delineate the objects that may influence the pedestrian's intent. When a pedestrian is observed, our model starts reasoning about the intent by building graphs around the pedestrian. We build one graph for each time point and connect corresponding nodes across time. And finally, our model predicts the intention as defined by future crossing or not crossing the street probability. So with this model and this modeling that we used here, we were able to obtain very good results on this dataset, joint attention autonomous driving dataset, JAD dataset. We first tested our algorithm on these dataset quantitatively and compared with several methods. Here are the results. These are our results in comparison with methods that were based on only trajectory forecasting, methods that were based on past and future pose, and methods that were based on action anticipation and early prediction of actions. Again, our spatiotemporal reasoning framework outperforms all methods by a large margin, as it obtains an accuracy of nearly 80% for predicting 1 second into the future. When we widen the prediction time horizon as expected, the accuracy drops. Here, the results of a prediction up to 3 seconds into the future are shown here. As you can see, 3 seconds into the future. As examples of qualitative results, by observing this past Our algorithm predicts if the pedestrian has the intention of crossing the street or not in the next like 30 frames or 1 second, for which the answer is yes here. For this example, our algorithm predicts that these pedestrians do not intend to cross the street. Probably they are waiting for the car to pass first. Some more interesting results. Here are some more qualitative results. The cyan color is the observation, as you can see, and then green and red mean cross and no cross intention. Interesting part is this, these pedestrians that are coming from the right side, first, the algorithm thinks that they are not going to cross the street, but as they get closer to the curb, the algorithm changes the bounding box color for them to green, showing that they are actually having the intention of crossing the street, which was an interesting result. We further developed a data set for this task, the Stanford TRI intent prediction data set. In addition to the novel method that we presented in this work, we released this data set, which you can go online and now request access to it. Our data set included over 900 minutes of video. There are over 1 million annotated frames in the data set with over 350,000 manually annotated pedestrians in instances and at 2 frames per second, which were then interpolated to 20 frames per second. Our data set has videos recorded for recording of 3 cameras, left, front, and right cameras in the vehicle. And finally, the data set was collected in 5 dense cities in the United States. We performed some experiments on this data set. We ran our method on the Steve data set, results with different input output settings and lengths, as you can see here, are shown for cases that we use 1 or all 3 cameras. So as the colors indicate, using 1 camera, red, and this dark gray, using all 3 cameras for building that graph. So as expected, when we are using all 3 cameras, we are getting better results. And interestingly, predicting even up to 3 seconds into the future, results are relatively still good because we have a wider angle of the view. I talked about many different aspects of visual forecasting in general. Visual forecasting of behaviors at multiple levels of abstraction in dynamic, realistic environment helps make quicker navigational decisions, as we discussed throughout the talk. This requires reasoning over the scene involving all of its components at different levels of abstraction, as we've talked about them today. So at the end, I would like to thank all my collaborators and mentors at Stanford and other institutes, and would like to thank the institutes and different entities that supported my research. Thank you very much. And if there's any question, I would be happy to answer.
Yes, Ehsan, thanks for a great talk. It was kind of a lot of interesting topics that you covered. So like I was curious to understand that that the pose estimation, or like the forecasting of the pose, how does it transfer well to forecasting the different kind of scenes in video understanding? So it's like the pose estimation has the pose of human body, right? And then that is still problem statement from a direction of it still is an easier problem in context to the overall flow of next frames or next things. So these algorithms that you spoke about, how generalized they are, or have you tested those things?
Good. I think it's a very good question. Basically, the thing is, actually, before I completely answer the question, in one of the works I've shown that we start with the image. So we take the image as inputs, we run some off-the-shelf model, we tested open pose and a dense pose to extract the pose and then do the predictions for each individual separately. So yes, when you have in cases in these benchmarks and data sets, you often have the past prediction of the past estimation of the body pose, the ground truths, and all of these works in the pose forecasting space. They use the ground truth pose as the input. As I said, we have tested extracting the pose information automatically from off-the-shelf models and then train a denoiser and post-completion model on top of it to be able to actually plug the system into any usable any video system. So this work was actually sponsored partly by Toyota Research Institute, and we are right now at the stage that we are discussing with them to implement these in real scenarios, for real scenarios in terms of either prediction of trajectories or intentions from images themselves, from videos, not necessarily only depending on the pose data. But you're right, most of the works are assuming that the poses are given, which poses another challenge to this problem.
Yeah, I also had one more question in this direction. So often I have read some recent papers that I have myself done some forecasting. So, but we have done like 2-3 frames, you know. But if you try to forecast like 5 frames ahead or 10 frames ahead or 15 or 20, 30 frames ahead, how well this pose estimation based forecasting works out? Is it, how do you have, can you share your thoughts on this?
Right. That's so specifically your question is about like poses, right? Not actually predicting the frames, because that's a different.
Like.
What's that?
You can touch both if you like.
Yeah. So those are actually different problems, because predicting the future frames, the pixel values, we always have problems, and we struggle to see why this could be useful, because you need some semantic information about the future. You don't actually need the frames themselves to, unless you want to do video authoring, for example, or video generation creation. So that's a different thing. It's for graphics people. But in computer vision applications, what happens is we often need to understand and know what's happening in the scene. That's why we went from the lowest level of hierarchy to like higher levels of abstraction, like scene semantics. We can actually do maybe a pose and trajectory, or even action anticipation and intention prediction. So basically with that motivation, we didn't go very much into the frame prediction field, and actually I skipped it from this presentation too. But in terms of post prediction, the experiments show that, and it's actually obvious that if the movements are sudden and non-predictive, then it's going to be itself very challenging to predict a longer term in the future. What we have done and used in these works are mainly data sets that are on predefined and well-defined actions, not 3D PWM and post-track, like not the later works. But to begin with, these types of post-forecasting models, they were run in, for example, Human 3.6, which has like 10, 12, 15 activities defined. And those activities are basically somehow predictive. If you're walking, or if you're like, for example, doing discussion, it's more of like one single activity that when you see part of it, you can probably predict the future. But in terms of the results, as you also saw in the plots that I've made, as you go longer into the future, the prediction, the errors become much larger, the performance drops significantly. And that is why, one reason is because we always want to predict one single future for the future. All of these methods are like deterministic. This is the output for like five seconds from now, or for like 5 frames from now, 10 frames from now. The one solution is to go to multimodality and trying to understand the future probability distributions, how this person may move, which will consider like different types of moves and movements that can happen in the future. We've done some works for the trajectory forecasting work in terms of multimodality and trying to understand the future in multiple probability distributions, but not very much in post forecasting. But that's one solution that I see that can probably help with decreasing the future errors as you go longer into the horizon, into the future.
Yeah, indeed. It's I have seen, so it's in pose, I can certainly believe that there might be intrinsic ambiguity, so that if you're moving forward or you are moving backward, how you decide that, right? So just from the distribution that you have, or the distribution from where your samples are drawn, and what kind of distribution you have seen is what you can predict. You cannot really cover in the wild like situation, right?
Exactly. That's right. That's right.
Okay, cool. So thanks once again for your talk. Now we can move on with the next speaker. So guys, our next speaker is Xiaolong Wang. Xiaolong was unable to take this call in person, but has sent us a pre-recorded talk. Xiaolong is a assistant professor at UC San Diego. The title of his talk is Learning to Perceive Videos for Embodiment. Now I can share the screen and we can go on from there.
Hello, this is Xiaolong. I am an assistant professor from UC San Diego. Today, I'm going to talk about our work on learning to perceive videos for embodiment. So let's take a look at this video. Both the baby and the dog observe and act in a dynamic environment. The baby observes the ball and takes it to the dog, and the dog observes what the baby does and responds back. Our goal here is to also enable embodied agents to observe dynamic visual world and learn to act accordingly. The key problem for perception in here is how to deal and react with a stream of input data that forms a video. If we see what has been done in the research in videos so far, a very popular topic is on action recognition. So given the video, we learned a representation to say this is jumping, this is drinking, and so on. To do so, researchers have labeled hundreds of thousands of videos. However, representing a video with a single label is wasting away a lot of information. Instead of relying on human labels, a Lockwood also studied how to leverage the space-time information as self-supervision for learning visual representations. Specifically, a lot of efforts have been done on studying contrasting learning with videos. We have our own work back in 2015, and there are lots of recent works on learning representation invariant to time changes. So given all these great self-supervised representations, what are they useful for embodied agents? As the agent or the robot interacts with the environment, it needs good and adaptable visual representation to observe the world. Self-supervised signals can be a good fit for this, since as the agent is moving, it keeps collecting new data, and this new data can be used for learning since we do not need any human labels. And the representation can be updated and adapted to new environments continuously. We will show some examples on how self-supervised learning can help reinforcement learning agents to generalize to new environments. Of course, if we only perform robot learning with reinforcement learning, it will be very inefficient. A more efficient way to perform learning is to use imitation learning from human videos. So how to extract useful information from the videos for imitation learning? A lot of efforts have been made on extracting the 3D structure of humans and 3D interactions from the videos. And there are also efforts on estimating 6D object pose and 3D hand poses from videos. However, most of this work is still focusing on in the lab environment, and a lot of videos are actually not doing a real task. They are just some data on moving the object randomly in different views so we can collect data in multi-view. So laterally, we have not seen so far yet how these videos can help robots to learn. So to improve the learning efficiency, we can perform imitation learning. And if we can extract the 3D structure from the videos, then we can generate very useful 3D demonstrations for imitation learning. And if we can generalize the 3D estimation in the wild videos, it can help scale up the demonstration data. But interestingly, there's no such a benchmark that bridges the 3D estimation to imitation learning for robotics manipulation tasks. In computer vision, we are still optimizing the millimeters for pose estimation, and it is not clear how useful the metric is and what it is useful for. So instead, we could have used how it helps imitation learning as a benchmark for pose estimation. So in this talk, there will basically be two parts. In the first part, I will talk about our recent efforts on contrasted learning and learning 3D information from videos, and then how this temporal self-supervision can be used together with reinforcement learning agents to improve its generalization power. We apply on robot manipulation tasks and also vision-guided local motion control task. In the second part, I will talk about our work on generalizing hand object pose estimation. And then I will introduce a new benchmark DEX-MV, which stands for dexterous manipulation from videos. We try to bring the 3D estimation on hand and objects to help robots to learn. So I will start with the first part. I will specifically talk about 4 papers, 2 on the vision side and 2 on the robotics side. The first problem we want to tackle in here is to learn space-time correspondence for tracking. We have a previous work on learning to track objects using the cycle consistency of time, which is a self-supervised task tracking object backward and forward in time and find the consistency between. This work is also recently extended with contrasted learning. So the interesting thing about contrasted learning is that by just learning invariant features across different transformation of the same object instance, it can get good representation for recognition and semantic tasks. So our hypothesis is that if the high-level representation is good enough for recognition, it requires the convolution features to find correspondence between similar objects or parts to support the recognition. So do we actually need to decide tracking task, the cycle consistency task, to learn correspondence? or we can actually learn correspondence by just comparing images. So in this work, I would like to introduce video frame level similarity learning. This is work done by my PhD student Xiaolong, where we applied contrastive learning on video frames. So here's an animation of comparing two video frames. In our method, given two frames as input, we forward them to a Siamese legwork. We only extract the fully connected layer feature in the end of the legwork and perform contrastive learning or similarity learning with these fully connected layer features. By just doing so, the correspondence automatically emerge in the convolutional layers. All we do here is just comparing the frame level features. By using a ResNet, we can find the object level correspondence for object tracking automatically emerge in Res5 block, and the fine-grained pixel level correspondence automatically emerge in the Res4 block. More specifically, we can use the fine-grained correspondence in Res4 to perform video segment propagation and tracking. So this is an example of mask tracking results given the mask in the first frame. Again, we just use the nearest label on the self-supervised Res4 features to do the task without using any fine-tuning. By just learning from comparing the two video frames, we actually achieve better results than previous state-of-the-art approach, which designs tracking tasks to learn tracking. Besides tracking pixels, we can also find higher layer convolutional features on Res5 for tracking objects. So we use these features to perform object bounding box tracking. This time we fine-tune the pre-trained features on the downstream tracking tasks. There are many interesting findings like on why this works well for tracking pixels and tracking objects. So the first thing we find is that larger frame interval improves correspondence results for both tasks. So what we do is we gradually increase the frame interval when sampling the two frames in training. We can find the correspondence, the performance for both tasks consistently improve if we learn from image that is far away. Another interesting discovery is that using negative pairs in training actually hurts the performance of learning correspondence. So there are lots of recent work showing learning the similarity between the same instance can be achieved without using the negative pairs. Basically just input two frames and minimize their feature distance. Why those results are interesting? It does not really improve over contrastive learning in different downstream tasks. In here, we find that learning without the negatives actually improves tracking and finding correspondence. So this is temporarily just empirical results. It's still unclear, and there's still a lot of space to study on why removing negative pairs actually can help tracking doing better. But a lot of the results we find that it does hurt the recognition results a little bit. So there might be some trade-off between these two types of tasks. Finally, learning with our approach allows our method to be applied to deeper legworks like ResNet 50. Specifically, for fine-grained correspondence tracking masks, previous approach of correspondence learning works well on ResNet 18, but it does not really generalize to ResNet 50, and the performance actually drops significantly on the deeper legwork. Our simple approach consistently improves the correspondence results with deeper legworks. So here are some more examples on the Davis dataset. Note that we didn't use any fine-tuning on this dataset and only propagate the first frame in the video. And here is a dancing video that we basically propagate the the frame, the rotation in the first frame to the following frames in these videos and do tracking on different people. So besides doing constructed learning, I would also like to introduce our recent work also in this ICCV. So the goal in here is to learn to separate or disentangle 3D structures and camera motions from the videos. So given the input video, we want to learn to have this video is about static scenes. And then we basically want to extract the 3D structure as deep voxels from this video. And then also the camera trajectory. And we want to disentangle these two components in a self-supervised manner. So our algorithm is very simple. It's a video autoencoder. Given the video input, what we do in here is that we first extract the 3D structure and 3D trajectory from these videos in two branches. And then given this 3D structure can be extracted in the first frame of the video. And because we are assuming the 3D structure does not change, it's static across the whole videos. So it can be used to represent the whole video. Given the 3D trajectory or the camera motion on all the frames relative to the first frame, we can perform these 3D transformations on top of the 3D structure, doing all different affine transformation or rotation or different translations. We can basically obtain a new voxel feature. And given these new voxel features, we can decode back to different video frames. So given different camera motion, apply on the same 3D structure, 3D voxels, we can obtain different new 3D voxels that can be used to render different new frames in the video. So our only loss in here is basically the reconstruction loss. There's reconstruction results by rotating different angles of the voxels to basically to be the same as the input videos. And here is basically some details of our framework that given a sequence of video frames, we basically extract the 3D structure from the first frame. So it's a static structure and it's fixed in the first frame view. And the lower branch, we basically given every 2 frames, we can compute the camera transformations between these every 2 frames. And then what we do is basically we use this camera to do a 3D affine transformation on these 3D voxels to basically obtain a lot of 3D voxels which can be decoded back to the corresponding frame. And our encoder and actually the 3D voxels is actually a deep feature itself. It's basically a 4D tensor with height, width, depth, and channel. So it's just a 4D tensor, a deep feature itself. Given the input image, we first use the ResNet to extract 2D features. What we do to obtain the 3D feature is simply by doing reshaping. We reshape the 3D tensor to become a 4D tensor. And then these 3D deep voxels are basically can be used to decode back to or rendering back the image. In here, what we do is just we have this camera pose and we apply this camera pose to rotate or to do a fine transformation on this 3D deep voxel. And then the transform features are going for 3D convolution and doing reshape back the 2D features. And the 2D features can be basically going for the convolution to render back the image of the input video. So the whole process here, there's not much fancy geometry operation. The only geometry operation in here is basically applying the 3D transformations using the camera pose on the 3D feature voxels. So how to obtain the 3D voxels and how the 3D voxels are used to rendering back the image are all using neural network operators, basically doing reshaping from 2D features to 3D features and reshape the 3D feature back to the 2D features. So it's not a geometry reprojection to the 2D image. It's just reshaping the feature and decode back to the image. So during inference time, our work can be used for view synthesis. So given the test image, we can extract the 3D voxel from this image. We can then basically apply a camera trajectory applied on this image feature, and then rotate these voxels and render back different frames in behind. So here is an example. We basically train on our model on this real state 10K data set, and we can apply a trajectory and render the new views. So I would like to emphasize that we are actually training one model on all the videos in real estate 10K. So this is actually a model that can generalize to different videos. For example, this is an out of distribution video that is not existing in the real estate 10K. And our work can even generalize to videos like this Van Gogh painting. Just given the painting, and we can apply the camera motion, zoom into the painting. And also this Minecraft game. So although the synthesis results is not as good as NERF, but we are not doing per video optimization. We are training a single model for all the videos. And it can be generalized to a lot of out of distribution scenarios. So view synthesis is just one application. Another cool application in here is actually we also have a way to obtain the camera motion in a self-supervised manner. So different from previous work, we didn't use any ground truth SFM or SFM camera in training time. The camera itself is also automatically emerged and learned by doing the reconstruction. So here is some comparison between the infer SFM trajectory and the predicted trajectory from our model. And we compare to CoMap and basically show that so our camera motions, if only given 2.5 second videos, we actually have much better camera estimation and much faster time. Instead of doing 71 seconds, we only need to use 0.004 seconds to invert the cameras. But of course, when there are longer videos, CoMap will get better results on the estimation. But in here, in a relatively short video, we can show that our camera estimation are actually quite reliable. And it's all trained in a self-supervised manner without any ground truths. So the third application here is that is the video following. So what we can do is, given the image and the moving video, we can extract the 3D structure from the first video and the camera motion from the second video, and then we can basically have an output that is following the camera motion in the second video. So here is another examples, because we can disentangle the representation in the video. So far, both of this work, we have introduced self-supervised learning that is applied on this passive data, on the YouTube videos or on the sim videos. So how about apply self-supervised learning in an active setting? So in this following work, which is led by my PhD student, Nicholas, I would like to introduce how to utilize self-supervision in time to generalize reinforcement learning agents in new environments during deployment. So it is a very challenging problem to generalize a trained RL agent across different environments. Normally, an agent trained with the environment on the left using visual inputs does not really generalize to environment on the right, even we just change the color. In this project, we investigate and the research directions which we want to learn a policy and fine-tune the policy in a single environment during deployment, and then adapt this policy during the deployment itself. So instead of training a robust features that can be generalized to all the environments, can we try to adapt the trained model to the new environment during test time? So to adapt our policy in test time, we are facing with the following challenges. First, we may not have access to any data from the target environment. And second, we cannot assume we will have access to the reward signals, as the target environment could be the physical robot. To address these challenges, we basically propose to adapt online using a self-supervised training signal and only data collected during the deployment. So our algorithm is very simple. It consists basically two phases: the initial training phase in the fixed environment and the adaptation phase during deployment in the target environment. So first, we divide our policy legwork into an encoder and a policy head. During training, we then jointly optimize a self-supervised task together with reinforcement learning, with both tasks sharing the same encoder. So during policy deployment, we cannot assume access to the reward signals, and we may therefore not be able to optimize our RL policy. But we can still optimize the self-supervised objective using the observation that we receive from the environment. So we can still continuously tune the self-supervised head, which is used to train the PIE, which is the share feature. And because the share features is used by the reinforcement learning head as well. So as the share features adapting to the new environment, it helps improve the RL agent at the same time. We apply this approach to many scenarios in simulation. In here, I specifically want to show our results on some robot pushing tasks. So basically, in this environment, the task is pushing this red block to this yellow block to the red dot as the goal. So it's a goal condition policy. The agent or the robot is only trained with image input without any state input. So in simulation, it works pretty well. But when you try to do direct transfer to the real world, we basically buy a disco light and play the disco a little bit in the lab environment, and we can see that the direct transfer will completely fail. The disco light will just confuse the legwork, which use only visual input. By using our adaptation methods, we basically continuously train the self-supervised objective to make this legwork continuously adapt to the new frames. So the legwork can basically work very well on pushing the block to the goal. And here is another example. We're basically showing that if we just change the table sheet different from the training environment, so by using our adaptation technique, we can also transfer the policy that is trained in simulation to the new environment in the real robot in an online manner. So here's the work on robotics manipulation. So we also have work that is trying to do local motion control. So this work is basically done by my PhD student, Raquel. So in here, we propose a method that trains IR agents in an end-to-end manner, taking the state input and also the front wheels of the robot as the input. And then we need to output the action directly with one network, basically control each joint of the robot to do local motion control. And the robot needs to move forward to avoid obstacles. And the obstacles can sometimes be moving. So the advantage of using reinforcement learning in here, instead of motion directly doing planning, is that if the environment is changing all the time, planning might take, and optimization will take a lot of time. If we can change this vision-based RL policy, you can basically apply to this environment to do very fast inference. So in here, the paper is about how to combine the vision information and the state information using a transformer. We didn't apply the self-supervised task in here, but it certainly can be extended in this kind of environment. During the summer, we also extend our work to apply this approach in the real robot instead of just simulation. So in here, you can basically see that our robot, even running in the wild, we can avoid the boxes running on the grass and avoid the boxes. And also the human can move and stop the robot, but the robot is trying to avoid the humans and the bugs. We also run the robot in the forest that it can avoid the trees, and then it can also run in the evening. And on the left is basically what the robot sees. It sees the trees and then try to avoid it. And all this is trained in an end-to-end style with reinforcement learning, taking vision as input and the state information as input. So while all this work in here is showing some promising results or application results of reinforcement learning, but certainly training with only RL objective is going to be very inefficient. So is there a better, more efficient way to do robot learning? So, in the following, we basically try to look into a more efficient way for learning by imitation. Specifically, we introduced our recent work on extracting 3D hand and pose object poses from videos and use them to provide 3D demonstrations for imitation learning for dexterous manipulation. So I will first introduce our work on hand and object pose estimation from videos. And this is work done by Xiaolong and Wang, who was our master students. They are going to do their PhD in UT Austin and UIUC. And our goal in this project is basically to estimate the 3D hand object pose estimation and the 6D object pose estimation at the same time, as you can see in this video. So in this work, we basically applied a semi-supervised learning to try to generalize this kind of pose estimation better. So instead of just perform estimation in a lab environment setting, we hope to generalize our methods in the wild videos. So we first train our model for hand and object pose estimation on the actual 3D data set, which is in the lab environment. And then we deploy the models on the something video data set to generate the pseudo labels. And we use these labels back to perform self-training to tune the model back. So it can improve and see more data and improve the generalization ability of the model. So our model is also very simple. We just have a joint model to output the hand and object features, and the features are being processed with a transformer, which help to get some context information and interaction information between the hand and object features. And the final outputs are both hand and object poses. We apply this model in a semi-supervised learning manner on this something video data set. We basically in here, we use some spatial temporal constraints to filter the good estimation and the bad estimations. So in the green boxes represents the estimation is good, the red boxes represents the estimation is bad. We basically use some time constraints or consistency constraint. If the two poses in the nearby frames are changing a lot, that basically means that it's not a good estimation. So here are more examples on we basically apply the pose estimator on the something videos and generate pseudo labels to retrain our model for hand and object pose estimation. In here, we are only able to do semi-supervised learning for hands. That is because the number of data for training objects in a supervised manner are really scarce. In the actual 3D data set, we only have a few instances on training objects, and it does not really generalize to this in the wide video with many different objects. So in here, we are only able to do semi-supervised learning on hands. But interestingly, even though we are only doing semi-supervised learning with hands, because the hands and objects are sharing the features and they are interacting with these transformer models. So by improving the hand results, it actually also at the same time improves the object pose estimation results. So there are basically around 10% environments improvements over the baseline. However, the object pose estimation is still a very, very challenging problem in here. So given these results on hand and object pose estimation, how are they going to be useful? So in the next project, which is done by my PhD student Hilde and Yuehua, so in this work, we are basically trying to use this 3D hand and object pose estimation to help the dexterous hand in the simulation environment to perform these different manipulation tasks. We propose a framework called DexMV on dexterous manipulations from human videos. So there are a lot of previous work on doing imitation learning from human videos. However, most of the work are still focusing on manipulation with 2D parallel jaw grippers. Thus, learning from RGB directly might already be enough, since most we need is the motion of the arms and open and close of the gripper. However, when dealing with dexterous hands, we will need to have detailed information on how each finger moves, which is a much harder action space, much larger action space, and more challenging. In this case, we need to have detailed 3D demonstration from the human hand. So because of that, we proposed the DexMV, a new benchmark for dexterous manipulation, using imitation learning from human videos using 1 or 2 cameras. The DexMV stands for dexterous manipulation from videos. We collect paired tasks where human hands and the simulated robot hands are asked to do the same thing. We so far collected data for 3 different tasks. So you can see we use the green table in here. So we do that primarily because we find that object pose estimation in the wild is still very, very challenging. So in this project, we are still collecting data using the green table in here, but we are planning to extend it in the future. So although the hand pose estimations are already pretty good, but it's still very challenging for object pose estimation. So in the second row, we can see some pose estimation, both hand and objects. In the third row, we basically show some robotic environments of these 5-finger hands to try to manipulate these objects. So although the data collection process is using the green table background, it's actually very efficient to use our framework to collect the data. We can collect 100 demonstrations in just 1 hour. So our goal in this project is to bridge the gap between the 3D computer vision and robot learning. We show how computer vision can provide data for improving reinforcement learning. And we also want to show imitation learning itself can potentially be a new metric for pose estimation. Instead of estimating the millimeters on how accurate the pose is, can we actually look into downstream tasks, imitation learning tasks, to see whether the pose actually helps imitation learning. So our platform basically contains 2 parallel systems, including a computer vision system and a simulation system. So we first collected raw human videos on collecting the human hands operating the objects, and then we do 3D pose estimation. And then this 3D pose estimation are basically being retargeted to robot motion, because human hands and robot hands are different. We need to do retargeting here. Given this robot hands manipulation demonstration, we can use it to combine with reinforcement learning to basically trained for a policy, a goal condition policy to do this robot hand manipulation in the simulation environment. So here is more detailed. In the computer vision system, we basically collect human demonstrations, perform 3D pose estimation, and motion retargeting to generate the demonstrations. So in here, here is the human hand grasping the master bottle. We can collect 100 demonstrations like this in 1 hour. And here is examples on pouring the beans in the cup into the bowl that the human is doing the task. So given this 3D pose object and hand pose estimation results, we can then do hand motion retargeting to basically convert the human hand to the robot hand. So because the kinematic strengths and the structure and the degree of freedoms are different from the human hand and robot hand. So we applied some optimization-based technique to convert the human hand trajectory to make it become a robot hand trajectory. So here is some motion retargeting results. Given the 3D pose estimation results in the middle, we can convert the trajectory into the robot hand trajectory on the right. So you can see that it's a kinematics retargeting result. It's not the dynamics retargeting results, which means that the retargeting results does not really have a physical constraint. It's just animations. Because there are occlusions and the contexts are not correct in the 3D pose estimation. So the retargeting results also does not have perfect contact and the perfect physical interaction results. But we still find these kinds of demonstrations can provide a very good high-level ideas on how the robot hands should roughly manipulate the objects or interact with the objects. So given the demonstrations on the right, which is like hundreds of human robot hand manipulation demonstrations from the simulation, we can combine it with the reinforcement learning data together to basically train a policy for this robot hand to manipulate the object. So in more detail, in this imitation learning algorithms, we basically train a policy for each task in each object. And the policy input is the current hand and object state. The policy output is the actions to take to finish the task. We learn a goal conditional policy, which means that the policy can be generalized to different object configurations. It's not just like motion imitation, which just repeat one trajectory of the demonstration. We are actually a more generalizable goal condition policy that can be applied to different object configurations and placement. So the imitation learning algorithm is mostly based on DAPG, demonstration augmented policy gradient. So there's an equation here. We don't need to dive deep into this equation, but it basically contains two terms. One is the reinforcement learning term. The other is the behavior cloning term. In the behavior cloning term, we are basically use the demonstration data we collect to guide the policy to do the actions that is following the human demonstration. And the reinforcement learning terms will basically guide the policy to behave to have the correct contact and interactions in the very detail. So the way I see it is basically human demonstrations can provide high-level guidance to tell the robot how roughly you should move. And the reinforcement learning term can basically tell the policy to do the very detailed interactions, like how it will actually work in the physical simulator. So the benefit of doing so is not only we have higher efficiency, better sample efficiency, but also it can guide the policy to do more natural or expected or safe behavior. So here is basically a comparison. If we only learn to grasp or relocate the object to the target location using reinforcement learning on the left, because the dimensions of the state and action space is very large. So it's actually very hard to explore the policy to make the robot hand to behave normally. But using imitation learning data, we can actually guide the robot to do the actions that human will do. And here is a lot of examples. So basically, this is grasping a clam. We can see the grasping pose on the right is different from the previous one, because we human also use different grasping pose to grasp different objects. But if you use reinforcement learning alone on the left, you can see that the IL agents can explore some very weird grasping pose to get the objects to the goal locations, not what human would do naturally. And for more complex tasks, like the task in here is trying to pouring the beans from the cup into the container. So we can see using imitation learning, we can do the task, but using RL alone, basically we fail to accomplish this task because it has two stages. So you need to first pick up the cup, and then you need to safely pour the beans into the, or the particles into the container. And it's just a very complex space for reinforcement learning alone to explore. But given some guidance from the human, we can efficiently and safely learn this policy. And finally, I also want to basically show that the imitation learning algorithm itself can possibly be a good metric for 3D computer vision. So instead of just estimating the millimeters or the errors of post-estimation, we basically try to have different 3D estimation results, and then that leads to different demonstrations in imitation learning. So in here, we have one camera and one camera plus post-processing, or two cameras plus post-processing, means that we use two cameras to estimate the hand pose in here. And we can see that if we can improve the 3D vision results, it will help improve the imitation learning results as well. So in return, the imitation learning can become a metric for 3D pose estimation, so that in the future, I hope that there's a possibility that we can evaluate the 3D visions based on how much it helps imitation learning, but not just how large the error of the estimation result is. So that's the end of my presentation. So in summary, I have introduced our work on self-supervised learning in videos, and use self-supervised learning to help reinforcement learning, and also use these kinds of 3D pose estimation from videos to help imitation learning. And all this work are done by the great students in our lab in UCSD, including PhD students, master students, and the undergrad students. So if you have any questions, we can start the Q&A section now. Thank you.
I practiced it. Gkioxari, Georgia Gkioxari, right? Yeah, that's cool. Right. So Georgia is a research scientist at Facebook AI Research, and she has been a previous recipient of MAR Prize and Kwame Young Research Award from this year itself. We are happy to have her here itself. And the title of her talk is "Can Video Rescue Video Recognition?" The floor is yours.
Okay, thank you, Vivek. So, you know, we're kind of a little tired, like for all these talks. So I kind of wanted to have a talk / discussion / ideas / it's a tutorial after all. So, you know, it is so some food for thought about what video, like define video. What is video? How can we expand the idea and notion of video and get to more interesting tasks? Okay, I'm getting ahead of myself. So I will talk about video today, and before I talk about video, I kind of want to talk a little bit about object understanding and object recognition. And I don't know if Xiaolong touched a little bit on these things, but you know, the goal of the people like me and hundreds or thousands of other working in this field is to be able to build models that take an input image or potentially many input images, but it's a continuum. So even from one input image, and be able to start understanding things about what is on those pixels in that image. So we want to understand objects. We want to be able to understand humans, their pose, how objects interact with humans. And when we say understand objects, we might want to understand 3D shapes and property of objects. After all, we live in a 3D world, so we can't just restrict our predictions to be in 2D. And don't get me wrong, we have made great progress in this direction of input image to the objects. And here I'm showing you a little clip from what it looks like to apply these models on images in the task of object recognition. This is a little demo from the Detector 2 team, which is like a library of many models for object understanding from 2D images. And the pipeline we've been taking in the past, which has become the predominant paradigm for how we proceed in this field, is by spending a lot of money annotating images for the particular task that we want to solve and training a model to imitate these annotations. So we train models to basically imitate what annotators have annotated. Things are not quite different in video than in images. So we've had all of these, a slew of very interesting tasks that have been dominating video understanding. These can be tracking, like tracking objects across time. This also action classification. So you have a clip and you want to say what every human in the clip is doing. Or forecasting, like, you know, you take a clip and you want to say, well, here I'm seeing this clip, what is the human doing 5 seconds later? And we have all this interesting data, videos of complex motion, of people doing interesting things. And my perception of what we're doing right now, and I am critiquing my own work because I've worked in this field, is that we take this video, we chunk it into frames by separating all these frames in this high frame FPS rate, and then we average. So it's basically a fancy averaging that goes from many, many frames into one 1D label, like an action. That can be the action that's happening right there in the clip. That can be the action that will happen later, or even a 2D pose, which is a little richer than 1D signal, but it's still very much less rich than what the videos show. And I'm going to say, and I hope I don't offend anyone by saying it, but this is kind of a depressing state to be. Sure, these problems are very important, but why are we obsessing over only these problems? I mean, videos contain so much more information than just one action label. And I also don't see why the problem of action classification is the only problem that we actually work on. It makes very little sense. We want to solve more problems, and we want to understand more about the world. Video is how we understand more about the world. So we need to come up with with a diversity of tasks and a more open-minded way of looking at what it means to work on video. What is video? And I've tried to come up with like a few really important sort of like buckets of new ideas and new direction in the computer vision field. One is this idea of collecting egocentric videos. So you have a person that is walking around. I'm not sure if this video was playing. Let me try to play it. But you have basically people walking around their home or their living accommodation, whatever that is, their garden, and they're collecting images. They're like, this is how they live. I'm sure that you all do this if you will, like in your everyday life with your phones. And this is a really nice set of data. It is the kind of data that we all use. It has richness in domain, and it has a richness of information that it contains. And there's a lot more interesting tasks that we can do. And people have already been working on them. People have been trying to use data sources like this to train robots to navigate around and achieve goals. The other bucket of really interesting data that exists out there is white baseline data. So sparse views of various structures, indoors or outdoors, it doesn't matter. This is what I call a white baseline. There's some really interesting data that have come up. One is HyperSim, one is Omnidata. Omnidata, I think, is presented in this ICCV. That is a data set of views of scenes, indoor and outdoor. And again, we know that they're from the same scene, so we know that they represent the same environment. The objects repeat themselves, the same object from different viewpoints. This is also a video. It is a video because it is in the continuum of high frame rate FPS to low FPS, but it's also a video because it captures a scene, it captures a continuum of motion, where here the motion is perhaps the person walking in the scene and capturing that scene. So, and I'm saying this because I've been having all these fights with reviewers and researchers about, oh, but this is just multiple views. No, it's not multiple views. It is video, because multiple views means that you're looking at the same objects from different viewpoints. Well, actually, that's also a video, but this is not just that. This is just sparse views as you would walk around with your phone and take various snapshots of where you live. And we should be able to do things with that. So I want us to start thinking of all of this as videos and try to broaden our minds about what things that we can do with these things beyond this action classification, forecasting, tracking that we've been used to seeing. Okay, sorry if I'm coming too aggressive, but I'm really passionate about learning from video, and I want to invest less energy into fighting about nuisance, about what it is, if it's video or not, and move more into tasks and important and what it is that we can do better through learning from these really beautiful data sources. And I want to give you two representative works that are in this direction, which make use of exactly these structured data sources, these sort of videos in this new definition of videos. So one is the novel view synthesis. I'm sure that you've seen this task before. Here, I will define the problem. So you're given an input image. This is a scene that you've never seen before. So I'm showing you two images right here, scenes that you and your model have never seen before. And you're asking your model to predict how the scene looks like from different viewpoints. So this is, and here, shout out to Olivia, of course, but I want to mention that two things. So first, this is a problem that's been studied extensively. You've all heard about NERF and all these follow-up works on novel view synthesis. And of course, NERF is not just it. There's an abundance of prior work that I'm trying to summarize in this slide. And of course, there is a lot more. But I want to emphasize 2 points. First, it's really important whether we talk about fitting or generalization. In this particular setup of novel view synthesis, we're tasked with the problem of synthesizing new views from a single image of an unseen scene. So you have a scene you've never seen before, you're given an image, and you are asked to synthesize novel views. Now, this is a different problem than fitting, and I'm going to give you an example of fitting work afterwards, where you're given views of an object, like maybe sparse views around the object, and you're asked to interpolate on novel views, but when you're given already some views of that object. And I'm highlighting this because there is an inherent component of semantics in this generalization task. In order to understand how to synthesize new views from a novel scene, you need to understand objects and you need to understand 3D structure. And this is because you need to understand how objects appear or disappear when a camera view is changing. And for that, you need to understand what object are you exactly looking at. A chair will appear or disappear differently than a TV monitor or a table. And of course, you need to understand geometry, what object is far and what object is near. So this is something that your model, your core model has to learn in order to accomplish this task. And so the approach that we take here is a latent point cloud approach. And it goes also into this question of differentiable rendering. So here's the model. So you take an input image and you train a feature network. So this is just a CNN, let's say. It could be a transformer, whatever, you know, your cup of tea. You train a feature network that extracts a feature vector at every pixel in the original image. So that network projects an image into a feature vector, into well, feature map, feature vector for every pixel. And you also train a depth network. That network predicts for every pixel in the image the Z value, which is the depth of that pixel from the camera. So now you can combine these two outputs and construct this point cloud. This is a latent point cloud. Latent because you have an XYZ point. For every XYZ point, you have an associated feature vector attached to it. This feature vector can be like 64 dimensional, 128 dimensional, depending on your feature network. So now, given a new viewpoint, the viewpoint that you want to synthesize a new view onto, you take this 3D latent point cloud and you project it onto the new view. And of course, this has to be differentiable projection. So now you have this new projected feature map, which is the result of transforming and projecting the point cloud onto the new view. But of course, it's a feature map, so you wanna, at the end, you want an RGB image. So you train a generator network that will take that feature map and output the predicted image. And of course, you need to have a discriminator to understand whether it's a real or a fake image. And you train this model with an L2 loss between the predicted image and the target image. And I want to say that here the network has to do a lot of things. It has to understand a 3D structure, and the generator network has to also, along with the feature network, have to also understand how to in-paint and out-paint that image to construct the new view. Just this rotation of this transformation of the point cloud is not enough, because as you rotate a scene, when you look at it from a different viewpoint, parts of the scene become occluded, and that is where, so parts of the scene are not part of your initial viewpoint in the input image, so your model has to hallucinate. And this is sort of the power of end-to-end learning with a feature network and a generator network. And have in mind that the only supervision here is the input image, the target image, and the camera transform, but you're not given any other 3D information at train time. And and this goes back to my question of what is a video and what's not a video. But so we use an abundance of data sets here. We use Matterport and replica environments to construct walkthroughs of these scenes. And we also deploy this model on real video. This is the real estate 10K videos, where we walk through, these are walkthroughs of people going through various properties like gardens or houses or whatever it might be. And I want to emphasize that video here is used very differently. It's not used by taking consecutive frames of like a 1 second clip. In order for this method to work, you want to choose views that are not too far from, but that are far from each other. Taking two consecutive frames from a video will not contain enough change in order for your model to learn all this complicated 3D structure and semantics. So this is where you use videos as a way to get to this wide baseline, low FPS regimes of getting views of the scene that look differently. But you know they're the same scene because they're part of the video. So we're ablating and running extensive experiments to show this power of this latent point cloud idea. And we use, of course, we have all these metrics that people use for image synthesis, like PSNR, SIM, and perceptual similarity. These are all like standard metrics to evaluate how good your RGB outputs are. And we compare to baselines to image to image. So a baseline that will just produce the output image without this latent 3D structure being learned in the network. And also a very a similar method to SynSyn to our approach, but instead of point cloud using voxels. And our metrics are very promising in showing that this idea of latent point cloud is actually effective in generating better RGB images from a metric standpoint. And let's look at some qualitative results. So I'm showing always the first image that's being input into the network. This is scenes that the network has never seen before at train time, and it's generating these views at test time. And I'm going to leave this slide a little bit for you all to check it out. And I want you to focus on not only the quality of the RGB, which is the first thing that the human eye attends to naturally, but also on the structure in the geometry. So as the view changes, you should be looking for, is the geometry consistent? Do the lines stay being straight lines? Do the objects actually change in a very reasonable manner? These are things that as your eye actually processes without you knowing, but pay attention to these little details when you watch these videos. More interestingly than looking at these RGB images is to see whether the network is actually able to learn anything about the 3D nature of the scene. And here we visualize that point cloud. That is the point cloud that the model learned inherently in its design. And we see that it actually is able to capture some rough 3D structure of that scene. So things that are far away are actually far away, and things that are closer are closer. So this is what the point clouds look like, and this is for a lot more scenes. Fantastic. So, and there's a couple of great properties of this, of using a point cloud as the 3D interpretation. First is that it is a really, using a latent, the latent aspect of the point cloud allows us to actually do a generalization from Matterport, which is from basically do different data sources. And this is only possible because the model, the point cloud has actually left it into a higher dimensional space that is able to deal with the domain gap. And more importantly, we're able to generalize to higher resolutions without any training much easier. And this is a nice property of having now the point cloud aspect of the representation, where that allows you to generalize to higher resolutions much easier, while a voxel, which is what we're comparing to here, is much worse at performing that generalization because of its it's definitely far from an ideal representation for resolution. Voxels do suffer from resolution. So this is the one project where using this different way of getting data sources from videos allows you to learn something a lot richer than just like an action label. And last, I want to mention this work from Shubham, who was a UC Berkeley grad student, wonderful guy, where we wanted to study the problem of 3D object reconstruction from sparse views. So here the problem is as follows. You're given RGB images of an object. These are multiple views of the object. And remember, this is actually really a real problem. So I don't know if you've ever used Facebook Marketplace or Amazon or eBay to sell any of your stuff, but these are usually the kind of images that you would take. You would not really take an actual video. That's not really what you would do if you wanted to sell something. You would actually take snapshots of that object that you're selling for maybe 4, 5, or 6 views. So you have small number of views, white baseline, so different. They show the objects from kind of different angles. And from these very sparse views, white baseline views, you want to be able to reconstruct the shape and the texture of the object. And to facilitate that, we will also use masks, object masks, in addition to RGB views. Masks are easy to obtain through our latest, greatest instance segmentation models. And we'll also start from noisy estimates of cameras. This is something that can actually be provided by running CoMap style camera estimators. They're not going to be perfect because of the wide baseline, but they'll give you some sort of estimate of the cameras, noisy, but estimates. And through our model, not only do we want to reconstruct the 3D shape, we also want to perfect the cameras. We also want to estimate the cameras much, much better. And so I'm showing here some results fast forward, where we have this views of the statue from the Tanks and Temples dataset. Also, this was a video that we sampled views from. We obtain measurable mass carcinogen, and we are able to reconstruct both shape and texture of that particular horse without any 3D information. And you will, of course, guess already that this is not a new problem. This has been studied and extensively in like many years, even before deep learning. Of course, this is the multi-view stereo, binocular stereopsis problem, where you're given views and you're asked to reconstruct it in the form of a 3D shape, point cloud or mesh. But the problem with traditional techniques here is that they rely on this first step, which is the step of finding correspondences across views, which are then lifted to 3D space by a triangulation. And now the problem becomes that in order to get a good 3D representation, you need dense correspondence. You need an abundance of correspondences. And in the absence of dense views, you can get this many accurate correspondences. So in this particular work, we are trying to bypass that problem of finding correspondences and go directly into estimating 3D shape from views. And the idea is very simple. We are it's based on this old paper from Gavves and et al. On model-based stereopsis. So we're going to start from the views that we have available, and we're going to start from an estimate of the shape, and we're going to warp it in the target view, and we're going to compare it to the target image, and through iterative optimization, we're going to try to perfect the shape and the cameras until the predicted and the target view come close together. We're going to use differentiable rendering here, in particular PyTorch 3D, that allows us through this modular design of the library to do our warping and texture transferring that I'll describe later. And so here's a problem setup. So and the solution setup. So let's assume that you have 3 views of the object available. You're going to make 2 views as your source views, and the third view is going to be your target view. And you're going to start from a shape estimate that at the beginning is completely inaccurate. It can be a sphere, it can be a polygon, it can be whatever you want it to be. And so from that shape estimate, you're going to find which pixels, which points on the 3D shape should grab texture from which image. And the criterion there is whether that point is visible from the particular source view, how visible it is. So you're going to do this texture transfer exercise to find which pixels for every point of the shape, which input view to pick the color from. So which input view to interpolate the pixel from. And then we're going to warp. That is the warping procedure of transferring the texture from the existing views into the target viewpoint, and compare it to the ground truth view. And we're going to have a texture loss. We're going to have a mask loss, as well as some shape priors on the shape, just to enforce some sort of smoothness into the shape. And through differentiable rendering, we're going to propagate all this information back into the shape. And I'm going to show this video that Shubham has prepared that shows the reconstructions. And notice that we're only having very sparse views. This is in the order of 4 or 8, so not a lot of views, and very noisy cameras that are much noisier than a lot of shape reconstructor methods can handle right now. You also see the complexity of these shapes. They have a lot of holes, a lot of weird structures, I like this particular example because it's only 4 views of a guitar, and it's able to actually understand the shape in the form of a mesh and the texture. This is the example that you've seen. This is the word I showed you at the beginning, but here you're seeing this together with the texture. And finally, we also compare to a lot of baselines. So we actually choose the NERF baseline to compare to as well, which is developed for this particular setting, fitting a model from a set of views. The NERF usually requires a lot denser because of this implicit representation. It requires a lot more views than 8, which is the number that we're striving for here, like low, small number of images. And we train NERF for this, we optimize NERF for this task for our data set. And we also have a variant of NERF, which allows gradients to flow back to the cameras, because original NERF requires accurate cameras, which we do not want. We want noisy cameras and we want to fix them, so we allow gradients to propagate back. So we enhance NERF to do this, and also other more traditional techniques. And you see that, I want to play this, I mean, you actually see this already, that a lot of these methods are not able to reconstruct shapes. That doesn't mean that these methods are good, but in this particular regime of small number of images, a lot of these methods fail, while an explicit shape representation is much more suitable. And I want to show more images. This is from this data set. It's called the Google Scan Objects data set. And again, we're showing the input views on the left, and we're showing the reconstructed shape on the right. And more images. You see is a variety of objects ranging from cups to toys to coffee makers to shoes to trays, all sorts of stuff. I also like this particular data set here. This is images from Amazon, exactly what I was saying before. People try to sell their stuff. They take images, not very many of them, just 4 or 5, and we reconstruct their shapes only from this small number of views. And also I wanted to give an looping back into traditional techniques and how they're not able to reconstruct well given small number of images. We're also comparing to CalMap, and you see that CalMap is can do point cloud reconstructions, but when it comes to these sparse views, it fails to do this because there is holes on the shape, since there's parts of the object it never sees before, that it cannot reconstruct. And last but not least, I want to leave you with the last bit of ablation that we did that I found very insightful, which is understanding which part is important to reconstruct shapes accurately. Whether comparing textures or only comparing silhouettes is, and what that impact is to the model. So we show the input views on the left, and then we show 2 variants of our model. First on the right, far right, we show the ground truth shape. On the second to right column, we show our method. This is a method where the loss is both a texture loss and a silhouette loss. And then we also compare to a variant of our model that was trained without the texture loss. So it was trained without comparing textures, only masks. And what I want you to notice is that when you omit texture from your loss, you're incapable of capturing these creases in the shape, these concavities in the shape, these ones that show up in the Monopoly box or in the backpack, these creases. This is something that the model relies on texture to capture. It's not able to capture purely by a silhouette. I found this a very insightful example that also was captured by the model that we trained. And so this is the end of the presentation. And I wanted to say video is important. Video is going to be the data source from which we learn from. It's abundant on the internet. There's so many exciting data sets coming up, like Higo 4D, Omnidata. All these are video representations. And it is a data set that allows us to capture continuity in time as well as appearance from a single frame. But I think that it's important to expand our definition of video, think broader, think about more tasks, think about all the nice things that you can do, and not be too just about news. It's about what is a video, what is multiple views. Everything fits, everything comes from this continuity of representation that one captures. either that being a wide baseline or a narrow baseline. And I want to say that feel free to ask me a question or disagree with me in one way or the other, but it's a very exciting time to work on video.
Thank you very much for a great talk. Yeah, thanks. So I was kind of curious, so you spoke about like some use cases that you spoke about, right? So if 5 images are being uploaded on Amazon and then they try to reconstruct things, no one is going to buy that kind of product. If I would see that, I'm not going to buy those products if it looks that crap.
I know, it's true. So we're not there, like, correct. So it's not only, right. So selling products, I have to say, you need to be sure to make it very pretty, okay? So yes, so it's not necessarily for, so we have more work to do to sell products. However, I feel that there is a lot more things that we might want to do with these 3D reconstructions. For example, how do you see if this shape will fit nicely in your living room? Okay, like you definitely want some sort of notion of the 3D. Also, it is important to start reconstructing 3D shapes because you might want to interject them in other environments and create more sort of this diversity in data, this data annotation. Maybe I'm like talking about projects that we're working on, but there is a lot more applications to and interest in reconstructing 3D than just producing nice results that look good to the eye, and which is another point I wanted to touch. It's not just about things that just are beautiful, because this is a hard problem, and I think we'll get there at some point of good looking shapes, but there's more to it than just having shapes that are beautiful looking.
Yeah, indeed. And I would also say something that often I think the Matterplot, for example, they request everyone to upload their videos. So in like different type of real estate business, right, where Correct. They are actually uploading videos because no one trusts images in that point. Nowadays, often we are putting it on, but it looks, I'm not sure. Videos does help, at least in Cambridge.
So you mean videos help in what regard?
So as if like if somebody's trying to rent out a place or
yes,
then videos are much more interesting in comparison
Correct.
to images.
Correct.
Right?
Correct, absolutely.
Yeah, and one question I had in this direction is how complex are these setups? Like differential rendering, it's like all inference, right? So in the end, what you deploy is the inference mechanism, and which are not complex at all.
Well, differential learning is not just inference, because I showed two works where the last one is inference. Like, I mean, inference meaning that you fit a model. So you actually don't learn any feature representation. You just try to propagate back directly to the 3D representation. But the first one on the novel view synthesis, differentiable renderer was actually used in order to learn features. So it was used in order to build this higher level representation of this scene that will allow you to do all these other tasks, like the synthesized views from different viewpoints. So differential rendering is a tool. It can be used training or inference. It's not tied to where it's used. But it blends very nicely with videos. It's videos and 3D. So that is where it shines, I would say.
Yeah, indeed, that's true. 3D and videos, it has a huge use cases that one can think of. Yeah, awesome. And like I would also ask, so what do you think? What's next in this direction?
In which direction per se?
Like if we talk about differential rendering, because I see that like nowadays, like vision conferences there's so many papers, everyone, it's like a new direction now. So what do you think? What is gonna happen next? So would this be included in like each pipeline that we would see?
Okay, I mean, there is what's next. And I mean, I have a lot of opinions on that. I think that I think that in computer vision, we have a lot of problems, including the ones that I showed that are not solved. They're very far from being solved in IRL, like in real life, in the wild. at scale, to the point where exactly what you said, Vivek, like, I want to sell this. Are we ready to make that into that level of quality, of good? So I think that if I was now a student, I would not just be discouraged, I would be encouraged. I was like, look at all these different problems, which are far away from the boring problems, I'm trying to tread lightly here, of classification and like ImageNet numbers. And let's get 2 more points on the kinetics data set. Boo-hoo, that's boring. Like, there's so many more problems that we care about now, we want to solve. And not only for the sake of solving a new problem, because I can't, like, I might not have the $1 million to spend on TPUs, but it's actually, these are more important problems. We are in the space of wanting to build AR, VR, where we can, I guess, embed ourselves in like another experience in another universe, and we will need more solutions to these problems. So actually the space is opening up. It's about becoming creative and about pushing things to concoct more solutions or improve solutions or come up with new problems. I mean, I think that we are at that phase.
Yeah, thanks. I don't think so. I have any more questions.
Hi, Georgia. I have a small question.
Yeah.
Thanks for a great talk. Thanks for the work. Same thing is also inspiration of our work. So I think a lot of current work in here, it does require a small thing, the camera. So yeah. So what do you think? I was trying to push something that like we get rid of the camera, get rid of SFM. Do you think it's important directions? Like
absolutely. So the camera is a kind of yeah, I think so. I mean, correct. And I think the camera and the need of cameras is something that's holding us back from going in the wild. I agree with you 100%. And every effort in that direction should get attention. Like, this is something that a lot of people don't understand, but a lot of these methods like NERF and they're not just collection. And a lot of the things that I showed today, they're not just collection of images. They are actually requiring also. So when we say no 3D supervision, that's not quite right. Asterisk, right? There is that 3D camera. Now, there is definitely that aspect of estimating 3D cameras is easier than 3D ground truth because it's you actually need 8 points in theory, right? To solve for cameras. Of course, you can get more than 8 points and then, to filter out noise and get even more accurate cameras. But it's still a big, drain because it puts a restriction. And if your cameras are, far too noisy, and we should have, we have in the paper, things go off the rails, right? So you can't even recover, no matter how much you're trying to fix things, you can't recover from wrong estimates. So here's another problem to work on. Try to get rid of cameras. Like, I don't have a solution, but I agree with you that it's a big problem.
And also SFM does not work all the time, right? So it's just, So I think even like the data set like Facebook released recently, the CO3D, we are trying to, it gets good reconstruction results, but we are also trying to use the depth that is compute from SFM to do something, but it's just a little bit off when you are trying to actually use it for like 60 pose estimation and those tasks.
It becomes a chicken and egg problem, right? Because I'm not surprised. I think that SFM for cameras, so like cold map style techniques for cameras, I would trust more. But 3D reconstructions, I guess you're saying that the SFM reconstructions actually look good.
It's okay, but then when we are trying to use the depth, to like we try to do some 60 pose estimation, like matching the template with the depth, and then it goes quite off. The scales and everything is not quite right usually. So
the other question that I have is whether SFM style techniques can actually understand metric information well. Because everything is like, you can have a scale depth ambiguity. I guess you might know the camera, the focal length and everything, but it's still difficult problem.
Yes, yes, yes. Yeah.
I haven't used the CO3D data set. I think it's a great. I think it's like a good large scale data set to use in this direction. But so I don't have like lots of. You're actually the first to tell me that, and I thank you for that. Like having that.
Oh, we are just only recently looking into it, but maybe we are doing something wrong. It's not. Yeah. Okay. Thank you. Thank you for.
Yeah. Of course. Of course.
We have two more questions from the attendees. So the first question is, how effective is the proposed approach at reconstructing the same scene?
So, I mean, this is a good question. I don't know which work it refers to, but I can answer for both. So we actually have work on this so to try to go into more complex scene rather than just one object. The problem becomes even more difficult because if you want to reconstruct multiple 3D objects in the same scene, you not only have to infer the 3D shape, you also have to understand the layout. You have to understand how far or close objects are. If you're aiming to understand exactly the layout of the objects in that scene, which I think you should, otherwise your differentiable rendering reprojections are going to be completely off. So for differentiable rendering, for you to be able to use differentiable rendering, shape and distance from camera need to be inferred. So it becomes a lot more challenging. Especially if the goal is to generalize, so to be able to do this, train from video, but be able to do this from a single image. But it is a direction that this is where video can shine once again, especially these more realistic videos where many objects are present. And differential rendering can get you actually quite far. I'm hoping to get that, I mean, this is like a constant fight about making progress, even though things are kind of not like perfect yet, and being able to see some of these results and talk about them and discuss them. But again, another problem to work on.
Yes. The next question is, what do you think about using GANs to leverage 3D structure to generate more pretty and realistic images, probably with controllable attributes like color, texture?
Yeah, I mean the Simpson model has a GAN. It has actually I think it's big GAN that we're using with all the latest greatest tricks to be able to synthesize new images. But it's more important problem than just generating. It doesn't only have to be a pretty looking image. It has to be geometrically consistent. I have to tell you, this is the hardest part. A geometrically consistent consistent image is difficult to generate, and GANs can get you so far, but it's more of a modeling and understanding what representation works best, especially with models like GAN.
Okay, I think so. That's all we got.
Excellent.
Appreciate it, and thanks for all your energy and great words.
Of course, I hope that you enjoyed it. I know it was like a little philosophical, but yeah, I mean, thank you for inviting me, Vivek. And am I the last talk?
Yes, you're the last.
So, so you're done. So you're done.
Yes, I am actually.
Awesome. I hope you go celebrate.
Yes, indeed. Thank you once again. So
bye, everyone. Bye, Xiaolong, and really nice to be with you today.
Right. So finally, we have reached the closing of our event. We thank our amazing speakers for the great talk of the current research. We also thank our attendees. All the talks from our event will be shared online and will be available to the general population in the next few days. Thank you guys and have a great evening. Ciao.